सबको हम लोग आते हैं ऊपर उसमें वो टी लगा
सर हीटिंग कॉइल की जगह उसके लिए भी यही है कि आपका सर्विस शेडर लगा, जैसे सर्विस शेडर लगा इसके ऊपर आपने लगा सर्विस शेडर जहाँ तक होगी बाकी का आपका इसका आउटलेट भी अंदर चलेगा। तो ये यहाँ से वापस पाइप आपका ये एज ए पीसी पाइप यहाँ पर आ जाएगा। सर ये जब आप इसके पाइप के ऊपर लगाओ कपलर है यार ये सर्विस शेडर ही है ये नहीं, ये आप इसके ऊपर लगा के आप इसको लगा वहाँ पर होल्ड करके आप सर्विस शेडर लगा और ये पाइप आपका अगला थ्रेड होकर इसमें फंसा जाएगा। ये जो इसका आउटर है इसके ऊपर तक चढ़ा सकते हैं, ये इसके आउटर को इसमें वॉल्स कैसे फिट करेंगे सर? इसके वॉल्स आपके बट वेल्डिंग में भी ये जैसे ये है फ्लैंज जॉइंट्स हो सकते हैं, इससे फ्लॉन्च जैसे लग गई ये पाइप में आएगा वॉल्स हाँ
उसको फ्रीजिंग डेप्थ नीचे डालते हैं और कंट्रोल ऊपर से डेप्थ में डालते हैं जैसे
फिर तो हमारी पाइप फ्रीजिंग डेप्थ के नीचे चलेगी जब आप वॉल नीचे लगा रहे हैं।
नहीं वॉल्स का समझना है सर, वो मतलब वो जहाँ फ्रीजिंग डेप्थ वो आज तक हम लोग भी इसीलिए समझना है
जो आपको भी वर्केबल चीज़ें नहीं
स्प्लेंडर को आपको नीचे नहीं हाँ वो भी कर रही है तो क्या कर सकते हैं बताओ तो इसका डाउट तो अभी हमें
सारे पैनलिंग करेंगे
जो पॉलीकार्बोनेट पे शेड बना सकते हैं वही ये जो 3 लेयर्स पाइप का पाइप आता है वो आइडिया नहीं है हां उसमें सैंपल
कल
इसमें उसमें क्या था सर बेसिकली आउटर लेयर एसडीपी वाला लेयर एसडीपी
उसका पैनल
बट ये जो नीचे लेयर है या जो सस्ता जो पाइप वाली बात आती है वो भी आता है ये बीच का कोई मटेरियल उसका मटेरियल आ रहा है पर ये जब जॉइंट करने आप जाते हैं तो वो टेम्परेचर जो एसडीपी करनी चाहिए वो पहले ये जॉइंट होता है वो सब रेट चालू
ये दिस इज ये है आपका पॉलीथिन शीट चिकन मैश टेप नाइट्राइल रबर देन द रॉक रूल
सिंपल है सर आपका पाइप उसके ऊपर रॉक में आपने लगा उसके ऊपर इंसुलेशन आप कुछ भी ऊपर करते जाए वो सिर्फ सेफ्टी के लिए पाइप
टीम की बात पर भी आपको फोकस करना है टेम्परेचर वेरिएशंस में इसके क्रैक्स आ रहे हैं
नहीं सर मैं उसका हमारे तब चीज़ों के ऊपर IS अलग है और उस बेसिस के ऊपर अगर जाता है आपका डिजाइनिंग प्रॉपर है मटेरियल प्रॉपर तरीका का आया और इंस्टॉलेशन प्रॉपर तरीका है तो कोई भी मटेरियल ऐसा है 100 साल से कम आपको लाइफ
बिल्कुल आया था ये एक्सचेंज है के नाम पे ओके कोई और
तो
वो आए थे इनके साथ
22 हाँ
हाँ वही
कश्यप जी गए थे
हाँ कब से चेयर लो प्लीज
हो जाए क्यों उठते हो जाए
आ जाओ कौन 7 बज के
हाँ
और सब भी आएगा संजीव सर भी आएगा हाँ उसके लिए वो आया क्या वो बनना ही नहीं है बनना ही नहीं पेट्रोल हालत ही नहीं है उसमें तो डलर प्रपोज करनी
तो आप कल मॉर्निंग में भी आ गए आप मैंने तो ऐसे ही करवा तो किसी ने बोला बोले कि यार फिर मैं आ गया मैं अच्छा
Is it like very heavy?
light.
But the heat tape is 6 to 30 watts per watt.
And typically, who is paying for that? The municipal corporation or the individual?
Typically the municipality.
Not the individual.
It varies from village to village. Like in cities, it would be the whole way. If you know, in some of our rural villages, they're rural native villages, and so have a different financial agreement as well in bigger cities. But typically in the U.S. in most cities, the on-property cost is individual.
Typically, sir, what the walls do like walls? Is it like with the protected walls?
Houses?
No, the city houses walls.
For controlling from delivery tanks to for isolation of water from
Oh, valves.
valves.
Yeah.
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 So distribution network.
Yeah.
You have the walls. So how do you protect the walls?
Either with insulation on top.
Cover it.
Yeah, on top.
So you box it completely
Or just frequently just on top.
on the top.
Yeah, and then they thaw wire.
So again that wire.
Sometimes
Can we place those those walls in open, or those should be buried in
usually they're buried. Yeah. I mean,
certain depth below 3 or 5 feet?
in the Arctic where there's permafrost, where there's no permafrost, right? Then we bury it. I don't think you have much permafrost.
And do you have water meters also to each house?
Sometimes not.
Because water meters may get jammed.
Right.
No.
In Montana, we all have water meters. And all that stuff is on property.
How long, sir, you are yet in India?
So I'm here.
You are again going back?
No, I was going fishing in.
Himachal or
No, near Nepal.
Near Nepal.
Yeah.
Okay. So
If you have time, you will visit our Java factory.
our factory.
Oh,
Where
really?
we manufacture it.
Manufacture this all the type of pipes.
Oh, yeah, nice. Yeah, I'm going to, after here, I'm going to wrote this down so I can remember. Kancheswar.
Okay.
And return you are from Delhi or via Bombay?
Delhi.
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 Okay, next time,
Yeah.
please plan to
Yeah,
visit
yeah.
our factory.
We have,
Very nice.
we are manufacturing 450 tons per day SDB pipes.
Oh, really? Oh, wow. Great.
And we are largest
Manufacturers of piping and drip irrigation.
drip irrigation.
We are also in food processing. We have got mango pulps, purees, onion dehydration, vegetable dehydrations.
Oh, really?
$1 billion.
Oh, wow. Awesome. Great.
We are manufacturing solar water heater systems,
Oh, really?
solar pumps.
And now we are into hydrogen to electricity.
Oh, really? Wow,
Green
wow.
hydrogen.
And then you sell a lot of this here in the north?
In all over India.
All over India.
Where it is required, we will do it.
ते पण त्यांना ते एक्स्ट्रॅक्ट पाहिजे स्पेसिफिकली तुम्हाला जे पाहिजे ना त्यांना पाठवून आपल्याला
आता एवढं एक्सपेक्ट
Nice.
Also in agriculture, horticulture, plants, greenhouses.
You buy the raw polymer?
Yes, raw material.
Craig Bulant, Mr. Nandilaksh Kodhari, Dr. Ramakant, Mr. H.V. Patel. We'll start with the lamp lighting first.
शुभं गुरुत्वं कल्याणं आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोस्तुते दीपज्योतिर्नमो.
Thank you, sir. Thank you, Dr. Ramakant. Thank you, Dr. Prem. Thank you, Mr. Nilaksh. Now I request Dr. Ramakant to have to say a few words for us.
Good evening, and first of all, I would like to thank my friend Nilaksh, and Dr. Prem, Mr. Patel, and wonderful friend Mr. So actually, when this concept for holding workshop in Golden region has come to my knowledge, and I heard from Mr. Patel and Mr. Kothari, then personally I requested all of them that I will join your conference because I want to learn what is actually happening in this Golden region. So if you see the manual which is released recently, water supply, that is called Manual on Drink from Tap. So in that manual there is nothing more mentioned about the water supply system, how to plan in the Golden region, what could be the technology that should be implemented very well. Though I was discussing with Mr. Shah that I personally appraised the DPR for Leh Ladakh for water supply sewerage solid waste about 9-10 years back. So there they proposed the WTP should be under the ground below the freezing point. So though it was on the paper, but I have not seen anywhere, particularly in the Golden region where the snowfall is going on. So it will be, I think, my great experience to see all of you and learn from all of you what type of technology, what type of planning is required, what is actual conditions on the ground when we go for implementation of the water supply systems. So these are the only my request, that you should call me. Then he called me up and I got the permission to attend this workshop because of only that what is happening in the Golden region. And this evening is very beautiful for me because we have a lot of wonderful friends here from the states, particularly Himachal Pradesh. So we are very happy to be here, and it's my honor to be here to attend this workshop. So thank you very much.
Thank you. Thank you, Dr. Ramakant.
Good evening, friends. I am H.V. Patel. I am chairman of the Waterworks Association. I know everybody has heard of AWWA, but AWWA India has recently commenced its operation as an independent body in India for the last 3 years. And we have been doing a couple of annual conferences. First was in Varanasi, second was in Jaipur last year. And we have a very heavy presence from all states. And we felt that there are certain regional problems that need to be addressed in a focused manner, in a focused platform. So I think Dr. Gill from Himachal Pradesh is a regular attendee and a very passionate member of AWWA. And we have been discussing with him, and we felt that we need to address this issue which has not been properly addressed before in Indian context of operating water utility in a freezing weather conditions. We thought that as soon as the winter is over, we should time it. But unfortunately, with the elections and all that, it's a bit of not suitable for the other states. But I'm very much thankful for the good support that I received from Himachal Pradesh officials. And also extend thanks to our colleagues from Leh, who also, due to shortage of time, but they have spared 2 days to attend this workshop. I also thank our chief guest, Dr. Ramakant, who has also spared this valuable time from his heavy appraisal schedules from office. And but it is his personal interest that has he has made up his mind that he would like to attend at any cost. So that's this bill that has brought him here. Dr. Craig from USA. We have a brief introduction already laid out in our flyer, but to give you an insight, is Dr. Craig has been managing utilities in Alaska for the last 20-25 years. Also in the state of Montana, he has been working with water utilities. These two states are known for its heavy freezing conditions. Currently, he is with the Montana State University as the head of civil engineering department, and we are lucky to have him with us. We have Nilaksh Kothari. He is Indian by birth, but then he has planned to settle back in USA after his studies. Nilaksh has got a unique experience of working with is a CEO of a water utility in Manitoba. It's a very northern part of America, and it's got at least 6 to 8 months of heavy winter, if I'm not correct. Right? Yeah. So, so he's got he's been a head of an organization which run power, water and wastewater. So it's a totally utility management experience he has. So we could draw out of him whatever we can and make it. And he knows the Indian context as an Indian, so it was good of him to make this travel and share his experience with us. I also thank the sponsors which has made this whole event possible. Jain, Unipro, RG Industries, and our long-standing Mr. Jadhav from Maharashtra. They have been supporting AWWA for the last 3 events, and this is the continued support that we get them on the events. We would basically like to have certain roundtable discussion format today evening. Is we'd like to know from each of you in terms of what are your experience and what are your issues that you would like to get it covered in terms of some sort of discussion or presentation that we are going to do tomorrow, so that the speakers and the other experts that we have, they get some insight in terms of what kind of issues are there, and they could deliberate on those issues and have a more focused discussion on those issues, which would help you to carry some knowledge back from this seminar. Once we're done with some question, basically it's a roundtable discussion, it's an informal one. Once we are done with that, we'll start with our cocktail dinner, and we can continue the discussions as we go along. Tomorrow's program we will try to start around 9:30 is what our target is, so that we get enough time for our chief guest, Dr. Ramakant. He wants to do a talk on about the new CPHU manual that has been launched by the Ministry of Housing and Urban Affairs, so that we are familiar with that and how it can be more useful to the water professionals for India. Then we will start with the workshop by Mr. Craig and Nilaksh. We would also like to give some time to the sponsors, so there will be some presentation slots, maybe before lunch or after lunch as per the schedules that permit us. And I hope we should be done by 4:35 by tomorrow. So I'm just trying to update so that people who are planning to head back to their busy schedules can keep this in mind. And I would ask Arul,
Yes.
yeah, kindly give a welcoming bouquet to our chief guest. So with this, we are done with the formalities of honoring the guest. How would you like to start? I believe people are sitting with the state, I mean, in terms of a group format, then we can start with Himachal Pradesh, which was the highest presence. So what we would like to know is what is your background, where do you what kind of work you do, and what are the issues that you face specifically to the topic of the seminar and workshop. So we could stay focused on your background and then your issues. So we can start with, so Jain, you can just, give your a bit background.
We are from Jain Irrigation. My name is Dr. Madhusudan Chaudhary. Basically, we are the HDP and PVC pipe manufacturer. So we have the new product puff insulated HDP pipes, which can be used in the sub-zero freezing temperatures. So we have the samples outside this conference hall. So in case you have some questions, we can discuss also.
Yes, again, I'm from Electro Steel Castings Limited. We are the manufacturers of the ductile iron pipes, and we have a presence in about 40 countries, including the US and UK European markets. And we are manufacturing the ductile iron pipes in the range from 80 mm to 1200 mm there, in both the classes, like I will go by the Indian classes K7 and K9. And recently we have come up with a new kind of jointing which is especially used in the hilly terrains where you don't require the thrust blocks, etc. in the anchoring. That's a double chamber restraint joint pipe. So it's an ideal kind of pipe which is can be ideal for the panacea for the hilly regions where you don't need any thrust blocks. And we are also foraying into, as Mr. Jan said, that into insulated, pump insulated. And our European contemporaries are already using those pipes in the ductile area using the pump insulation. And we are trying to foray into that market. And in addition, if there are any questions, I'm here for the session. Thank you. Has also been introduced and approved in the recent advisory of the CPHO, which has just been issued. The Government of India CPHO advisory. It has also been introduced and incorporated as a jointing system in the latest CPHO advisory.
But now, instead of advisory, to go for the manual, whether that content is given in the manual or not. So now the advisory is absolute because of the release of the manual, all advisories.
Yeah.
Absolute. So just check in the manual also. That's available on the website.
Okay.
If it's not there, then
Okay. Okay.
Fantastic gathering on the stage. Experts of the experts, topmost experts of the freezing water condition, from the Alaska and from Manitowoc, and to listen and to know everything and to put in the Indian context is Dr. Ramakant. First, the very basic thing I would like to start. As a very junior student of these conditions, what is the permafrost line or the deep freezing line in these regions? Is it required to lay your pipelines below that depth? what happens if you lay the pipelines above that depth? What is the MOC of the pipelines you suggest if you lay the lines above the permafrost line? What is the MOC of the pipelines if you lay the pipelines below the permafrost line? Number one. Number two, I'll start right from the beginning. How do we design our intake works, raw water lifting from the rivers, or as I heard from the Dr. Gill some time back that at many of the sources in Himachal Pradesh, now they are going for the river water supply. At what depth the intake has to be there, whether it has to be below the freezing conditions or anything, I really do not know anything. I have no knowledge about it. Number three, coming to the water treatment, in which I have got some kind of expertise. Can the people from Himachal Pradesh explain us the physico-chemical parameters, bacteriological conditions of their sources, which our plants are going to treat? Number fifth is that, is it required to run the water supply scheme 24/7 to keep the water supply flowing? Again, that question is related back whether you are laying the pipeline above the permafrost line or below permafrost line. So whether the taps are going to run continuously for 24 hours. Again, I am telling you that I have got no knowledge about it, but since the experts are sitting on that stage, I am addressing your concern. And fifth is that, what is the effect, what is the lowest temperature of raw water you have found in Alaska and Manitowoc in the worst winter season, and how it affects the water unit processes in terms of loadings or the backwash rates, etc. What is the efficiency of chlorination or anything other measures are required to be taken? Thank you so much.
Myself, Upendra Vaidya, I am working as Chief Engineer in Mandi Zone. Basically, I am looking after approximately 3 districts in Himachal state. So, but we are talking about the anti-freezing system in the water supply. We require it in our one of the highest district of the state, that is Lawrence Spiti. So, I am concerned for all part of that district. Till now, we are supplying water supply. That is true. We are supplying water supply, and the water supplies mostly they all are based on the spring sources only. So in the winter season, like nowadays, we are struggling for supplying water in household connection because of the reason, one, the sources are getting freezed and the discharge is getting very low. So in that scenario, what we are doing, we are not being able to supply the water in the household connections. We are simply putting on the water supply in some few public stand posts for the local public, so that they could survive their livelihoods. The second point is what he has already asked for, that is, if we lay the lines below the freezing line, and if it is being laid on the above the freezing line, so what is the criteria behind? Till now, we are just using HDP pipes in those winter areas. We are not using insulated pipe systems till now. And now, third point is that what about the SRs, that storage tanks? Because we are having, most of the tanks are RCC structured. So if we are going for any type of, any puffed panel type of structures, so what are those type of things? We would like to know that also, because we are also finding the problems in that part also. And above, most important is the WTP point, that is the water treatment plant. Sir told that in Hill, this Leh region, they have proposed the underground WTP, but I don't know if it is so and how it could be happen. So these are the few questions in our mind as far as GSV department is concerned. So we want to tackle those blinded, and we are eagerly, anxiously want to know the technologies what you are adapting for. So we are quite excited to see these also. Thank you. Thank you very much.
From Shah Technical Consultancy. Recently we are working in water treatment plant and water distribution network in Kargil town. We have discussed the issue with Jain irrigation people also about their pipeline which they are providing, insulated pipeline. But as you all know that Indian market is a price sensitive market, and the insulation which needs to be worked out at -30° temperature is becoming very costly. So I would like to know if there is any solution. Okay, obviously we are planning to have a pipeline network below the freezing line. So that's okay, but above freezing line, if there are any other options, I would like to know.
Pass the mic to Lady.
Good evening. Myself name is Kacho Mumtaz, Executive Engineer, PhD Division Leh. When we get this invitation from AWWA, so we were very eager to join this because the workshop, the planning and management of water utility in freezing weather was a relevant topic for us because our main challenge is freezing. So we have completed almost 100% of Jal Jeevan mission in Ladakh, but the main challenge is keeping it operational in winter. So we have devised so many local technologies. We have laid the pipes below 5 feet frost line, below the frost line, and still we face so many challenges in running and maintenance of this system. Also, and we are hopeful that we will get some good suggestions and good this knowledge from Mr. Craig and Mr. Nilash. And one more thing, we are going to construct a water treatment plant in Leh. So it is an open, open, it will be an open. So how we can keep that, this prevent from freezing in winter. And we are hopeful that we will get some good suggestions and good feedback from our distinguished speakers. Thank you, sir.
What is your current practice? How do you manage nowadays? Particularly during the winter season?
Winter season, actually, first of all, we lay the pipes below 5 feet, and most of our service reservoirs are covered with earth. It is, you can say, it is underground. And the main problem we face is the delivery point. Unless and until we keep it running, we can say leading at points, there's every process, apprehension of freezing. So one more challenge is that when we keep that running, there's this problem of icing in the area because the wastewater gets to freeze and ice accumulate in the area. And that is in congested area, that's a big problem here. And one more thing, where we cannot lay the pipes below freezing line, we have applied insulation with the pipes. And some at most of this our source of this spring. And one more challenge is that our source are in higher ups. And in winter, avalanches and extreme cold damages our source. So this is a big, and avalanche come, we cannot restore the source. We can do nothing at the source. And for that, we hope that we will get some good suggestions from our good speakers. Thank you, sir.
Myself is Iftikhar Ahmed. I'm Assistant Executive Engineer in PHE Leh. Sir, I think we have done 24/7 project in Leh, which is running successfully from last 3 years. So, as per everybody is asking, what is the methods we have adopted in this running 24/7? First of all, it varies from area to area. soil conditions, what is the frost line. First of all, we have to find out the frost line. That is one of the important aspect that you have to find in your areas. What is the frost line? For example, the area which is in the town, it is called one zone, it is called the Ganges, where we have found it is around 5.5 feet is the frost line, and we have laid the pipe at the 5.5, you can say 5 feet, we have laid the pipe. So our main lines doesn't get freezed. Now the questions comes, it has to be come out from somewhere else to the household, because at the delivery point it has to come out. So what we have done, we have used heat tracing cables to accommodate this insulation. I cannot say it's an insulation, but it is a kind of a defrost method. So what we do in the evening time, they switch on this heat tracing cable so that it will not get freezed. The areas where it is possible and where you want to run 24/7. One aspect is that we have done it in town where we want to run 24/7. And one village where we have done it at 24/7, but we are providing 70 liters in 24 hours by using drippers as per the family strength. It's a pressurized system. So as you all know, one thing is to make the flow continuity. So to make the flow continuity, it is possible that you have to make it a pressurized and using the drippers. For example, if the family strength is 10, you are providing 700 liters in 24 hours by using the family strength. If it's a 5 members, we are providing 350 liters, but in a 24 hours. So it is one success story with what we have done in rural areas where you can done, as Chief Sir is asking for the source for the source, what we have done, we have constructed a greenhouse at the greenhouse so that the source will not get freezed, and wastage of water is very less, because if you will keep on the tap open, there will be a lot of wastage of water, but here the wastage is very less. So we can adopt in the rural areas by this kind of dripper systems can be used so that wastage can be minimized, we can use. And third thing what we have done for the intermittent supplies in Jal Jeevan missions, what we have done, we have kept our valve at the lowest point. So after supplying for 2 hours, 1.5 hours, whatever your timing will be, after that we will flush out the pipe so that next day there will be no issue of freezing. Third is somebody is asking what should be the RCC, they are making these reservoirs. What we do 1.5 meters of earth cushioning, good earth cushioning, and maximum it will be in 1,000 of gallons of water, and it will not get freeze in that short period of time. Within 24 hours, it will not get freeze. That much of cushioning is, we have done it from a long time. It's a very proven success story in Indian context, that if you 1.5 meter of cushioning you will done. And for the valves, what we have done, one of the valve of the reservoir is used as a heat bank for the valves, so that the heat that are dissipated from the reservoir it be used or used in that chambers so that the valves are not get freeze. Otherwise, mostly what we have seen that valves are kept separately, and that chambers get freeze and the valves are getting freeze. So if you used one of the wall of the chamber as a reservoir wall, the heat which is dissipated from the water, it will be consumed by that chamber, so it will not get freeze. These are the and anybody we can ask these are the what we have done. I'm telling you, and I think we will learn a lot of things from others. But these are some of the challenges what we have faced and what the solutions we have found in our own context, and the best things what we can do it in our locality. And we have done I think we have got some videos. If anybody want to share it, we can share the videos also. And if it's time will be permit, we can share you some of the videos. What are the best techniques we have done in Ladakh? Thank you, sir.
So I have two concerns. First is, you said that you are going to create a greenhouse effect at the tapping point basically. but the source may be coming from far away from your tapping point. So if the source beyond the tapping point is freezed, then what will happen?
Most of the
So your in-house effect will not work on that area.
The source is, most of the source are the spring source, and the temperature will be around, it will be 10 to 12 degrees. So source freezing will be not issue.
Not issues. And the second thing, you're talking about this surface reservoir that should be below 1.5 meter of the ground. In that case, we should not go for the elevated reservoir. It will only be a ground reservoir.
Yes, sir.
Yeah, no elevated.
No, we haven't got a HTC, sir. We have got a surface reservoir on the top of the hill.
Oh yeah.
And we keep it earth cushioning from all the sides.
Okay, thank you.
Thank you, sir.
Nipro Techno Infrastructure Private Limited. We are EPC contractors in the states of Himachal Pradesh and Uttarakhand mainly, and few more states presence we have like MP, Manipur, Rajasthan and UP. So our main area of working has been for last 25 years been working in Himachal Pradesh. So these have been challenging tasks which we have been, our department have been looking for, and today I think and tomorrow many things will be enlightened to us so that our water supplies in the freezing areas does work. We do have experience in working in semi-freezing areas which we are doing, like in Chamba, Khajar, some parts of Shimla and Kasauli, Dharampur. But not yet we have worked in too much in freezing areas. Recently our department has floated some pits, and they are also very keen, and we are also very keen to know the techniques, and so that we can put our expertise in this anti-freezing, and we are looking forward for the sessions. Thank you very much.
I think working in Lahaul Spiti is really a challenging job.
Yeah.
Yes, that is.
We have heard a lot about Lahaul Spiti and Ladakh.
Yeah.
We are very happy to see you here today.
Basically, sir, we have adopted the same structure what they are doing there.
Yes, yes.
So let's see what it happens after that.
Thank you.
So I have a question that same questions about water supply, but what would be the action with respect to wastewater, because every household releases the discharges the wastewater from each household. So what would be the action when freezing point, below freezing? How to keep it running in the drains?
Just sharing my experiences in the cold region. I worked a lot in Sikkim on Gangtok water supply scheme, where the raw water is tapped at the 40,000 feet from a glacier. And the main impurities which are found in the raw water which comes down is the sand and mica. Only when the snow thaws, a little bit of turbidity around 10 to 15 NTU comes to the water treatment plant, and they have a full-fledged water treatment plant. So I want to really share this information with my friends with Himachal Pradesh. Do you have the same experiences as far as the impurity of contamination of the spring waters in your region? Number two, Dr. Bullard, talking with Dr. Gill some time back, there's a water treatment plant coming in a place called Kelon, is it? It is at the elevation of 10,000 feet, and it is the water source is one of the river or the rivulets. The scheme which is given is the desilting unit prior to the water treatment plant. I do not know what is it must be something of pre-settling tank, and then the water treatment plant. Now this water treatment plant is supposed to be enclosed in a anti-freezing room, since the temperature are freezing and there is snowfall. I have seen many pictures in the AWWA manuals and off-flow that in the winter regions you have got some kind of a structure around the water treatment plant. The roofs are sloping 45 degrees, and there is some kind of insulation to the building material to keep the plant flowing. So if you can enlighten us tomorrow on this aspect, I will be highly obliged personally. Thank you.
My name is Shirish. Currently, I am a consulting engineer, K consultation, and I was on the expert committee of revision of manual looking after the chapter of water treatment. Unfortunately, as Dr. Ramakant has said, that we have not dealt with any freezing or the low temperature regions in India in our CPHO manual. After interaction about tomorrow's seminar, definitely we will propose some relevant things with Dr. Ramakant's help and the support from Dr. Deen Dayal. Thank you.
Yes, of course, because I just come here only to understand, and because really I am not aware what is happening on the ground, as I said. So if I learn from you, I will get some good case studies, then certainly I will take this matter in the form of the advisories. That's not even, I know that is not an issue, but we can just frame our advisory based on your inputs, your suggestions, and your best practices.
We get there very long back, but we chased the e-portal. Value of packages were small.
No, when you are talking about the EPC contractor, you should not think about the package is a small, large. So no, you have to perform, you have to work. That's all. There is a small, large. You are not only work for Lahaul Spiti, you are also work for this Leh. So you are the contributor for the country. We have to work everywhere. Don't say that small package.
Economics were not coming. We tried to.
No, those who are working with them, they might have also
mainly I think local contractors. Yeah.
And the experiences that you have been facing so far. I think we take away this thing for tomorrow, and I would request everybody to join for cocktail and dinner.
वो तो मैं दूंगा ना, इनकी क्या डेरिंग है करनी चाहिए।
हाँ ठीक है उसमें
दोनों ही।
It's pretty busy.
I like Grover.
It was a very warm winter.
आप अंदर के सर्व करो।
कई जगह तो जो अपर
I hope everybody had a good sleep yesterday. In the morning, we will first take up with Dr. Ramakant's presentation and talk about the new CPHU manual which he was referring yesterday. After that, we will start with the discussions and presentations of Dr. Bullard. Dr. Ramakant.
Himachal Pradesh, Solan. I was supposed to call here for study function as chief guest or whatever, but I thought I should make some presentation before you in regard to the new manual on water supply systems, which is released on 5th of March. That is available on our website, Ministry of Housing and Urban Affairs website. If you go to the English version of this ministry website, you will get it. If you go to the Hindi version, which is not there. So just remember it, you should go on the English version of our website. So today I will only discuss about the content given in the manual in regard to the colder region or hilly region, what is mentioned in the manual. And whatever is written in the manual, that I will show you here. I'm not going to take extra from the market, from this implementer, executor. So whatever is written there, that I am going to present before you, so that we can get input from you all. What correction is required. The manual is recently released, but immediately we cannot go for any correction in that manual. But so of course we can go for release of the advisories, keeping in view of the implementation of water supply system in colder region based on your inputs and best practices. System, as we all know, that the water supply is intermittent in all over country, and it's varying from 2 to 6 hours. The national average is coming about 2.3 hours per day because of the so many regions. And if you go for the intermittent water supply, there is a chance of contamination of the water supply in the pipeline during non-supply hours. And it is a high NRW. As we all know everything, what is the problem in the intermittent water supply systems, the high NRW, then there is no metering at the household level. Because of that, we are not getting to collect the proper revenue for maintenance of our systems. And unbilling water is also going to be wasted, lack of commercial orientations. So there are so many issues with this current situations in the water supply systems. So you see some values that though we have ample amount of water supply in our various cities, like Goa we are supplying 341 LPCT, that is only for 8 hours. Chandigarh 332 LPCT. So we are saying that there is no water available in our cities. Yes, water is available, but we are unable to manage it in a proper way. That is our concern. We have sufficient amount of water, like if you take over the daily, we are providing 223 liters per capita per day, but we are supplying only for 4 hours. If you go for 135 LPCT naturally, it will go up to 10 to 13, 14 hours. So it's only management of the water. By keeping this in view, the Puri is the first city in the country that they have gone for 24/7 water supply systems. And anybody from us, they would like to go to see the Puri system. It can be facilitated to all of you. But I think my request would be you just go and see there what is going on. But that is for not for the colder region, it's for the plain areas. So keeping this in, what is the government of India vision? The vision is to provide the continuous water supply, 24/7 water supply system, which is called as drink from tap, which reduces the NRW, and equitable distribution of water is very important. So that if you go for intermittent water supply system, we are not getting water at each and every household with the same amount of water. So if you go for 24/7, that will provide equitable distribution of water. Then we have to gradually shift to 24/7. It's not a task of 1 day, 1 year, 2 years, 3 years, 4 years. It will take another 10, 15, 20 years to move from intermittent to 24/7 water supply system. So we have to gradually move towards drink from tap facilities. So this is one of the pictures for drink from tap facilities that we have to provide water for 24/7. And the water should be very clean, and the pressure in the pipeline should be continuously maintained throughout the time. So what are the advantages of 24/7 water supply system? That they will prevent the contamination in the pipeline, contamination of water in the pipeline, reduction of waterborne diseases, reduction of NRW, equitable water distributions to all households, ensure adequate pressure throughout the pipeline, throughout the days and night. Then life of the network will also increase, because if you go for intermittent water supply, there is a chance of corrosion of the pipelines. So that will increase the life of the pipelines, reduces consumptions. It is presumed that if you go for continuous water supply, then the water requirement is not 135 LPCT. It is going down to 120 LPCT, even it's going to 110 LPCT per capita per day. So there is a savings of water in that way. So, and elimination of household storage. If you go for, if the people have faith that they are getting water 24/7, so there is no need to store water by providing this tank at the household level. So that can also be limited, and that is one of the reasons to save the water at the household level. Consumer satisfactions, everyone willing to pay that we are getting the safe water, secure water, good water, so they are willing to pay with the water utilities. So keeping all this in view of drink from tap facilities, Government of India, as we all know that we launched this Amrut 2.0 on 1st October 2021, Amrut and Amrut 2.0 subsequently. And the outlay of this Amrut is about 33,425 million USD, and out of which the central share is about 9,261 million USD. And the target is to provide 26.8 million new water tap connections at household level in 4,800 step-living towns. And the major focus on this mission is to reduce NRW up to the 20% and provide 24/7. It's a mandatory for each and every city that they have to do the piloting in one ward, at least one ward, in one city for 24/7 under AMRUT 2.0. Even though city is willing to take this 24/7 throughout the cities or towns, they can go for it. There is no condition for that. You have to go for only one ward. But one ward is the mandatory in the guidelines. Then we are also emphasizing on this recycling and reuse of treated water, treated used water. That should go up to the 20% of the total city water demand. And industrial purposes, it should go up to 40% of their industrial demand. So these are the major reforms which we are going to achieve in another 3, 4, 5 or subsequently in the next time. So when we talk about the drink from tap facility, there were no guidelines at the central level or country level. So we revised the previous manual water supply and treatment, which was published in 1999, and that manual is now this manual is called as Manual on Drink from Tap Facilities. And this manual is published in 3 parts: Part A, Part B, and Part C. Part A is engineering, that's for planning, design, and implementation. This is the 4th edition, and the Part B is the operation and maintenance. This is the 2nd edition. And Part C is on the management of the drink from tap facilities. So this is the completely new version of that one. This is the first version of this manual. Other than that, we have also this sewage manual, solid waste manual. You all agree with most. There is no need to explain everything here. So what are the salient features of this manual? The manual is based on the drink from tap facilities concept. The GIS-based hydraulic modeling applications, that is very mandatory for this new concept. Then, when in the previous manual, this residual pressure was varying from 7 to 12 meter. Now it is a change for class 1, class 2 cities and other cities towns. So 17 to 20 meter that should vary for class 1, class 2 cities, and 12 to 15 meters at the consumer end. The pressure should be for other cities. Then the reason for that 71 to 20 meter is to provide the water up to the 4th floor, so that the gradual elimination of the storage time at the household level. Peak factor initially it was varying from the population to population, 50,000, 1 lakh, 2 lakh, something like that. So there was a bracket for the populations to get the peak factor. Now there is a straight way we can take 2.5 peak factor, is irrespective of the population, whatever it is the population of the cities. So you have to take 2.5 for designing of the systems. Then when we talk about the drink from tap, we have to go for the operational zone basis and DMA basis. This will give you the better picture for the maintenance of the systems, because the entire city is divided into different zones and the DMAs. That will also give you the reduction in the NRW, and that will help for the water audit, and based on that we have to take the initiative, we have to take the measures, what measures is required for control of water. Adopted concept of equitable distributions of the water system when we go for the DMA-based system or operational zone systems, that will provide you. Some new technology is introduced. It was not there in humans, it was not there in the previous manual, though it's in the market. So based on the technologies about the VFD, variable frequency drive pumps, new and advanced methods of water treatment, and this chapter is written by our Mr. Sri Skadile. So he has given a lot of input, a lot of advanced technologies, their applications in these chapters, and AWWAIndia with the SCADA and IoT applications. And the last one is the management chapters. In fact, management part of the manual. Other than that, these are some of the technical points, that the capacity of ESR should be 1/3 capacity of the water demand in one operational zone or one DMA. The storage reservoir of MBR is having capacity of 3 hours storage of ultimate water demand. Then capacity of raw water sum or clear water sum should be 2 hours of storage capacity of the WTP capacity. Previously, if you see the previous manual, there was only one formula given for the fire demand calculations. Now we have bifurcated it for two categories. One is for the cities having less than 50,000 populations, and the second one is the cities having more than 50,000 populations. So there is two formula given. Based on that, you can calculate fire water demand. So these are some of things related to the hilly regions. It's particular to the hilly regions that was given for this common for hilly and plain regions. So these are some of this contents given in the manual. If you go for the planning and design in the hilly regions, that we have to make operational zone in a such a way that the number of house connections should not be more than 6,000. That we cover about 5,000 populations. Number of household connections in one DMS should be about 300 to 1500 connections, depending upon the operational zone and DMS. All DMS should be hydraulically isolated, for which zero pressure test shall be planned. The minimum size of the planting pipes is proposed at 80 mm. And for the secondary line, for the other line, we can go for the 63 mm. If the system is having existing water supply system, if you go for the replacement of the pipes, so we can retain up to the 63 mm entire pipe in your systems. For secondary pipes in a small lengths, before to the house service connection, we can go up to the 32 to 63 mm pipe as per the local conditions. Then the value of exhaust rating can be exceeded. The velocity should be less than 2.5 meter per second, should not be greater than that. Otherwise, there is chance of corrosion or some other problems. Metallic pipes are preferable. See, I am just writing here because this is written in the manual. So, metallic pipes are preferably suitable due to undulated topography and rocky land. I think some of the actually also from the PE pipes, FGP pipes, they can discuss about this matter. The placement of isolation valves should not be exceeding 50 houses per connection. So, at every 50 houses connections or less than that, we have to provide the isolation valves. PRV are also needed in hilly regions because if the ESI is on the top level, so there is more pressure in the pipe network, so the chance of worst. Recently, we received a case from the Guwahati that the pipe network was worst because of the low workmanships. The selection of pipe material is based on the IS 6295/1986. And PVC is not recommended in case of exposed to freezing conditions. This is written in the manual. A new PVC pipe shall be buried to depth unlikely to experience freezing temperatures. The level of thrust line is generally varying from 0.9 to 1.2 meter. The study we are talking about the thrust line where it is. When we place the pipeline below the frost line or above the frost line, what will be that? So we'll discuss, we'll see in the presentation because I really do not know what will happen. So I cannot speak about that one, I cannot reply for that one. So we'll get some information from Dr. Blake, what will be the process for that. And STP pipe is preferred where there is a high risk of freezing. It is corrosion resistant and not affected by extremely cold conditions. Pipeline should be laid down below the level of the frost line to avoid freezing, that we have already discussed. Well consolidated bedding of clean earth or sand under, around or over the pipe should be provided. Bedding is very important. Normally we are not thinking about the bedding, but bedding, particularly in the colder region, bedding is important. Material for insulators of the pipe is to be with the straw, grass, acid cloths, stripe or jute wrapped over with gummy and painted with vitamins. So study we will also discussing about the what should be the isolation material. So these are some of the materials given in the manual. For the efficient operation, the available heat in the water shall be economically used and control the freezing of the water in the pipeline. House service connections shall be kept operative with the use of adequate isolation at exposed area. In the temperate regions, taps are run to discharge. See, we were talking about the how to avoid the freezing of the water in the pipeline. So it is suggested that we have to just keep open the tap and the water should drip out from there, so that water should not freeze in the pipeline. If the water is flowing in the pipeline, there is no chance of freezing in the pipeline. But the concern is that when we just allow to drip the water from tap, there is a chances of freezing of the water at the surface or nearby area. So that we have to see. So, as I already explained, the document is already released and available on the ministry website. As part of the manual, we have also constituted national level task force under the chairpersonship of Additional Secretary Madam Tara, and by adopting the members from the various sectors, various field experts. And that national task force shall coordinate with the state level task force. I think about 23 states they have already framed this state level task force. And we are regularly coordinating with the state level task force. In fact, Himachal has also framed a task force under this chairmanship of Dr. Gill. Dr. Gill is the chairman. So we are regularly having workshops with the states, capacity building, knowledge sharing, knowledge exchange of knowledge. So we are regularly doing with the states. Just to achieve the drip from tap facilities in nearby 5, 6, 10 years. The target is about next 10 years we should converge from the intermediate water supply to the continuous water supply systems. So these are some of the presentations. If you have any observation, come we can discuss. You can write to me so that we can issue an advisory letter on after getting all this information, discussion, case studies. So that's all from my side. Thank you very much.
Talking about the success story of 24/7 at Puri. Last year we have went to Puri. Now we have a very limited time there, and we discussed there that storage tanks are still there. We are saying that it 24/7 it 100% eliminate the storage tanks. Then I said, then why the storage tank we are seeing in the city is there? That we didn't have a confidence because damage we cannot avoid. Damage of our system, and when there is no water in our house, then from where we have to fetch the water, because line in new roads, so many work is going on. If the line is break, then we are not provide water. And now you are talking about the hills, and you said that we have made a provision of only 2-3 hours storage at the WTP or 1/3 storage at the distribution level or the DML level. When we have so much little storage, and we are saying that you do not provide storage tank at your household, and in hilly regions, whether we are transporting water from 100 kilometers or 200 kilometers of lines, and huge distribution system, how we can avoid the damage, then there will be no water.
Agreed.
And one more question. I think from Shimla, SAPN nobody is there. They have tried in one of the ward at Sanjoli 24/7, and they have awarded the work I think 3-4 years back. But still there is no success, and people again requested to switch over their question back to the same system. So it will be a long way to take confidence for 24/7 in my opinion.
I agree. Why it was not happening usually? What is the reason?
Yes.
Why they are switching over from 24 by 20 intermittent?
Because people are not getting water at one place. They have very high pressure, and they are not getting the water.
They are not getting water because of the improper design of the systems. They are not getting water because of the system. We have to go for 24/7. It's not like that. The system is not properly designed.
So what are the drawbacks there? That
personal experience, and I want to add something. Sir, in hilly areas we have sources like nalas or rivers, especially in monsoons when flash floods comes. So we have a major issue there like turbidity. So we can't stop that.
Yes.
So there is no such appropriate or such a proper system in this. We don't have such type of technology that we can we can, I just want to say that we can handle the raw water like whose turbidity is like more than 10,000 NT or something more than that. So in that scenario, what he wants to say that we have nothing to do just to stop the just to stop the intake point. So when it happens in any scheme, like if you are saying it is a 24/7, and that too without any addition of buffer storages. So how could we supply the water supply when we have stopped the intake point itself for a week or for 10 days together? So what would be the scenario in that?
When we talk about the sedimentation tank, pre-sedimentation tank, there is certain design criteria given.
Sir, that is
design means that if you store the water for 2 days, all the party will settle down. It will not settle in 2 hours or 3 hours. So there is certain guidelines now for if you even go for the.
I do agree, but for that we need practically it is not possible. We don't have such type of large areas in those places where we can handle that sedimentations there. We need an area, huge area for that, for settlements. But it is the personal experience. It is not like we are saying otherwise. So what is the criteria for 24/7 at that time that we want just to know?
There is no criteria given for a storage of water.
Can't we go for buffer? Can't we go for any buffer storages?
We can have provision, but it's not within the manual. It's not yet required because we discussed with the EA people. They said that you don't need to store water for 2 days or 3 days. So if you provide 2 sedimentation tanks, one at the intake, the tapping point, and second before to the WTP, there is sufficient for that. One at the tapping point.
Capacity of the storage tank will be such that
storage.
So that for that you have to take a dedicated power corridor. Dedicated power corridor. Without that, you cannot provide 24/7 water supply system.
But damages disturb power also.
So damage is everywhere. No? There is no damages. The system is not designed for every damages. No system is designed for every damages. आप ब्रिज बना रहे हैं तो सोचते हैं कि ब्रिज गिर जाएगा तो फिर क्या करूंगा मैं? ऐसा सोचता है कोई? ब्रिज कैसे बनता है? पर्टिकुलर डिजाइन गाइडलाइंस है उसके हिसाब से हम ब्रिज बनाते हैं।
हमें लगता है कि बफर कैपेसिटी जब उसमें डाल देंगे तो हमारा सोल्यूशन मिल जाएगा।
Buffer capacity can be given for 3 hours, 4 hours, 5 hours, 6 hours, not for 10 days or 5 days.
Sir,
Bridge cannot stop line, but if water stops.
Like a water resource, you need to work with your water resources department or irrigation department who is dealing with the water resource and try to create a natural pondage or some storage of that sort, which is not a burden on the drinking water, but it can be preserved and used for drinking water. Because we have such symbiotic uses even in Gujarat, where the irrigation department is given the onus of creating a water storage, and during the drought or when the dry season, the water storage is made available for drinking water purpose, and it's not a burden on the water utilities. So a symbiotic approach needs, because what you say is very apparently a problem, and you need to resolve it by creating a storage. But if we burden it on a drinking water cost, it is not going to be a justifiable thing. But you have to treat it along with the water storage with water resources department, and they will also use it partially for some irrigation purpose, or they will also partially use it for drinking water purpose. Some dams are 100% drinking water in our state also. So it's the responsibility of the irrigation department, but the 100% storage is used for drinking water. So something of that sort will need to be worked out.
But sir, his concern is also very valid point. And we have to provide some additional storage for drinking purposes. It might be 6 hours, 10 hours, 1 day, 1 day. So that's a valid point that we have to think about it. But not 10 days. 10 days is not our point. 10 days is not our point.
Sir, I have a point. Since I have
one day we can consider, we can see, in fact, we have to see the situation where it is coming out. Based on that, we have to take decisions. It's not very hard and fast that we are not going for that. We are open for that.
If we are going for 24/7,
yes,
then we have to do
We have to have some buffer storage. Yeah, I agree with you.
That is
I don't deny that.
If it is not 24/7, then there is no issue.
Yeah.
Then there is no intermittently.
We are linking with plain areas. So sometimes while we notice a damage during a landslide or a monsoon season, sometimes we don't have resources there. We can't move our machinery there to rectify those defects. So it takes 2 to 3 days, 5 days to make our people move there to reach that far-flung areas. So that is also one reason we need more water storage in hilly areas. So my suggestion here will be...
No, storage about the raw water or treated water?
Both, sir. Both.
See, if we have a storage of the raw treated water and the pipeline is worse, what is the purpose of that storage water?
But that's why we are requesting for both, no, sir. That's why we are
store the pipeline immediately, na?
That doesn't happen in hilly terrain, sir. Vis-a-vis as it can be done in the plain areas.
Sir, it can be at multiple
We had
places.
faced this problem in Mandi.
It can be at multiple of places, depending upon the availability of land. It can be near the source. It can be at the entry of a town, or it can be a small storages. It cannot be one place. It is not possible in hills. It can be a multiple of places, and it is better near the source. Near the source, it is better because it will cater both the needs.
Agreed. Because of that, the DMA concept is introduced. Because of that, DMA concept is introduced. You cannot go damages in all the DML altogether. It may be damaging in one DMA. So the interruption of water supply can be done in one DMA for 2 days, 3 days. Rest of the area is safe, no? So this is the reason that we introduced DMA concept.
But we are saying that there is a more likely damage in the conveyance system.
हमारा 4 दिन के लिए वाटर सप्लाई स्कीम डिस्ट्रॉय या डैमेज होती है, रुक जाती है, तो 4 दिन तक हमारे हाउस होल्ड में पानी रहता है।
मैंने पहले बताया सिस्टम डिजाइन कभी कैलामिटीज के लिए नहीं होता है, ठीक है? आप अगर सिस्टम जो है वाटर यूटिलिटी जो है जो प्रोवाइड कर रहा है वाटर वही एफिशिएंट नहीं है तो हाउस होल्ड में तो रहेगा ही ना स्टोरेज। पहले तो अपने आप को ठीक कीजिए ना कि हमको प्रॉपर वाटर देना है। जब तक हमें फेथ नहीं होगा कि हमको वाटर मिलेगा तो हम तो स्टोरेज करेंगे ही करेंगे, चाहे वो टैंक में करें चाहे बर्तन में करें।
What is the point that we provide collective storage at a single point when we have already in individual household we have storage tank?
There is 2 reasons.
That is the distributed storage.
No. See, DMA concept आपको समझ में आ गया तो ठीक है, नहीं तो फिर से समझा सकते हैं। DMA concept इसलिए दिया है कि सिटी को आप डिफरेंट पार्ट में डिवाइड कर दीजिए।
But in hilly area, it is very difficult to divide a city.
People are doing in the region, na? People are doing in the DMA base.
No, it can be done.
ये important है।
It can be done, but from
hilly area के लिए तो DMA और important है। क्योंकि अगर आपका एक पाइप खराब हो गया तो पूरा सिस्टम खराब हो जाएगा। यहाँ भी ऐसा नहीं होगा।
Sir, it cannot be overruled. Sir, DMA is a good concept.
What do you mean to say that the guiding factors should be different for plain areas and different for hilly areas altogether? Actually, what we are doing here, we are creating manuals only based on mainly based on the plain areas and very little stress given for the hilly areas. So emphasis needs to be given more to the hilly areas because we have adverse conditions which do not prevail in the plain areas. Now, what we are telling is like creating a buffer storage of 2 to 3 days in the hilly areas. That could provide rationing, though at a very less rate, but minimum need waste for 1 week or so, because incessant rains prevail for a period of say 7 to 10 days when we are not in position to restore our system right at the source because of high values of turbidity and other factors like slidings in the area. The system, our conveyor system becomes inaccessible.
So that I agree, okay. Other than the storage, what is your concern? What parameter do you want to change? Other than the storage is discussed already. Other than the storage, what changes you want? Like you don't want DMA concept, you don't want operational concept. What exactly is required to be changed?
DMA concept is not.
Then what others? Other than the storage. storage already discussed. Other than the storage, what parameter you want to say?
Sir,
आपके पास आएगा नहीं. हाँ, बताइए. आपका क्या suggestion क्या बताइए?
Sir, our suggestion, DMA is of course better. We can put PRVs for that matter.
Okay.
For controlling the.
PRV हमने mandatory किया हुआ है, फिर आएगा.
Mandatory किया हुआ है. This metering of course should be necessarily introduced and.
Essentially introduced है. और बताइए, ये already है.
Already has है.
बिल्कुल है. जो नहीं है वो बताइए कि आपको क्या चाहिए, सब एरिया क्या रिक्वायरमेंट होता है, दैट आई वांट टू नो.
हमें बफर स्टोरेज चाहिए सर.
वो तो डिस्कस हो गया ना, वो चेक करेंगे ना, वो देखेंगे कितना चाहिए, वो तो स्टडी करेंगे तो डिसाइड करेंगे कितना करेंगे. स्ट्रेट वैल्यू से कि 10 दिन का चाहिए, 5 दिन चाहिए, तो मुझे भी साइट विजिट करना पड़ेगा, अंडरस्टैंड करना पड़ेगा, उसका तो डिसाइड कर देंगे आप लोगों के साथ मिलकर. उसके अलावा क्या चाहिए जो बताइए.
सेकेंडली सर, मैं ये चाहता हूँ कि हिमाचल में हिली एरिया में प्रेशर डिफरेंस जो है बहुत ज्यादा होता है. ट्रेमेंडस प्रेशर डिफरेंस. और जो आपका प्रेशर रिड्यूस वाल्व है उसको हमें बहुत ज्यादा इंट्रोड्यूस करने पड़ेंगे फॉर इक्वल.
तो who has stopped you to introduce? Who has stopped you?
उससे
Who has stopped you to introduce PRV?
कॉस्ट बहुत ज्यादा बढ़ेगी. मैं कह रहा हूँ कि जो शिमला का
कॉस्ट की तो बात ही नहीं कर रहा हूँ मैं.
नहीं
I am not talking about the cost. I am talking about the system, design of the system.
Cost we cannot ignore. Cost we cannot.
किसने बोला कि इग्नोर कर रहा हूँ? मैंने कॉस्ट की बात की है, बताइए कि ना.
You are saying that we cannot charge everything to the district.
Yes, yeah, you cannot see, you cannot make a barrage in the river in the name of water supply system.
No, that is.
I am talking about that. I am not talking about the cost.
सर जो कॉस्ट अमरूद में दी है वो भी तो पॉपुलेशन और है उसके हिसाब से दी है.
So we adopted two methods. One, if it is possible, it is if there is space, we can put a backup system by solar pump.
ऐसी स्थिति आ जाती है कि वो सिस्टम भी फेल हो जाता है. तो उस सर्कमस्टेंसेस में हाउ कैन वी सप्लाई द वाटर, दैट इज द इशू. एंड वी हैव ओनली ऑप्शन फॉर दैट इज अ बफर कैपेसिटी. We have to go for that. And
that depends upon the region to region.
That is what we want to say.
अभी सर 3 दिन तक तो लोग हमें पूछते नहीं हैं.
आज हम करना शुरू हो गया टास्क. आज हम कल
आप इरिगेशन पार्ट से मत बोलो, आप इरिगेशन पार्ट बोलो, आप क्योंकि ये सही बात कर रहे हैं.
सर लास्ट
आप इरिगेशन पार्ट मत लगाओ.
Sir, last evening we sat together and we were just talking about this gentleman. He is taking care of that scheme itself. जिसकी मेंटेनेंस ये कर रहे हैं, तो हम दोनों बैठ के ये बात कर रहे थे. बादल आने शुरू हो गए, तो कहीं अपने अलर्ट कर शुरू कर दो और कम से कम सिस्टम इस तरह से चलाना शुरू करो, देखना शुरू करो कि जब बंद करना है शट ऑफ इमीडिएटली हो जाए. जब तुम्हारा लगता है कीचड़ आना शुरू हो गया तो बंद कर दो, लेकिन आगे चाहे पानी दो चाहे ना हो, लेकिन वो 30 किलोमीटर की लाइन में कीचड़ मत आने दो. अदरवाइज सर, अदरवाइज वो कीचड़ एक बार एंटर हो जाता है तो हमें 10 दिन लगते हैं सर WTP तक क्लियर होने के लिए. सो दैट इज द इशू फ्लशिंग द टैंक. मतलब प्रैक्टिकल प्रॉब्लम्स हैं, वी कैन नॉट अवॉइड दैट. वो दिक्कतें हैं सर. हिली एरियाज में डिफरेंट है सर.
स्टोरेज आ जाएगा तो लीन में भी आपका कंस्ट्रक्ट हो जाएगा, उसमें कंस्ट्रक्ट हो जाएगा.
इसको करें आप.
Sir, मतलब that is one of the solutions.
It might be some other things also.
ले बताएं और क्या बता रहे थे. ले बताइए और क्या बता रहे थे.
वही सर,
वो सोल्यूशन बता दिया आपने इनको सोल्यूशन नहीं जम रहा है उसी. पर आपका साइड देखना पड़ेगा. चीफ इंजीनियर साहब, आपका साइड देखना पड़ेगा क्या है. अभी आएंगे, अंडरस्टैंड करेंगे तभी.
सर अभी जब ये आती है ना सर, मानसून आती है, प्लीज मोस्ट वेलकम सर.
उसको भी देखिए. संजोली वाला जो हमारे उसका निगम का है,
संजोली का तो प्रॉब्लम डिजाइन का प्रॉब्लम, मेंटेनेंस का प्रॉब्लम.
उसको देखें आप कि क्या उन्होंने गलती करी है, उसको भी आप पॉइंट आउट करें.
क्या गलती किया उन्होंने?
आप हमें पता नहीं है क्योंकि सुपर लॉ नोट
एक्चुअली सर आई एम नॉट ए कॉन्ट्रैक्टर देयर. वो उसमें जो डीएमएस जो बनाए हैं ना जी, जो एग्जिस्टिंग सिस्टम में डीएमएस इंस्टॉल करना है, दैट इज बिकमिंग अ चैलेंज. दैट इज बिकमिंग
एक्चुअली शिमला से
संजोली का हिली टाउन है.
शिमला पार्ट ऑफ शिमला, ये वार्ड ऑफ शिमला.
तो शिमला का तो हमने अप्रूव किया वाटर सप्लाई सिस्टम.
सर वो तो
शिमला का मैंने खुद किया है वाटर सप्लाई सिस्टम का, जो अभी समथिंग 400 करोड़ का था प्रोजेक्ट. वो
बल्क है.
नहीं बल्क का नहीं था, इंटायर डिस्ट्रीब्यूशन सिस्टम है कंप्लीट टू हाउस होल्ड लेवल. बल्क का तो आया नहीं था.
टेंडर इज स्टिल अंडर प्रोसेस.
बल्क का कुफरी से आना था उधर से, वो बल्क वाला आया नहीं.
टेंडर नहीं हुआ सर, वो वर्ल्ड बैंक से हुआ सर.
ये तो शिमला का स्टार्ट हो गया ना, कुछ टेंडर हो गया ना उसका.
हुआ था छोटा सा संजोली वाला.
और डिस्ट्रीब्यूशन सिस्टम का तो हो रहा है ना, वो
ऑलरेडी पार्ट वहाँ पे चला हुआ है जिसका टेंडर हो चुका है, जिस पे काम चल रहा है.
बाकी सर 24/7 ऐसा नहीं है, हमारे मोस्टली जो रूरल वाटर सप्लाई स्कीम है दोज आर बेस्ड ऑन द सरफेस वाटर,
ग्राउंड वाटर
एंड नॉट एक्चुअली ग्राउंड वाटर, स्प्रिंग सोर्सेज के ऊपर बेस्ड है और वहाँ लिटरली 24/7 चलती है।
ये प्रॉब्लम जो टर्बिडिटी का आता है बेसिकली रिवर में आता होगा।
ये सर प्रॉब्लम वहीं आते हैं जहाँ हम
नाला से टैप कर रहे हैं,
सरफेस वाटर पे ये प्रॉब्लम है।
जहाँ से स्प्रिंग से कर रहे हैं वहाँ पे प्रॉब्लम नहीं है,
वहाँ नहीं है।
और रिवर से टैप किया तो
रिवर से टैप करें तब भी आ रहा है,
तब भी आ रहा है,
तब भी आ रहा है।
हमारे जनरली हमारे हिमाचल में जैसे मेरे पास कुल्लू वाटर सप्लाई स्कीम है, तो हम एक सोर्स पे डिपेंडेंट नहीं है वहाँ पे पानी मेंटेन करने के लिए 24/7। हमारे 3-4 सोर्सेज हैं जहाँ से हम पानी लेते हैं, तो एक में अगर टर्बिडिटी आ जाती है, एक में स्लाइड हो जाता है, तो दूसरे पे थोड़ा
नहीं, वो हम लोग भी प्रपोज करते हैं कि आप
इस तरह से
सोर्स पे जाओ,
इस तरह से पानी चलता है।
मिनिमम 2 सोर्स यू शुड गेट
और
आउट।
इंडिविजुअल हाउस होल्ड की जो स्टोरेज है उसको एलिमिनेट करने के लिए हमें बहुत टाइम लगेगा। जैसे पूरी का केस
बहुत टाइम लगेगा, आई एग्री, बहुत टाइम। आप 2-4-6 महीने में
फ्रॉम पॉइंट ए टू पॉइंट,
आपको 4-5 साल लगेगा तब जाकर पूरा कंप्लीट होगा।
इसको डिजाइन में हमें बहुत ज्यादा चेंजेस इसमें लाने मिलेगी। हिली एरियाज में आप सीपीएचईओ का जो मैनुअल है हिली एरियाज के लिए कोई
क्या डिजाइन में चेंज आना चाहिए?
नहीं डिजाइन में वो
पूछने जा रहा हूं, वो जानना चाह रहा हूं।
प्लेन एरियाज के लिए आप सारे नॉर्म्स हैं आपके उसके लिए। हिली एरियाज
तो आप बताइए ना।
सो वी आर डूइंग इट, हम अपने
आई एम स्टैंडिंग हियर ओनली फॉर यू टू अंडरस्टैंड फ्रॉम यू क्या डिजाइन में चेंज होना चाहिए।
तो
आप बताइए ना क्या चेंज होना चाहिए, तो कौन बताएगा चेंज होना चाहिए?
वैसे वैसे सीखेंगे और हम करेंगे उसको 24। हमें जैसे गैस मिल रही है, आज सिलेंडर एलिमिनेट हो गया गैस का, उसी तरह पानी करना चाहिए, तो रिक्वायर्ड है 24/7।
अभी कुछ है ऐसा
अभी
आइडिया?
जो इंडिविजुअल हाउस होल्ड है वो ले ही रहे हैं, 24/7 ले रहे हैं। वो अपना टैंकी है, अपना टैंकी से 3 घंटे दो 2 घंटे तो उनकी टैंकी स्टोरेज रहती है। वो 24/7 ऑलरेडी चल रहा है। वो जब भी खोलते हैं नलका तो घर में पानी होता है।
उस टैंकी में भी कंटामिनेशन हो रहा है, स्टडी हमने करवाया है।
नहीं, हमारा पानी जनरली बहुत अच्छी क्वालिटी का पानी है। ऐसा
पानी नहीं, टैंकी की सफाई नहीं होती, पानी तो अच्छा मिलता है।
वो इंडिविजुअल उस पे डिपेंडेंट है।
वही तो है।
जागरूक लोग हैं तो कर रहे हैं, हमारा रेगुलर टैंकी को सफाई करते हैं।
हमने स्टडी करवाया है, वहाँ पता चला है कि 30% जो कंटामिनेशन हो रहा है, वाटर खराब हो रहा है बिकॉज ऑफ वो टैंकी।
डीएमए का
पानी अच्छा दे रहे हैं लेकिन वो हाउस होल्ड लेवल पे जाके पानी खराब हो रहा है।
नहीं, ऐसा जनरली नहीं।
हमने स्टडी करवाया है ना, हमने स्टडी करवाया है उसको। तो आपका पानी तो अच्छा है, तो पानी वहाँ जाके खराब हो गया। किसी ने अंडरग्राउंड टैंक रखा है, सालों साल साफ नहीं किया। ऊपर का टैंक है, साल भर में साफ नहीं होता, एक बार कभी मना कर साफ कर दिया, ब्लीचिंग पाउडर डाल दिया, कुछ कर दिया।
डीएमए का कंसेप्ट इम्प्लीमेंट करने के लिए थोड़ा हमारे लिए हार्ड पड़ रहा है इनिशियली, बट दो इट इज अ वेरी गुड कंसेप्ट, इट विल टेक टाइम।
हार्ड क्यों हो रहा है, क्यों हार्ड पड़ रहा है?
वो ये प्रेशर मेंटेन बहुत हाई डिफरेंस है प्रेशर।
तो पीआरबी लगाएगा ना।
ये ट्री सिस्टम जो हमारा ऑलरेडी वहाँ पे चला हुआ है वो बेस्ट चल रहा है प्रेजेंटली।
आप लेके ही मेरे पास बताते हैं
सर। एक्चुअली मैं कुछ ऐड करना चाहूँगा जो आप बात कर रहे हैं सर। डीएमए हमारे एक्चुअल डीएमए इटसेल्फ इज, हमने अभी सिस्टम चल रहा है सर और 24 घंटे चलता है। होता क्या है, जहाँ वॉल्व्स लगे हैं हमारा फिल्टर की मैन जाता है, वो अल्टीमेटली कर क्या रहा है, वो उसको ऑपरेट करके पानी 24 घंटे चलता है सर। बट आपके कंसेप्ट के अंदर वो हट जाएंगे वहाँ से और वहाँ प्रेशर रिलीज वॉल्व जहाँ जहाँ लगाने हैं वहाँ लग जाएंगे। व्हील तो अभी भी लगे हुए हैं सर, वो चरखियाँ तो अभी भी घूमती हैं, लेकिन वो बंदे ऑर्गेनाइज, हाँ बस इतना सा फर्क है। बाकी चलता है सर, वो हैं लेवल्स हैं, नोड्स हैं वहाँ पे बने हुए, वो जहाँ पे उसको पता है कहाँ कब खोलता है, वो प्रेशर कैसे रिलीज होता है, ही नोज दैट थिंग। अब वो मैनुअल छोड़ के वो अदरवाइज आना है, दिस इज द ओनली चेंज इन दैट। अदरवाइज
सिस्टमाइज कर देगा सिस्टम को, आपके पास
हाँ,
है,
अदरवाइज
है, वही चल रहा है,
सिस्टम है,
हाँ।
हम चला रहे हैं उस सिस्टम को। एक और चीज़ ऐड की सर हमने इसमें, जब लास्ट टाइम ऐसी चीज़ें होनी शुरू हुई, आपके एक तो वी वांट टू आस्क यू फॉर बफर स्टोरेज एंड विद दैट हमने डीएमएस के अंदर ही वी जस्ट ट्राई टू लोकेट द टू सर्च फॉर द टू गेट द वाटर अंडरग्राउंड वाटर्स। हमने डिफरेंट बोर्ड्स करने भी शुरू कर दिए जहाँ जहाँ हमें मिले, सो दैट जो आपके ESRs हैं उनको कनेक्ट कर सके हम फॉर डीएमए पर्पसेस, फॉर दैट फॉर दोज पीरियड्स जब हम उस कन्वेंस को
इट इज द फर्स्ट पीरियड।
बट वो भी हमें सक्सेस सब जगह
आइडिया अच्छा है,
सब जगह वी हैड ट्राइड दैट, बट सब जगह नहीं मिल पा रहा, वो
सब जगह नहीं मिल पाया।
तो जहाँ जहाँ हो पाया हमने वो भी किया है। बट ऐसा नहीं है सर, वी वांट टू डू इट डेडिकेटेडली, बट प्रॉब्लम वही आ जाती है कि वो 8-10 दिन का ऐसा सिनेरियो बन जाता है कि हम 1 महीना पीछे चले जाते हैं सर उसमें। इट हैपेंस सर, इन हियर्स इट हैपेंस।
ठीक है, और कोई सजेशंस? डिजाइन सजेशन तो नहीं दे रहे आप लोग कोई भी नहीं, बस चेंज होना चाहिए, क्या चेंज होना चाहिए पता नहीं।
डिजाइन में सर एक वो है सर कि अब पता नहीं
फैक्टर बदला है
एयरबीज से हिली एरियाज में बैक प्रेशर चेंबर ज्यादा कारगर वो हो रहे हैं सर। जो मेरा ऑब्जर्वेशन है, जो बैक प्रेशर चेंबर्स हमने मैन्युअली बनाए हैं वो ज़्यादा कारगर, मतलब अगर आपका डिज़ाइन परफेक्ट आप उसको करते हो तो पीआरवी से ज़्यादा बेटर अपना मैनुअल बैक प्रेशर चेंबर्स इस ज़्यादा सक्सेसफुल ज़्यादा रहता है सर, क्योंकि उसमें फ्रीजिंग का भी हमें फिर दिक्कत आ जाता है तो अगर आपका हाइड्रोलिक मॉडलिंग अच्छे से हुआ है तो और उसका क्लीनिंग एंड एवरीथिंग कुछ भी हो तो उस वेरी इजी टू डू इट। सो मेरे ख्याल से वी शुड गो फॉर बैक प्रेशर चैम्बर्स रादर देन इन पीआरवीज। अगर आप
सर यही है, हम तो हिमाचल में अभी तो बैक प्रेशर टैंक्स ही ज़्यादा बना रहे हैं।
वी हैव कंस्ट्रक्टेड विद द सिंटेक्स।
तो कॉस्ट में क्या वेरिएशन आता है दोनों में? पीआरवी एंड बैक प्रेशर।
पीआरवी में तो सर actually PRV is a new concept in India, so not many manufacturers are coming up with very concrete solutions. Sometimes it takes so much of time to design the system and suggest the system कि उतने में project ही complete हो जाता है। Darling Mills को है, other people, I mean, it needs a lot of hydraulic studies.
And one thing we have observed, sir, not from I'm talking from the core climate. What is our observation? Previously we think we are using 70 LPCD. Once we have done one DNA zone in Leh, we have observed that in winters the people are using less than 30 LPCD. Previously we are assumptions that this much of water is using, but actually when you have put in the meters, we have got the data, it is water consumption is काफी reduce हो जाता है। But there are two concepts. One is the hilly region, हिमाचल के जो hilly regions है उनका flooding and all this. But जो freezing वाले areas है वहाँ अलग एक issues है वो आ जाता है सर। तो उधर भी मतलब ये इनके साथ हूँ कि at least we need a backup for at least for one day, ताकि कुछ भी कोई issues आए तो टैंक हमारा रिजर्वायर इतना कैपेसिटी का हो ताकि we can do some alternatives we can think about. कोई या freezing हो जाए।
We have two criteria, one for the flooding areas and second for the freezing areas.
Yes sir.
So two different criteria should be adopted.
Thank you.
So I think we will conclude so that there is enough time for the.
I'm sorry, I have just taken more time. I'm sorry.
It was an interesting deliberation, but I would suggest the participants could put up a short note about the things that you take away from this and what are your, so like advisor said that maybe a short advisory could be issued specifically focused on the hilly states both from supply perspective and distribution perspectives.
Thank you.
Thank you.
Thank you. Craig Willard, I'm currently the professor and the department head at the Department of Civil Engineering at Montana State University in Bozeman, Montana. And just a little bit about my background so that you kind of know where I'm coming from. I wasn't always a professor, but I have spent really my entire career in the water sector. I actually started my career in Alaska. I taught for a while at the University of Alaska Anchorage. And then I spent about a big chunk of my career up there working in operations and as the general manager of the Anchorage Water and Wastewater Utility, as well as doing a bunch of consulting for Arctic utilities in and around Alaska, all the way up to the very north slope of Alaska. And so I have some experience there with cold regions. My wife and I are actually originally from Montana, and so we had a chance to move back to Montana about 12 years ago. I worked there in the city of Bozeman as the public works director, where I was responsible for the water and wastewater and stormwater utilities, as well as the rest of the public infrastructure there as well. And then most of you know Nilash. Nilash and I are long-term friends because we met on the board of the American Waterworks Association, and I think the first time I was actually in India was about 2010, which I think was the first kind of conference, right? I'm not sure East to see it. So it's great to be back. I've been back a few times. I always enjoy coming to India. It's a very interesting place. You have
beautiful country and wonderful people, interesting challenges. I do not pretend to understand the issues that you have in India. I hope that some of the perspective that I have and what we do in some cold regions in the United States may spark an idea, may give us some discussion. We might be able to compare and contrast, but hopefully you get some ideas on how you might manage your systems. Not that we've got it all figured out, but we do have, especially in Alaska, quite a bit of experience with cold climate utilities. So hopefully my background gives you some perspective that will be useful. Like I said, I don't pretend to understand exactly what your problems are here, although I got a pretty good handle on some of them from the discussion, and we have the same problems in the US. So there's a couple pictures there. The picture to the left is an Arctic installation on the north slope of Alaska, and so I'll show you some pretty interesting pictures there. This is true Arctic conditions, right? Where, above the Arctic Circle, it is dark 3 months a year. The sun doesn't come up, right? Routine temperatures there. Routinely -40, -50 low, -20 high, right? Now in Anchorage and Bozeman, actually much more temperate, and I'll show you some data from there. And probably more in line with what we're expecting here. But I do think we can learn some interesting things that you might be able to apply from the lessons that we learned in the Arctic. The middle picture is actually a dig in a pipeline break in Anchorage, Alaska. And so, just to give you an idea there, our minimum depth of bury in Anchorage is 10 feet. So 3 meters. And when you have a break at a 3-meter bury depth, it's an expensive and difficult proposition. And so we use a lot of interesting equipment. And then finally, there's a picture of Alaska, Anchorage, Alaska. And this is a town of about 250,000 people. In Anchorage, we served about 250,000 people. We had 90 pressure zones. We had several hundred pressure regulating valves. And so, very hilly area, right? So maybe some lessons there. Bozeman, not quite as extreme, but we do have some hills, not quite as many pressure zones, but a lot of relief, in the west. And so have some experience kind of dealing with those kinds of situations. Although I will say that my first trip to the Himalayas, the topography here is very extreme. Okay. So some acknowledgments, right? One reference that I wanted to make you aware of is this. This is the Cold Regions Utility Monograph. This is the Bible for Arctic utilities. This is what we use in the circumpolar regions to design utilities. It is published by the American Society of Civil Engineers. It is the definitive reference, if you will. It's kind of that, this must be in your library if you're a cold regions engineer. You can download it online from the American Society of Civil Engineers. I think for a non-member it's $150, something like that. It's a fabulous reference. Many of the figures that I will show you today I've taken from the Cold Regions Utilities Manual. I have tried to pull pieces out of there that I hope would be relevant for this talk. It barely scratches the surface of the information that's there. There's a lot of great information on design of water and wastewater systems, but also centralized facilities, planning some of these unique installations in the Arctic. And many of the installations and utilities in the Arctic will be a couple hundred people, right? Isolated geographically, right? No roads in, no roads out, no real economy. It's a subsistence economy where people largely get by hunting and fishing, a very small cash economy, very, very challenging economic and social as well as technical conditions. And so as Alaska and the circumpolar north developed, this group of cold regions engineers put together this utilities monograph, and it's a great reference. The other thing I want to do is give credit to my wife. Lisa Woolard is also a civil engineer. She's a partner in a small consulting firm in Anchorage called G.V. Jones and Associates, and they do a lot of work in the Arctic, on Arctic utilities. They really specialize in water and wastewater treatment, but taking some information from some of their work. And then I want to acknowledge Dan Schubert, who passed away a few years ago, but really a fabulous coal regions engineer, and we were friends for a long time and did some work together, and so some of the material in here is things that he put together while he was still alive. So here's what I want to try to do today, right? I want to talk a little bit about the impacts of cold temperatures on water systems. And when I say water systems, I really am going to mean throughout this water and wastewater systems, okay? Because the fundamental physical processes are very much the same. So I want to talk about that a little bit. I want to talk about some heat transfer fundamentals for water systems in hopes of getting you enough background here in a short period of time to give some simple calculations for estimating freeze depths, for calculating freeze-up times, for estimating heating needs in water systems. And this, it could be a very, very complicated topic. I've tried to pull out some of the more, I think, straightforward, if you will, relationships from the Coal Regions Utility Manual and other sources that give you some really fairly simple calculations that you can do for your system that I think provide some insight. I hope anyway, provides some insights on how you might be able to better manage, design, and operate your systems. And then finally, we'll talk about some techniques and some mitigation options for dealing with cold temperatures in water systems. And so I'll give you some examples and some ideas throughout that part of the presentation. And then based on last night's conversation at the opening ceremony, I've added a few things that at the end, where we'll talk a little bit about water treatment, a little bit about wastewater treatment. We can talk a little bit about water storage if you like, and what we do for water, some of the things we run for water supply. So, I really like cold regions. I've spent my entire life living in places that are routinely cold. And I think it's great. I think the environments in cold regions are fabulous. I think it's fair to say things are always tougher in cold regions. If it's cold, it's harder, and it's more expensive, and things are more prone to fail. And I will argue that, right, your engineering skills have to be a little bit crisper. Right? I compare notes to make things work reliably in those situations. I have interesting discussions with my friends from Texas, and I was working at the Anchorage Water Utility and comparing notes with utility professionals from Texas, and they would say, well, how deep do you bury your lines in Texas? And they say 2 feet. All right? I was like, well, ours is 10 feet. Burying things at 2 feet we call cheating, right? So a lot easier. But hopefully we'll give you some ideas of things to use. So with that, we'll just kind of jump in. I don't want to just sit here and talk, so if you have questions, please interrupt me, raise your hand. We can go off on a tangent. I have some slides, but I don't have an agenda. We'll kind of take this where you want to go. All right? And I'll try to remember to stop here every now and then. So let's talk a little bit about cold temperature impacts on water and wastewater systems. So, no surprise, right? We have this seasonality of temperatures, right? The Earth rotates around the sun. We have cold parts of the year. We have warm parts of the year. We have sunny parts of the year. We have dark parts of the year, right? That seasonality of cold temperatures is really important, and it requires that we think a little bit about, what happens. And so, this is a little bit hard to see, but I Googled what's the coldest place in India. And Leh, I think it's L-E-A, Leh, is that how I pronounce it? No, this will work. Yeah, this one I get to my notes here, hang on. So, Leh, India, right? So this is a little bit hard to see, but here, whoops, come back here, come back here. There we go. So here's Lay, India. Did I pronounce that right? Okay. All right. So, this is just right off of Wikipedia. There's no Indian climate system data here, just what I could readily find on the internet. But it gives you some idea, obviously, of the different seasonalities of these temperatures. And over here is, this is Anchorage, Alaska. This is Bozeman, Montana. And this is Ulaanbaatar, Mongolia. Right? And so you can see the blue here is where we have below freezing. This is the Lay's example here. This is the daily mean temperature in degrees Celsius. And so, right, the daily mean temperature of Lay has got 3 or 4 months where it's below zero. And if you look at minimum daily temperatures, right, they're below zero for many parts of part of the year. You can kind of see similar types of data in Anchorage and Bozeman. And then if we're really ambitious, we can look at Ulaanbaatar, Mongolia, and they've got low temperatures in the -40, -50 degrees Celsius for a big chunk of the year. So all these communities are dealing with these below average or below freezing temperatures. And I think the challenge from an engineering standpoint becomes, well, how do we account for that, right? Physically, right, we know part of the year is freezing and part of the year is thawing, if you will. How do we account for that? How do we use that, account for that seasonality of temperature data to come up with ways that we can use that information to figure out important engineering parameters like frost depth and how long it's going to take to freeze. And the way we do that cleaned up that data a little bit. We start to plot the temperatures over the course of the year. So the gray line on top is the average daily temperature, the middle line is the average daily minimum, and the bottom blue line is the record low for every month from the climate data that I had access to. Right? So we can use that, and we can start to now account for these sinusoidal temperature variations that are caused because the Earth rotates around the sun, right? And we need to take into account the time periods that are above and below freezing to calculate what we call the air freezing index, the air thawing index, or the air heating index are 3 really common parameters in cold regions that we use in engineering. And of most importance, probably for here in India, is the air freezing index, right? And so if we look at this diagram, we look at this diagram, right? So this crosshatch area that my cursor is on, right? That's the air freezing index, all right? That's the times of the year on the early part of the year and the late part of the year where the average daily temperatures are less than freezing, right? And this area here, right, TF is the freezing point, so 0 degrees Celsius. This area here, right, with the cross hatching going this way, is the thaw season, right? And then in Arctic or cold regions building design, we're concerned about the air heating index. Typically at around 18 degrees Celsius, right, we have to start heating buildings. And so we wonder how many days do we have to heat the building. And so we use the air heating index. I won't spend much time on that other than to kind of introduce the concept. So what we can do then is start to calculate these freezing indexes. Right? So the air freezing index is just the annual sum of the freezing degree days, right? Where a freezing degree day is the freezing temperature, right? 0 minus the mean daily temperature, right? When it's below freezing. So if I have a day where the mean daily temperature is minus 10 degrees C, I have minus 10 degree C degree day. And if I sum them up over the course of the year, then I can get a how much time my system is under freezing conditions, right? So it is a crude measure and but an easy measure to start to kind of account for all of the time during the year that things might freeze, and alternately all of the time during the year that things might thaw. Now, in India, I don't think the thawing part's a big deal, but in Alaska it's a big deal, right? We talked about that a little bit. When we have permafrost conditions, we're very concerned about, well, how much of that permafrost thaws during the year, right? So we're concerned about that thawing index. I won't spend much time on it here, other than to introduce the concept, but the freezing index is very relevant to what you're experiencing here, right? And so how do you calculate this? Well, I went to Wikipedia and got some data and just kind of did a crude number. Ideally, what you would do is go back and look at climate records for your town. The more detailed, the better. Certainly daily would be great, right? The general recommendation is you calculate that freezing index in the 3 coldest winters on record over the last 30 years. If you have 30 years of climate data. You may not, right? Or, right, what's the coldest winter in the last 10 years? We're trying kind of, with some measure, to start thinking about, well, how much freezing potential do I have in my system? And this is the typical way we do it. Okay, make sense? So here's an example, right? January average temperature for Leh, India is minus 5.8 degrees C, right? So January is 31 days long. The freezing index for January is 31 days times 0 minus 5.8 degrees Celsius, or roughly 180 degrees C days, right? So if I could go through every month of the year, and if I had daily temperatures for every month of the year, right, I'm using the average temperature for the entire month of data from the Wikipedia, right, information. So I'm making a pretty crude estimate. It's obviously not 5.8 degrees Celsius every day of January. It's going to vary around. If you have that data, you can get more accurate with your freezing index. But you can calculate that for each month of the year, right? And sum them up and you get an air freezing index. So I did that for Leh, and to try to just get a feel for the freezing index that we might experience in a cold community in India. And if I took the average, there's the data that I pulled off of Wikipedia, right? And over here, I just took the average daily temperature, okay? And summed them up. Anything in blue, those are months where there's an average daily temperature below freezing. Everything in orange, right, or yellow or red, whatever this orange color is those are freezing days, those are thawing days, right? So for average daily temperature, I have 3 months, right, where I may have freezing conditions based on just that really crude average data, and that's around 361 degree Celsius days, right? If I look at the daily minimum, right, and assume every day of the month was the minimum daily temperature, obviously again not a great assumption, but gives me a range. It's somewhere around 1,300, and then if I assume that every month of the year, in 1 year had a record low, every month of the year on the top end we're looking at 4,700, right? Freezing index of 4,700 degree days, right? So these are obviously not, these are limited, right, by the scope of the depth of the data that I have, but it does give us a feel for the kinds of freezing indexes that you might experience here. And so obviously the more data you've got, the more accurate your assessment can be, right? It's really useful to track it annually, right? Because it will help you predict frost depths. You're going to have some years where it's cold, right? And you don't have snow. And the frost depth is going to be deeper than years where it's warm. And you may have some snow cover, right? And so having a feel for what those potential frost depths are is a good kind of parameter to kind of get a feel for in your system, okay? So I'm going to use in our examples a range, right? I'm going to say that Leh, India, as a typical Indian cold region community, has a freezing index of 400 to 800, right, degrees. 400 being 400 to 800 degrees Celsius days. 400 being kind of the quote-unquote average year. 800 being kind of a cold year, right? Okay. give you a feel for how that stacks up, on the right here is the freezing index for Anchorage, Alaska. There we go. So we track this, right? The Weather Service actually tracks this on a daily basis. And so you can see, we start here in October, you can see the degree freezing days, right? Increase over the course of the year. Right? And so we're getting up here in the neighborhood of 14, 15, 1600 degree freezing days. Right? That's what we experience in Alaska. In Ulaanbaatar in Mongolia, right, their freezing degree days is 2700, almost 3000 days. Right? Very cold, very high, very cold. Right? This was a project that my wife's company did for the World Bank to look at ways to improve water and sanitation in some of the Gur regions in Ulaanbaatar, right? Some of the areas where they don't really have centralized utilities. So good number to kind of keep in mind, a really important concept, right? So we'll come back to that, we'll use that in some calculations, but that is a key parameter that we use in cold regions engineering for a whole bunch of things. Okay? So let's switch here real quick and stop talking about air temperatures, and let's talk about how soil freezes, okay? So when soil freezes, right, you probably have a pretty good conceptual understanding of this that's intuitive, I suspect intuitively right? Air temperature gets cold, that freezing front starts to migrate down in the soil column, okay? And it migrates down in the soil column as a proportion of how many freezing days you have, right? And so it's a very complicated process. You can think about that. You don't know what the soil type is, what's the water content, is it heterogeneous, homogeneous, all sorts of variables, how much water is in there, how deep's the water table, all sorts of these things kind of come into practice where in the process of estimating how soil freezes. And we could get lost in the weeds, right, down in the details of trying to figure out the soil physics of this, but from an engineering standpoint, we probably don't have the time or the resources to figure it out. So what we kind of need to do is have some sort of common understanding, and so that freezing front migrates over the course of a year down through the soil column until we get to a frozen fringe, right? We get to the frozen, unfrozen soil interface. In that process, water will generally migrate towards the water that's freezing within that soil column. It will pull water in, depending upon the soil parameters, whether it's how porous it is, what kind of water content it is, what kind of hydraulic conductivity the soil has. And you can also get ice lenses that form. When you get ice lenses that form, right, you get frost heaving, right? This is what causes potholes in roads, in a water system, right? It can impose some significant pressures and forces on the buried system, right? As that frozen front starts to approach your pipe, right, you start to get changes and movements in the soil systems and the soil column as water moves and starts to freeze. And so we need to be really aware of where that frozen fringe is and all sorts of things that can happen here. Now every situation is going to be different, but that's the general process of soil freezing. And so knowing where this is important. Ideally we want our pipes to be down here somewhere, right? Sometimes they end up in here, and we'll talk about what the consequences of those are. I won't spend a lot of time talking about the forces, but there are some significant forces. When the freezing front starts to hit your pipe, that's when you think things start to break. Okay? Give you some examples. So here's an important curve in kind of cold regions engineering, and I want to pick this apart a little bit. So I'm going to start over here, excuse me, on the left. And on the left is what we call a trumpet curve, okay? And the trumpet curve has some parts to it. The part that, so the trumpet curve has, right, a couple things that are important. So here's the 0 degree temperature line, okay? This line on the left is the minimum, this is the minimum mean temperature. So we're going to bracket the minimum soil temperature with depth. And on the right here is the maximum soil temperature depth. And those two things come together at some point down in the column, right? Where the mean and the maximum mean temperatures in that soil column meet here at a place where there's no change in the temperature with depth. Okay? There's a geothermal gradient that exists in the soil, right? The earth very simply, the center of the earth is hot and the surface is cold, and so there's actually a geothermal gradient. That's why we can take advantage of geothermal energy and heat pumps and all those things. The deeper you go, the more stable the more stable the temperature is. And so this trumpet curve gives us a way, right, to kind of look at that soil column and figure out what's going on. So the middle line is the mean ground temperature. It's going to vary from a minimum to a maximum, and it's going to have a mean, and that's going to be different with depth over the course of the year. Okay? In a permafrost system, this 0 degrees Celsius, right, line, right, that is where, right, the temperatures in this example, say it this way, here's the 0 degrees line, the temperatures in this example, this soil, are all below zero. So this is indicative of a permafrost system. Permafrost is defined as soil that doesn't ever get above 0 degrees Celsius. Okay? And so in this case, right, what's going to happen when we look at where the maximum average temperature intersects zero, that's going to be the active layer. So in the Arctic, in a permafrost situation, that's the amount of soil that that thaws every year. Okay? And then we get all the way down here, this is going to be the depth of permafrost, where the thermal gradient intersects zero, right? That's the depth of permafrost. Everything under that is thawed, right? It's closer to the center of the Earth. So permafrost doesn't exist. And so this permafrost in the Arctic can be, quite deep, tens of meters, depending upon the situation. Now let's go to something that's a little bit different, same graph, same concepts. I've moved the 0 degrees Celsius line though, right? So now we're talking about a seasonally frozen soil, like we would expect here in India, like we would expect in most of Anchorage, like we would expect in Bozeman. We still have that same trumpet curve, right? Here's the minimum, here's the maximum. I've moved this 0 degrees Celsius line over here to the blue. You can ignore this one. Right now, where the minimum temperature intersects zero, that's the frost depth. Okay? So very similar concepts. So the trumpet curve is a good way to kind of visualize what's going on, and that gives you an idea of how we kind of look at and kind of graphically represent that frost depth. So the frost depth is going to be a function of that freezing index. It's going to be obviously a function of depth. I mean, the soil temperature, is going to be a function of that freezing index, how cold it is on the surface, and it's going to be a function of depth. And one really important thing I think to keep in mind with soils is that there's a lag. In that trumpet curve there's a lag in the soil temperatures that you're going to see. And so this is an example of some data from Alaska that you can, I can't see that. There we go. You can see here's the soil temperatures at 0.5 meters below the surface. The red is 1 meter, the greens are 1.5, 2. We get down here to the black line, that's 4 meters below the surface. And so we may see a minimum soil temperature at the surface or just below the surface in, say, in this case, late January, February. But at 4 meters, right, the minimum temperature is going to be, it's not going to be as cold, right, because we're going down closer to the center of the Earth, but the minimum temperature, it's going to be The temperature as we go down warms, right? You can think about this as the air temperature is below zero, and we know at the freezing front, the temperature is zero, right? So you've got this gradient within that frost zone. But at 4 meters below the surface, right, the minimum temperature might be, right, right here, seen several months later. And so this is a pretty common situation. I expect you can see it here where it's really cold in January and February, but we have all of our problems in April and March. Right? When we, like in Anchorage, we would have most of our line breaks due to frozen lines occur in not January or February, but March and April, where you think it's safe. Well, it's getting warm, things are melting, right? But the frost front is still down there, and those minimum temperatures are just getting down to your pipe. That's a picture of the Trans-Alaska pipeline. I threw it just for some extra things to talk about. A lot of the really great research in cold regions engineering, cold regions utilities and pipelines was done in the 70s, 80s, a lot of it as a result of the construction of the Trans-Alaska pipeline. It was an 800-mile pipeline from the North Slope of Alaska down to Tidewater through all sorts of mountain ranges and permafrost situations and river crossings, and they spent obviously a lot of money developing technologies for building cold pipelines in cold regions. A lot of that research information has been kind of ported over into the domestic water and wastewater utility space. All right. So we kind of have an idea about ground freezing. We kind of have an idea about freezing index. We got an idea about how ground freezes, how we kind of account for that, what it means for the frost depth, what kinds of time lags we can see. So now let's talk about one more kind of fundamental process, and that's how water freezes in pipes. So it doesn't freeze all of a sudden, right? It's a process. And this is an interesting, this is what, here's a copper pipe that's frozen and burst. Obviously, this is not a good situation. But let's talk about how water freezes in pipes. So here's a pipe cross-section, right? And we start at some initial temperature. In this example, it's 6 degrees Celsius. And then temperature starts to slow down, all right? Starts to cool down. We start to lose heat from the water in that pipe to the surrounding air or the surrounding soil that's below zero, right? That's a lower temperature. Heat flows from high temperature to low temperature. So as the pipe starts to cool, right, we start to see the formation when it gets right around zero of this dendritic ice, right? So these are like little feathers of ice, if you will, that form on the inside of the pipe. It's the initial stages of freezing. It also happens in rivers and other water bodies. But that dendritic ice is kind of the initial freezing. It doesn't mean, right, that the pipe is frozen yet, but we have started to form ice crystals. We've started to form sites for the ice to nucleate. And so once we approach that nucleation temperature, which is typically well below zero, well below being -2, -3 degrees Celsius, that's when we get nucleation, and the dendritic ice starts to form annular ice. So now it's forming solid ice on the inside of the pipe, okay? And that solid ice on the inside of the pipe is going to grow and start to occlude the pipe until, right, we freeze the whole thing off. Now, you never want to get here, right? Because when you get here, you got a problem, right? Recovering from this is a real pain. We'll talk about some ideas. But our whole goal is to kind of avoid this and try to stay in this pre-zone, right? This zone before we start to have problems. And I'll show you some simple calculations that you can do to kind of estimate, well, when do we start to get this dendritic ice growing? And then we've got a little, how long does it take for the pipe to get to zero? And then we've got a little bit of a safety factor here until the water in the pipe gets to -3 degrees Celsius. Then we start to have real problems. We can make some calculations there. Pipes don't, so it's important to know they don't kind of just all of a sudden start to freeze solid. They've got this process going on, and they've also got, right, the fact that what the irregularities in the surface of the inside of the pipe. It's not just a nice uniform thin piece of ice, right? Lots of times it will form these different ice layers, all sorts of different processes. And in fact, you know, what really causes this kind of rupture to occur is copper is actually pretty elastic. That's one of the reasons it's used as a service line in interior plumbing. But it will rupture if you can freeze it. You can freeze it and not have it break. But if you freeze a chunk of it, right? If you have an ice lens or wedge that shuts off flow here and shuts off flow here, and this starts to freeze, now you've got this pocket of water kind of pinched between ice inside of an ever-shrinking ice lens, and that will create enough pressure to rupture the pipe, right? The problem is you just don't get nice, even kinds of things, and so this happens more often than not. Make sense? We have some idea now of how water freezes in pipes and what we need to do to try to avoid it. Okay, questions there? All right, so now we're going to get a little more theoretical, but hopefully not too much. So let's talk a little bit about how cool, this is what I want to do here, talk about some heat transfer fundamentals. I'll try not to get too into the weeds here, but I do think it's really important that we have some kind of basic understanding of heat transfer, because when we start to talk about how cold temperatures impact water systems, right? We know there's frozen ground. We've got this seasonal frost depth we talked about. And if we're burying pipes in that seasonal frost depth, we have a problem, right? The frozen ground also has all sorts of implications, especially in kind of Arctic conditions for, you know, structures. How we construct them, how we put foundations in them. I'm really not going to go into that here. That's probably a whole nother workshop. If we have time, we can chat at least a little bit conceptually about some of those things. We have frozen water lines and services, right? Typically, it's the services that are the first to freeze. And unfortunately, those are the things that impact the customer directly. Okay? And so we want to have some idea about those. This is a pretty complicated physical process, right? There's a variety of materials involved, different pipe types, different soil types, right? Different moisture contents, different heterogeneity, all sorts of those things. See a lot of different physical situations, right? It's not quite as simple as, well, if I know the air temperature, I know the soil temperatures, there's a lot of physical situations. You know this from kind of wandering around in cold temperatures. Sometimes, right, if we have surface cover or wind, those things are going to make a big difference in how effectively cold it really is. It's a multi-dimensional thermodynamic problem, and if you're building the Trans-Alaska Pipeline and you're in the process of spending several $1 billion, you're probably going to model the heck out of this with a finite element, finite difference model, right? If you're running a small utility, you need to have some a little more straightforward, okay? And that's what we're going to try to do here, is give you some basic calculations. The other thing that I found is who's measured the soil temperatures in your utility? Yeah, no one. No one does, right? It's not a bad thing to do. You can buy a thermocouples and thermistor strings very inexpensively, put them in the soil and take some resistance measurements. It's a pretty easy thing to do, but no one does it, right? Yeah, I don't do it, right? I worked up there, in Alaska cold regions for 30-some years, so I've never done it either. It's kind of a researchy thing, but we typically don't have real data on what our soil temperatures are, so we're going to make some assumptions and hopefully come up with some basic calculations that are giving you some help and insight in designing and operating those water systems. Okay? So there are a few modes of heat transfer. In water systems, the more so, I think, for buildings and building systems and those kinds of things. You know, we don't have convection as heat transfer between a surface and a moving fluid. Frequently this is, you know, wind blowing across the surface of a building. It can be water flowing through a pipe. but it's also proportional to the area. But this is one where it is small in most cases relative to production, and radiation is just that, right? That bodies emit some radiation really is important in cold climate building designs, but non-frozen soil have quite a bit of different thermal conductivity. And you can think about that, right? Ice is a better conductor than water. So let's take a look at some thermal conductivities for different materials in water systems. And so I want to point out a couple of things here. Let's just kind of dive in here, right? Let's go down to copper, right? Copper at the bottom, very common, I don't know about in India, but in the US, very common service line material and interior plumbing material. Relatively easy to work with, relatively inexpensive, but it's a terrible material from a heat transfer standpoint. All right, on the list of these things, right? Back here. Sorry. Oh, my pressure keeps going. What happens here? Something like that. There it is. Okay, so copper, really terrible, right? And I'll show you some calculations here in a little bit. Is a great conductor of heat, right? It's the best on the list, which begs the question, why would we ever use it, right? It turns out, I'll give you some reasons, right? It's a pretty good material other than for this circumstance. Let's look at air, right? Just a little bit of air, right? My puffy jacket, your polar fleece, right? Air is a fabulous, is a fabulous insulator. It has a very, very low thermal conductivity, right? Does not conduct heat very well at all. And so the idea of, putting some air around our pipes is a pretty effective way to insulate. You can look at different materials there. You can look at polyurethane foam, polystyrene foam, two very common insulating materials in cold regions, utilities operations. You can buy polystyrene, polyurethane foams. You can foam them in place. They're really effective insulators because they trap lots of air, and they're relatively inexpensive, or at least they used to be. And then you've got some other things that are important. Snow, really a very good insulator, right? Snow is a very good insulator. Just new loose snow has a a thermal conductivity of, something that's, right in the neighborhood, at least in the same order of magnitude as some manufactured insulation, right? So snow cover can make a huge difference in how things freeze. Ice at minus, ice at 0 degrees Celsius, ice at minus 40 degrees Celsius is a pretty high thermal conductivity of 2.2 to 2.6 watts per degree Celsius. And then you've got these other elements here, a couple things to look at. Here's clay, thawed and frozen, significantly at 20% moisture content. Significantly different thermal conductivity when it's frozen, much higher than when it's thawed. Which is gives you some insight as to what happens when your pipe is in a frozen front, right? You've got the surrounding material becomes a much better conductor of heat away from the pipe when it's frozen. All right, and here's different materials. Here's the other thermal conductivities for polyethylene pipe, HDPE pipe, HDPE pipe, around 0.06, polyvinyl chloride, PVC pipe, ductile iron pipe, right? a little higher thermal conductivity, but nothing in the neighborhood of aluminum and copper. So these numbers we're going to come back to give you some pretty good ideas of what's going on. These are really important numbers to talk about. So here's an example of some graphs out of the Coal Regions Utility Manual for 3 different types of soils. Here's peat, right? Peat happens to be a very good insulator, right? It has very relatively low hydraulic conductivities. If you look at these numbers relative to the thermal conductivity of silt and clays versus the thermal conductivity of sandy soils, you can see that peat is a very good insulator, a very poor conductor of heat, which is why, you know, the old timers in Alaska would chink the gaps in their log cabin with peat, right? Pretty common for cabins constructed in the Arctic to go out and dig up big chunks of peat and put that on the surface of the roof for insulation. Readily available local material. It's a good insulator, a poor conductor of heat. Lots of airspace within that heat makes it a good insulator, right? The differences, if you look carefully at these graphs, you can see the differences between the thermal conductivities of the silts and the clays and the sandy soils and gravels. And at a very minimum, that's kind of a distinction that you can make to kind of get you in the ballpark of what kind of soil you have. Do you have clay soils, silty soils, or do you have sands and gravels? You can make some pretty reasonable, if you know something about the moisture content of those soils, you can look at these graphs and look at, there's different densities, there's different moisture contents. You can go in there and pull off a thermal conductivity that gets you in the ballpark, right, of what you can use for the soil column. Okay? Thermal resistance is just the inverse of the thermal conductivity. Thermal resistance is a number that we'll use a lot. It's inversely proportional to the thermal conductivity. So a little bit of math there depending on how you solve those differential equations. But it has units of meters, degrees Celsius, or watts. It turns out, you know, it becomes handy to use in some calculations. We started to add up thermal resistances. So I got a layer of insulation, I've got a layer of, I've got a pipe wall, and I've got a layer of insulation, and maybe I've got another pipe wall. You can start to add up these thermal resistances to get the thermal resistance for your whole system. So this is the R factor, if you will. Okay. All right. Not too much more here. Heat capacity, and then we'll take a short break. Heat capacity is the amount of heat supplied for a unit change in temperature. It's top property of the material. The specific heat capacity is just the heat required to raise a unit mass of that material a degree. And then the volumetric heat capacity, right? Volumetric specific heat capacity is just the heat required to raise a unit volume of the material 1 degree, right? And so that big C, that volumetric heat capacity, which is what we're most often going to use in our calculations because we're interested in soil systems that have a certain density of kilograms per cubic meter, and its specific heat capacity. Okay, so the specific heat capacity really doesn't do us much. It's not very practical for us when we're thinking about soil calculations anyway. So we're very much interested in this volumetric heat capacity. Every now and then, this specific heat capacity will come in. I'll show you those when we do some example calculations. Right? So the specific heat of water, again, is a material property. It's 4.8 kilojoules per kilogram per degree Celsius. For ice, it's 2.09 kilojoules per kilogram degree Celsius. For water vapor, it's 2.01 kilojoules per kilogram per degree Celsius. For most dry soil solids, right, the estimate is about 0.7, completely dry, 0.7 kilojoules per kilogram per degree Celsius. Okay, so those are some constant numbers we'll see. The other concept I want to talk about here, and we get into these fundamentals, is the latent heat of water, right? So the amount of heat needed to produce a phase change. So for water, the latent heat of fusion is the amount of heat added or removed to change from water from liquid to ice, or ice to liquid, right? And the latent heat of vaporization is what it takes to vaporize liquid water to water vapor, or condense water vapor to liquid water. We don't care too much about this, right? We don't care too much about the latent heat of vaporization, but we do care about the latent heat of fusion. And it requires 80 calories, right? Removing or adding 80 calories to affect that phase change. And so once you've frozen a pipe, right, you gotta add 80 calories to get that pipe to start to thaw. The temperature won't change. You're just pumping heat, adding energy into the system, right? Until you get to the point where you get a phase change, and then we can start to thaw the pipe. And so that is frequently underestimated, right, in these kinds of systems. And once the systems are frozen up, it's really quite difficult to get them back, in large part, because of this concept of the latent heat of fusion of water. Okay, so what is the latent heat of fusion of water? We'll see these numbers again. Here they are. From liquid to a solid, or solid to a liquid. It's 335 kilojoules per kilogram, right? The latent heat, here's the latent heat of fusion, but the bottom one here is important, right? The latent heat for fusion of a soil-containing water is frequently estimated as just the latent heat of water, 335 kilojoules per kilogram, times the moisture content, times the dry density. So if you know the moisture content, and know something about the latent heat of fusion for soil-containing water, that phase change of water, right? Water is the dominant material in the soil column as far as a temperature change is concerned. So if we know the moisture content, we know a lot about what the column's going to do. Okay, so we stop there and see if there are any questions. Comments, thoughts. It's a lot of background material. Okay. Hopefully we didn't spend too much time on it, but give you some basics or understanding for what we want to do next. And do we need a break, or what's the okay. So let's now go into the third module. Now let's take all that kind of those concepts, both conceptual, we talked about the first module, and a little more theoretical and some kind of basic terminology of the second module. And now let's start to estimate some frost depths and freeze-up times, et cetera, which is where hopefully it gets maybe a little bit more interesting. So there's some useful calculations, I think, that are out there that are helpful in cold regions. One is the freeze depth, right? How deep can we expect that frost front to be? And obviously that's going to be a function of a whole bunch of things. It's going to be a function of the thermal properties of the soil, right? The thermal conductivity of the water, the thermal conductivity of the soil particles, the latent heat of fusion of water. Is going to be a function of air temperature. How cold is the air temperature? How cold are the solids? What is the temperature at the solid air interface, right? Just because I'm minus 10 degrees here doesn't mean at the surface of the ground I'm minus 10 degrees. Frequently I'm several degrees warmer, okay? We also want to talk about heat loss in pipes. Right? That's going to depend on a number of things, right? Thermal properties of the pipe and the surrounding soils, right? What's the thermal conductivity of the material itself? What's the thermal conductivity of the insulation around the pipe? What's the thermal conductivity of the surrounding soil? Obviously the temperatures, air temperature, soil temperature, water temperature within the pipe's going to make a difference, as well as what's the duration of the freezing period in both the soil and heat loss pipes. If heat loss calculations, if I have 1 degree C day of freezing, I don't have much to worry about. But when I have several hundred degrees Celsius days of freezing, which we could expect here in the colder regions of India, then I do start to run into some problems. Okay? So we can run some approximate calculations. They're going to be just that. Right? I think you need to take them with, you know, the uncertainty that we're baking into this, right? We're knowing all of these things. We need to understand that they're approximate calculations, but I do think they're helpful. And they do, when we run a few examples, give you some insight on the things that make a difference in your system. Okay? So let's first of all talk about the handy equation to approximate freeze depth. And so Newman, right, in the early 1900s, solved this frozen soil equation. He came with a pretty complicated solution. Since then, a number of people have modified his solution, and one of the modifications to that is the Stefan equation. It's got a very similar equation to what we use to calculate how deep how thick an ice on the lake will grow, right? But it's a pretty simple equation, and it tells you that. Oops. I think I just found a mistake. This should be raised to the 0.5 power. I think I've got it right on the other exams. I think I just found a mistake. So anyway, here's the soil freezing index, right? Raise that to the 0.5 power, right? Take the square root of that. Well, I'll show you an example here where I run the calculations. But there's a number of parameters here. K is the soil conductivity, thermal conductivity. The freezing index we've already talked about. The latent heat for water containing soil we've already talked about. The one parameter we haven't talked about so far is this N, right? All right. This calculation is going to give me a depth in meters. That 13.15 accounts for a number of unit conversions in there. All right. So let's look at that N factor. So the N factor is that factor that is relating air temperature to surface temperature. Right? It's going to be different depending upon, right, the circumstances on the surface of the ground. If everything is worst case or perfect, however you want to think about it, the air temperature and the ground temperature would be the same. So that's rarely the case because the ground material is different. And so we could have a very hard surface like concrete or asphalt, and that N factor is going to be pretty close to the air temperature, 0.7 to 0.9. But I could have a peat soil or some brush, or right, I could have grass, or I could put snow on top of it. I could put bales of hay. All right, I could put a bunch of peat, and I can dramatically increase or change the N factor. And so let's say relative to concrete, which might be a concrete or asphalt surface might be 0.8, 0.9, right? Relative to, you know, the grass around your house, right? That N is half, almost half of what we might expect on that hard surface. And so where do we bury all of our pipes? In the lawn or underneath the road? I don't know here. Huh? Both. In both, yeah. But in service lines, but I mean, most of it, in the U.S., most of our main lines are under roads, right? Which is the worst possible place for it to be from a thermal conductivity standpoint, from a freezing standpoint, but that's nonetheless, right? So you in the U.S. will hear this idea, well, the frost gets driven into the ground, right, as cars pound on the pavement. Really what's happening is, right, that pavement surface is a pretty good conductor of cold, right, a good conductor of heat, and the frost depth goes deeper because, right, there's not, the surface temperature is very low on those hard surfaces, as opposed to, right, if we have, some snow or, some willows, here's some grass, here's some turf, right? So that N factor becomes important. Okay. So let's estimate, for example here, the frost depths. And so let's do two soils. Okay, let's do a sandy gravel with a moisture content of 5% and a density of 2,000 kilograms per cubic meter, and a silt clay with also the moisture content of 5% and a density of 1,800 kilograms per meter. So these are kind of representative, if you will, of these two soil types. Would be helpful for your system to kind of have a better idea, but these are probably good enough right now to give us a feel for these calculations. And so I can go and read off from these charts that I've given you. They say watts per meter degree Kelvin. It actually should be watts per meter degrees Celsius, right? But I can go through and I can pull the numbers off for sandy soils and frozen soils, and you can see that for sandy soils at that density and that moisture content, the thermal conductivity excuse me, is going to vary from 2.3 to 2.5. Begs the question, well, which one do I use? I don't know, is the soil frozen or not frozen? Right? Kind of hard to say, right? Worst case scenario, you'd probably go frozen. I'm just going to use the average. They're not that far apart. Becomes a bigger question if they're that far apart, or a long ways apart. Same with the silty soils in this case. I'm going to use 1 watt per meter degrees Celsius for the silts in the soils, and I'm going to use a thermal conductivity of 2.4 watts per meter degrees Celsius for the sandy soils. Okay? So now let's talk about our freezing index. What are we going to use? So we're going to use for lay, we talked about this earlier. We're going to use an average year, and we're going to say that's 400 degrees C days of freezing. And then we're going to have a quote-unquote cold year, okay? It is 800 degrees. And we're going to look and compare these things, and we're going to look at N is the worst case scenario where the air and the ground temps are equal. Typically, right, that's going to be a factor less than 1, but this gives us kind of maybe a worst case scenario. And we know that the ground temperatures are several degrees warmer, right, than the measured air temperatures. Okay. So we calculate, next we need to calculate that latent heat of soil water. So L for the sandy soil is just 335 kilojoules per kilogram, the latent heat of water, multiplied by the moisture content divided by the density. Same for the clays. Okay? So now we've got our latent heat of water, and we can pull this together. All right, here I've got it correct down here. I apologize, I don't know what happened to my 0.5. I thought I'd fix that. All right, but here's our sandy soil. Okay? And remember, put here the 0.5. I'll get this fixed in the documents I send you. But here's our sandy soil. Okay, so I've got my conversion factor. Here's my thermal conductivity for the sandy soil. Here's my 0.8, that's what I'm going to use. I'm using in this case 0.8 for my N factor. Okay, I think I've got some examples with it at 0.12 or 1.2. 400 degrees Celsius per day is my freezing index, and then here's my latent heat of water, and I calculated an estimated depth right of around 2 meters. Seems about right, right? So that's for our sandy soil. What would you think the frost depth would be, more or less, for the clay soil? Who says more? Who says less? Why?
Negative conductivity of soil, clay and sand is different.
Yep, got a different thermal conductivity. Yep. In this case, the moisture content is the same, but the thermal conductivity is different. Okay? What if we change the moisture content? Right? Okay? A big difference, right? Show you some examples. What if we change the N factor? We use 0.8. What if I use 1? What if we use 0.5? Be a difference, right? What if I change the cover material? Right? Those are going to be difference. So here I've done a few calculations just to start to point out some things, give us some things to talk about. Okay? So, as an example, right? So here's our example that we just went through, 400.8, right? 2,000 kilograms per cubic meter water content. Here's our estimated depth. If I change the moisture content, right? If I change the moisture content to 3%, right? So here's an example that I showed the calculation for. Now I've changed the moisture content to 3%. What happened to the increase, right? Then conceptually there's less water in that, right? To make that freeze front progress, you have to freeze all the water. If there's less water there, right, the freezing front is going to go deeper, right? You have a certain fixed number of degree days that's driving the frost depth, and we're calling the frost depth, you know, where the soil temperature is 0 degrees Celsius. Sorry. There we go. Okay, sorry about that. Okay, let's look at the next one. Here, if I change the N factor, right, from 0.8 to 0.5. Now instead of being in looking at the frost depth in the road, I'm looking at the frost depth in the grass around your house or your garden, right? It may be 0.5, and so the frost depth is significantly reduced, right? Now if I look at this, these are all for 400 degree C days of your average Indian winter, right? If I look at 800, a cold one, you can see what I've got here, right? At 5%, a frost depth that could be up to 0.8 meters more on a really cold year. And so that's something I think to kind of keep in mind, and a reason to make the point of kind of keeping track of this freezing index, because it's going to make a big difference in that frost front. Now it doesn't double, right? It doesn't go 400 to 800 degrees Celsius days. Doesn't go from 2 meters of frost depth to 4 meters of frost depth because it's of the equation with the 0.5, but it does make a difference. Right? And then let's look at the clay soils. Here's our example, 5 degrees, 5% moisture content, 1,800 kilograms per cubic meter, 0.8, 400 degrees Celsius days. In the clay soil, instead of 2 meters of frost depth, it's 4. Excuse me, 1.4, it's much less, right? The thermal conductivity of the clay soil is not as good, right? It's 1 watt per meter degree Celsius as opposed to 2.4 watt per meter degree Celsius. So the type of soil material makes a difference. And then if I really wanted to get down to here and I just run one quick calculation, let's say I put an insulation on the top, or I filled I've got a really very well insulated soil with a very low thermal conductivity of 0.03. I can almost completely retard the freezing front. Right? Gives you some insight as to the power of that insulation. Right? So that's a pretty useful calculation. One I think that you can run in your system. You have some idea of your freezing index, you have some idea of your surface conditions, and you have some idea of the soil type and the moisture content. You can do you can set up a spreadsheet, right? This is a simple calculation to do. You're going to run and you can estimate soil frost depths for different conditions throughout your system. Even better, you can kind of, as the winter proceeds, and you start accumulating freeze days, you can start to kind of estimate, well, hey, in this part of town, it's getting to the point where I'm going to have some frost depths that are going to cause problems, or not. Yeah. Make sense? All right, so now let's look at some approximate times for calculating heat loss and freezing in pipes. And this is Fourier's heat transfer, Fourier's law for conductive heat loss. That's what we're interested here, is conductive heat loss, right? And it's got that term, thermal conductivity. It's got the area, right? Normal to the direction of heat transfer. Heat is going to go from a high temperature to a low temperature. And in our system, the high temperature is the water, right? And the low temperature is the surrounding air or soil. And the thermal conductivity is, right, how that heat transfer is going to occur is going to be dependent upon all of the material that's between the warm side and the cold side. If it's just the pipe, we don't have much thermal resistance, so we have a very high thermal conductivity. If it's a pipe plus insulation, things get much better. And I'll give you some examples here in a second. Okay, make sense? So we really don't care about, well, the configuration that we care about for solving Fourier's law is a pipe, right? And so we have to solve it in cylindrical coordinates. And if we do that, let's just take that solution for a very simple pipe. Here's my pipe, right? It's an uninsulated pipe. It's got, RW is the radius to the inside of the pipe wall. RP is the radius to the outside of the pipe wall, right? It's got a unit length of L. And the temperature on the inside is the temperature of the water on the inside of the pipe. Temperature on the outside is the surrounding environment. Could be the air, could be the water. We'll go through examples with both. And RP is the thermal resistivity of the pipe. And the thermal resistivity is related to that thermal conductivity K by this equation. So if I know the thermal conductivity and I know the configuration of the pipe, I can calculate the thermal resistivity. And then I can use that to solve for the heat loss per unit length of pipe in watts per meter. Right? If I know the temperature difference and the thermal resistivity, and that I calculate from the thermal conductivity and the pipe configuration, then I can calculate, solve Fourier's law, and figure out how many watts per meter of heat I'm going to lose. Right? So let's do that for some common pipe types. And what I've picked 4 different pipe types here. And I'm going to try to carry through all of the examples. One is just a 1-inch nominal type K copper service line. The second one is a nominal 1-inch HDPE service line. And then I've got a, well, now I'm lapsing into my English units, right? 25.3 millimeters, I'm going to call it 1 inch because that's how I think, right? 28.6 millimeter inside diameter, roughly 1 inch. And then HDPE 153, 152 millimeter pipes, and pull these off from some just generally available pipe dimension information. You're going to go to a vendor and they're going to have all this information available for you for the pipes that you want to look at, but I think these are reasonable representations of materials that we might use in water systems, and they've got certain wall thicknesses, right? And so we've got these different radiuses, and then here's this thermal conductivity that we've talked about before. All right, here's the thermal conductivity for copper, 375 watts per meter degree Celsius. Here's the thermal conductivity for HDPE and ductile iron. We're going to do a couple calculations, and we're going to see, well, how does this impact it, right? So let's just do another example, right? Let's just assume that we've got a copper service line, and it's exposed to air at minus 10 degrees Celsius, right? So it's out there, right? Someone ran it up outside of the home. It doesn't go underneath. It's just out there in the elements, right? In a worst case scenario, given, right? Say the water temperature on the inside is 5 degrees Celsius. I can calculate, right? Here's my thermal resistance. Here's the radius of the pipe and the radius of the ratio of the outside radius and the inside radius. Here's the thermal conductivity. Here's our sub P, and we have this whopping huge, right, heat loss per unit length of pipe. Right? So for all intents and purposes, the copper doesn't even, it's not even there from a heat transfer standpoint, right? It's such a fabulous conductor of heat that it really provides almost no resistance to heat loss. Okay. But let's compare pipe materials, exact same scenario. All these pipe materials are exposed to 10 degrees Celsius, minus 10 degrees Celsius on the outside, all exposed to air, right? 5 degrees Celsius in the interior just gives you kind of an idea of the impact of the pipe material itself on heat transfer. Huge heat loss per unit length for copper, much smaller heat loss per unit length for HDPE. Still a pretty good heat loss per unit length of ductile, right? Different materials, different thermal conductivities, right? Something to kind of keep in mind. Rarely, right, so if we're kind of burying uninsulated service lines, this makes a pretty good argument for being HDPE. Now when we start to coat these things with insulation, we find out that the pipe material is not quite as important, right? But if we're not insulating it, the pipe material is a big deal. And the metal pipes really are very good conductors of heat and tend to be very prone to freeze-ups, especially on some of the small diameter kinds of pipes that cause impacts to customers right away.
So here is the SDP pipe is better than the DI pipe in terms of heat loss per unit length. Is it correct?
That the HDPE
is better than DI pipe.
Yes. Yeah. But we'll yes, from a raw material standpoint, that's true. Yeah. Now there's other reasons, right, to think about these materials. Effective use of copper, HDPE, and ductile occurs in cold region systems. I just want to give you a feel for the type of material and what its thermal properties are. So, and I think also to make the case that I'm going to make right now is, if we're worried about freezing and you're not insulating, you're just asking for trouble, right? Because these pipe materials are really not very good. Now, HDPE is much better, but by themselves, right, if you're in an area where it's prone to freezing, if you wanted to wander out and put this pipe on the ground and you experience minus 10 degrees Celsius, these things are freezing. They are, right? Because there's not much thermal resistance by this pipe material. All right, so now let's look at an insulated pipe, okay? Same configuration. I've got a pipe now covered with some insulation. And in this case, I'll give you an example here a little bit, but now I'm going to add up, if you will. Here's my heat loss equation, right? That heat loss equation takes into account the thermal resistance of the pipe, and it also takes into account the thermal resistance of the insulation, right? So we're adding them up. That's the nice thing about using thermal resistance. When they're in series, we just add up the R's and get a total R for the whole system. Okay? So the total R for the system is the sum of the thermal resistance of the pipe and the thermal resistance of the insulation, and that's going to be proportional to the thermal conductivity of the pipe, K sub P, and the thermal conductivity of the insulation, K sub I, and the relative radiuses, right? Remember back to our initial equation, it's Fourier's law, it's a function of thermal conductivity and area, right? And so now I can calculate the heat loss per unit length of pipe by taking this composite thermal resistivity, right, and plugging it into this equation. So if I do that, here's an example, okay? Let's say that we are going to take each of those pipe types now and we're just going to insulate them with 25 millimeters of polyurethane foam insulation, right? Very simple. One inch of polyurethane foam. And I could have picked polystyrene, right? But air entraining foam that's got the right kind of mechanical properties. And I'm just going to put 1 inch around each of these pipes. And I'm going to stick them out in that minus 10 degrees Celsius air. And I'm going to put the water inside the pipe again at 5 degrees Celsius. And I want to know, well, what are my heat losses per unit length? Remember, so here's for the copper service line. I can plug in the numbers, right? I've got the dimensions. Here's the dimensions of the pipe itself. Here's the dimensions of the insulation. Here's the thermal conductivities, and I run these numbers out, right? When I look at this overall thermal resistance, the pipe is insignificant, right? All of the thermal resistance, many, many orders of magnitude for copper pipe, due to the insulation, right? Much, much better. And so then I can calculate my heat loss per unit length of pipe, right? And now it's 2.2 watts per meter, as opposed to before it was 290,000 watts per meter, something like that, right? Many, many orders of magnitude less. By just providing a small amount of insulation, I can dramatically reduce this pipe heat loss. And if I compare those same materials again, right? Here are my new thermal conductivities. They're about the same for HDPE and copper. It's a little bit different for HDPE because because the radius is a little bit different, right? The dimensions is a proportion of the area of HDPE has a slightly different inside and outside radius than the copper pipe. But for all intents and purposes, they're the same. As well as HDPE and the ductile iron pipe are also about the same, once I've covered them with just 1 inch of insulation, right? So I want to make the point here where insulation is really critical if you're worried about freezing. Now this is a worst case scenario where I've just flopped this pipe out in the air at minus 10 degrees Celsius. We can run the calculations with lower temperatures and get these heat loss per unit lengths of pipe. Pretty simple calculation for these basic kind of pipe configurations. Okay? Right? So, a couple points to take away from these simple examples, right? Differences between the pipe materials and the importance of insulation. In all cases, really, once you insulate it, the pipe material's thermal properties really kind of go away. It's the insulation that dominates the system. Now, if you're not insulating it, right, and you want to run that risk, well, then there's a big difference between metal and HDPE pipe, right? Really, that insulation is critical. Even small amounts, right? Even small amounts of insulation can dramatically reduce the thermal conductivity loss. And so, it could be something simple, right? You can buy, materials that will fit. You can, you can even wrap them with, glass wool, those kinds of things. Anything, right, to give a little bit of thermal resistance makes a big difference. Okay? So, I wanted to make that example with a pipe and air just to kind of make the point about the differences between the pipe materials and the importance of insulation. But in reality, right, in most utility systems anyway, we're not just flopping a pipe out on the air. Typically we're burying the pipe, right? And so how do we account for that? Well, the calculations are very similar. The configuration is a little bit different. But let's consider an uninsulated pipe buried in soil in the frost zone, okay? And so we can calculate that heat loss, right, using this equation where the thermal resistance of the ground is this arc cosine function. Z is the depth of the pipe buried. R is the radius of the pipe, right? 2 pi times K of the ground. So now it's the thermal conductivity of the ground that's important. And in fact, we're ignoring in this calculation the thermal conductivity or the thermal resistance of the pipe, right? And there's a pretty good, based on our previous calculations, that's a pretty good assumption, right? these pipe materials are not very good insulators. They're very good conductors of heat. And so what's really going to govern the buried pipe system is the thermal conductivity of the ground. Okay? So let's run the calculation. Same way, calculate the heat loss from each uninsulated pipe. And I'm going to bury it at the frost line of 1 meter. Okay? The soil is a sand or gravel. It's got a water content of 5%. It's got a thermal conductivity of 2.4 watts per meter degree Celsius. And I'm going to assume the temperature in the pipe is 5 degrees Celsius, and I'm going to assume the ground temperature is minus 5 degrees Celsius. So that would come back to this point that I made earlier, that nobody measures their ground temperatures. So we have to make some kind of estimate. But we certainly know 2 points, right? We know that at the freezing front, the ground temperature is 0. And we have some idea of what the surface temperature has been. And so we can make some estimate, right? And so I'm saying, well, we've had a reasonably cold winter, and I'm going to use a ground temperature of minus 5 degrees Celsius. It's kind of in the middle of what calculated this to be a 2 meter frost depth in our previous calculation. I'm right in the middle of that. I'm going to assume it's minus 5 degrees Celsius. Again, it's a pretty simple calculation, but you can calculate that thermal resistance, okay? And then I put in my heat loss per unit length of pipe, and I end up with 31 watts per meter. And if I look at all of those buried pipes in the same kind of situation, right? I've got the diameters, I've got the thermal conductivity of the pipe, I've got the thermal resistivity of the pipe, I've got the thermal conductivity of the soil, I've got the thermal resistivity of the soil. You can see in all cases the thermal resistivity of the soil is much, much greater than the thermal resistivity of the pipe. I'm going to functionally ignore that, right? And now I'm going to have these heat loss per unit length of pipe, so somewhere around 31 to 32 to 48 watts per meter. Okay? So much a little bit different than our minus 10 degree air. We've got a different kind of situation now with this buried pipe. And so, and this is an uninsulated pipe. We went back and looked at the example, right? An uninsulated pipe in the air at minus 10 degrees Celsius versus an uninsulated pipe buried in the soil. We've got, quite a bit of heat loss, but a much lower magnitude. Okay? So now let's do the same situation for a buried insulated pipe. And so in this case, same kind of equation. Here I'm solving, right, this equation, and my composite thermal resistivity is the resistivity of the ground, is the resistivity of the insulation, and it's the resistivity of the pipe. And the pipe, we know, has a thermal resistivity that's very, very small, calculated anyway. It's very small, we can ignore it, but the ground and the insulation are really important. And so here's the thermal resistivity of the ground. That's the same equation we used before. This is our cosine function, the depth of bury and the radius of the pipe, and the thermal conductivity of ground. And then here's our thermal resistivity for the insulation. Again, the radius, the thickness of the insulation, and the thermal conductivity of the insulation, and we're basically going to ignore that pipe. Here's our configuration, right? Here's our pipe, and here's our insulation, right? And here's our depth of bury. We have a soil temperature out here that we either have to measure or make some sort of assumption. That if I do all that, and I run the calculations, this is what I get. Again, for our frost line, or depth of frost buried in the frost line at a depth of 1 meter, so we're assuming the frost depth is greater than 1 meter. It's a sandy soil again. We've got a water temperature of 5 degrees Celsius, a ground temperature of minus 5 degrees Celsius, and I can run through the calculations here, right? Here's my thermal resistance of the insulation. Here's my thermal resistance of the ground. I plug these in, and now I get a heat loss per unit length of pipe of 1.4 watts per meter. Right? So quite a bit less than I had before. And here's the calculations again, just to give you some idea. Again, now we're really making a big difference, right, in watts per meter. If I go back to the previous one, right, here's our uninsulated pipe. We've got heat losses of 30 to 50 watts per meter. My insulated pipe with just 1 inch of insulation buried in the ground, I have order of magnitude smaller heat loss. Now this is something now I know I'm losing 1.4 watts per meter. I need to add 1.4 watts per meter or keep that water moving so that we don't allow freeze-ups to occur because of that heat loss. Make sense? Okay, I'm going to take a break there because we're growling through a bunch of numbers. Any questions or comments on that? Okay. I think they're useful calculations, and one that give you some examples. I think the examples are intended to kind of help illustrate the importance of insulation and the difference between pipes, but the fundamental calculations are very useful in, whatever configuration you've got. Yeah.
Sir, I understand that this calculation is very good for comparison purpose, but I am not able to understand where this is going to be used, because this heat loss per unit length, is it for the stagnant water or is it for the flowing water? Because time factor is not considered, velocity is not considered.
Yep, we're going to do that next.
Okay.
Yep. Yep, perfect. Yep. Those examples were just intended to help you understand the importance of material and insulation on heat loss. That's not a particularly useful. It gives you kind of an idea of how much heat you're losing, but you're really interested about, well, how much, right? How long do I have before things freeze up, and at what velocities? If I run the system. So let me back up a little bit. Those examples would be for stagnant water, right? Well, okay, fine. In that pipe, that's wonderful. That's a nice number. From a practical standpoint, what's that mean? Well, I'd like to know how long it takes for the water to freeze. I might be losing it at 1.4 watts per meter. But what I'm really interested in is that a day? Is that a month? Is that a week? Is that 5 hours? How long does it take to freeze? And the other thing I'm interested in is, well, if I keep the water flowing, right? And what velocities do I need to have in that pipe to keep that heat loss from losing enough heat to cause the system to freeze? And that's what we'll do next. Okay.
I have a question. Like, have you considered the Hazen-Williams part in this calculations or the seawell effect?
What?
Hazen-Williams seawell.
No. Those examples were basically stagnant, no flowing water. Yeah.
I don't know the practices, what I'm looking at with entire iron pipes.
Yeah.
But here we are adopting like the entire iron pipes which comes here. It is a kind of what do you call itself a pending insulation. It comes with the internal cement and outside bituminous and zinc coating.
Yep.
So there is a, you can say tertiary kind of insulation inside on the pipe.
Right, and you should be able to. I don't know if you've got the material, the data, but
we have considered those elements while making on this comparison.
yeah, what you want from that composite material is an overall thermal conductivity, which you can run some tests on and estimate. It's going to be less than just the bare pipe, but how much thermal resistance those different layers add to that, you have to run the calculations and run the test. Yeah. Okay? All right, so now let's get to some practical calculations. And let's take that unit length of pipe and now let's estimate heat loss and freeze up times in that pipe. Okay, so here's the situation. So now I've got water flowing through the pipe, okay? And it's got an inlet temperature and it's got an outlet temperature. And I'm going to have to make some assumptions about that. I know something at the end of a length of pipe, whether it's a service line or a length of main, I pretty much know I want the temperature to be above 0, right? Otherwise I have a problem. And the inlet temperature is going to be a function of your system. What's the groundwater temperature? What's the spring temperature? What's the surface water temperature? It could be seasonal. You're going to have to make some assumptions about that. You have to have some thermal resistance in the pipe, right? You've got an external temperature. If that external temperature is the ground, we'll do those calculations, and we can make some estimates. So the other things that are important here, right, are the Q, right here is the velocity times the area, the flow velocity times the area. You want to know what the velocity is. Here's the volumetric heat capacity of water. Those are going to come into play in the calculation. So there's my physical situation. This could be a 10-meter service line. This could be a 1,000-meter main line. Right? So in the Coal Regions Utility Manual, there's a whole series of very useful calculations, all centered around this idea of how long does it take for the pipes to freeze up, and what velocities do we need to operate the system at to keep them from freezing up. And so I'm going to pick and choose a few calculations out of there. I put them in here in entirety so you have them. Right? I think I've defined all the variables in the notes, so you can go back and do some calculations. But it utilizes this idealized pipe section. It's got variables of R, the width of the pipe material and the pipe insulation. It's got variables of inlet and outlet temperature, and it's got variables of velocity of flow, as well as heat capacity. Okay? So let's run a couple of calculations. So let's do another example here. Right? So let's estimate or calculate the time required for water to drop from 0 degrees Celsius to -3 degrees for a no-flow condition. So this is kind of what we're concerned about here. Is if I have a system failure, or I have a customer that doesn't keep, you all know we can keep water from freezing if we keep it thawing. Maybe a more interesting question is, how long does it take before it freezes if I don't flow it? Right? That's what this calculation will let you do. So that could be a service line, that could be a main line. But typically the service lines are the ones that freeze up first. And so how much leeway do we have? Right? If I have a customer that doesn't flow his or her water overnight, and it's very, very cold, and the water line is buried below the frost depth, how long do I have? Okay, those kinds of calculations. So here's our uninsulated HDPE service line, the same pipe we've been using throughout all of these examples. There's the formula. Okay, area is the area of the pipe. Right, A is the area of the pipe. R is the thermal resistivity of the soil. C is the volumetric heat capacity of water. And then it's the natural log of the temperature difference. TW1. TW1, right, is 5 degrees Celsius. Right, that's the water inlet temperature. TA is the surrounding ground temperature. Again, in this example, we're assuming -5 degrees Celsius. 0, right, is the point that we start to, when the water gets to 0 degrees Celsius. And so, right, that calculated freeze-up time is about 1.6 hours under these circumstances. So that's when it takes 1.6 hours for the temperature to go from 5 degrees Celsius, right, to 0 degrees Celsius for this pipe buried in soil with that thermal conductivity and that temperature. It's not an unreasonable kind of serious situation for a service line, and so, right, that's not that long, right? So that service line buried in a frozen soil is very, very prone to freezing. I've got a little bit longer if I did get it down to -3 degrees Celsius. Remember back to the example I had about how pipes freeze in water. -3 degrees Celsius is the nucleation temperature. That's when things start to get really serious. And we start to move from that dendritic ice to that annular ice, and it starts to build up very relatively quickly and start to include the pipe and freeze it off. Have a little bit, have almost 4 hours, right, to get there. Right? And then this last calculation, right, is how long until the whole thing is frozen solid, right? And so it takes a while, right? It takes 38 hours for the thing to freeze completely. Here I've started to, at this point, this one, excuse me, right? To get to that nucleation temperature is 3.8 hours, right? To have all the latent heat of fusion removed from the water before it completely freezes takes quite a bit longer. Now, you never want to get out there, but it's a useful calculation to do. Okay? So let's take a look at this. And so here's the different pipes. Here's the different freeze-up times. Again, here's my type K copper pipe uninsulated. Here's my type, my HDPE pipe. Here's the ductile and HDPE 6-inch main lines. You can see the different freeze-up times. And so that uninsulated pipe buried in the frost zone is very, very prone to freezing. Even, right, even the big ones are, right? Even the 6-inch and ductile and HDPE pipes have, right, if they're not flowing, and they're buried in the frost zone, they can freeze up in, a matter of days, right? Your service lines can freeze up in a matter of hours if they're not flowing. Okay. If I did the same calculation now for insulated pipes, my life gets so much better, right? Same exact scenario as before, same pipe, 1 inch of insulation around the copper, around the HDPE pipes. I can run those calculations again. I have much better thermal resistance, right? And my freeze-up times, instead of 1 hour, 1.6 hours, right, are now 28 hours. Right? So now I've got something I can work with, right? I've insulated this pipe. Now my question is it reasonable for a homeowner to not run the service line for 2 hours? Sure. Right? Do you think most homeowners might not run the service line for more like a day? Well, now we got something a little bit different, right? Now if you go away, leave, on vacation, things like freeze-ups happen. But this gives you an idea of how the importance of insulation is and how long it extends that freeze-up time. And you can run these kinds of calculations for your, for your system and get some ideas of how long, right, you've got until you've got problems with in parts of your system. Frequently, it's going to be the service lines. Okay, let's do another example. Okay, let's calculate the flow required now. Okay, let's calculate the flow required for that 1 inch, 28.6 millimeter HDPE service line, and I want to make sure that the water coming out of that service line stays at 3 degrees Celsius. Right? And I'm going to assume that my inlet water temperature is 5 degrees Celsius. That's going to be a function of your system, your water source, and that's a 10-meter long service line. And if I assume that the service line is buried at 1 meter deep in sand and gravel, with that thermal conductivity that we've used throughout all our examples, and I want to maintain I want the outlet water pipe. I think I've got a typo here. Sorry about that. Outlet water pipe should be maintained at 1 degree Celsius and the ground temperature is at -5. Right? So I can pull these numbers in. Here's the formula that I pulled off of that table. This allows you to calculate the velocity required. L is the length of the service line. A is the area of the pipe. R is the thermal resistivity of the soil. C is the volumetric heat capacity of water. And then here's my temperature ratio. 5 degrees is the water inlet temperature. -5 degrees is the surrounding soil temperature. 1 degree C is what I want the water coming out of the 10-meter surface tap to be at. Not 3, but 1. Or putting correct at the top. correct at the bottom. Then -5 again is that outside surface. So I need to maintain a velocity to keep that from freezing, or keep that outlet water temperature, the temperature coming out of the tap, if you will, for that service line. The velocity needs to be 0.02 meters per second. That's going to be different with different lengths, right? You have different heat loss over the length. But this is a calculation that gives you an idea of, well, how much water do I need to flow? And so, you know, I think we talked a little bit about, you mentioned, the idea of keeping some of these systems flowing to keep them from freezing up, and then having all sorts of problems with, you know, ice buildup and the watering points and those kinds of things. Well, it gives you some idea of what minimum flow you need to occur, and you give some homeowners and people some guidance as to how much should you crack the system if you want to maintain flow like this. Okay? So there are those calculations, right, for all the different types of pipe. Here are the flow required velocities and the required flow rates, right, based on the pipe, and so you can start to get a feel for how fast you need to have flow through these systems. Now, if it's a service line, you might have to bleed that water off to keep the flow through. If it's a main line, well, then we can start talking about circulating systems to keep it from freezing. Okay? Last calculation, and then we'll take a break and we'll start talking about some other kinds of ways that we can mitigate these kinds of things in systems. So here's the last example. I want to calculate the heat loss in a system, and I've got 1,000 meters now of uninsulated 6-inch, 153.4 millimeter HDPE pipe. I've got a water source temperature of 5 degrees Celsius. Again, it's buried at 1 meter. All right, in sand and gravel. I assume the ground temperature is -5 degrees Celsius. What is the output fluid temperature as a function of velocity? Well, what's the temperature, right? As the velocity changes, what's the temperature at the outlet of this 1,000 meter, right? I want to run some calculations there to see what my final temperature might be. And so this is the formula again right out of that table. G is this function now of flow rate, heat capacity, resistivity, right? I can plug that into this equation. It's a function of G, it's a function of the temperature difference, and it's an exponential function. If I run those calculations, again, pretty straightforward, here they are, right? And I picked the velocity, let's say I picked the velocity that allows me to calculate the flow rate. It gives me a G value. I plug that G value into this equation, right? And I get a heat loss of 35,572 watts. Okay? Now I can take that and I can use one of the other equations, this equation out of that table, and now I can start to calculate the external, the temperature coming out of that length of pipe. Here's TW2, that's the outside temperature, or the temperature of the water leaving that 1,000 meter piece of pipe buried at 1 meter in frozen soil. And if I plug in all of those numbers at that velocity, that outlet temperature is going to be 0.41 degrees Celsius. Right? So now, right, I've got a little set of calculations that I can use. And if I know the length of pipe and I make some assumptions about the velocity, I can figure out what the outlet temperature is. And if I know my inlet temperature is 5 degrees Celsius and I have a 2,000 meter system, straight line pipe or loop system, whatever, right, I can start to estimate, well, how much I know. I can calculate the heat loss across that length of pipe, and then I can also calculate the temperature that I would expect at water at the end of that length of pipe. So now I have a pretty useful set of calculations that will allow me to run some scenarios looking at different pipe types, different insulation thicknesses, make some assumptions about different velocities, right? You can see and come up with some pretty interesting calculations. So for this 1,000 meter piece of pipe that we're doing this example on, if it's uninsulated, right, and I'm flowing at 0.1 meter per second, the outlet temperature of that is going to go from 5 degrees Celsius to 0.41 degrees Celsius. If I take the exact same 1,000 meter piece of pipe and I insulate it, I can drop the flow velocity required by an order of magnitude, right? And still maintain a temperature above 0 degrees Celsius. So these are pretty simple, actually, calculations. You set up a little spreadsheet. I'll provide you the one I use to run these calculations so you have it. But they're handy calculations for you to do on your system. And so now we've got, I think, at least some rough calculations that you can use. We can use some rough calculations to calculate frost depth. We know something about how to calculate heat loss from pipes. We know something about how to calculate freeze-up times, and we know how to start to calculate situations where I can estimate temperatures on the front inlet and outlet and what kind of heat loss is associated with that. And so, if I take this example and I am uncomfortable with this, right, and I'm running this is too close to the edge, so I have a couple of options. So I say, gee, I'm not really comfortable with this situation. I said, that temperature is not high enough. Well, I could increase the velocity, right? That means I've got more, if you will, warm water coming in at the head of the system. And so it's flowing through the system faster. And so the heat loss is going to be less. So the outlet temperature will be higher. I could I could change the velocity. I could change the insulation thickness, right? I can adjust a number of variables that way so I can start to get a system that I'm comfortable with that will operate without freezing. Now, I'm going to take all these with a little bit of grain of salt. We made some pretty big approximations. I picked data, numbers that I thought were kind of representative. But you may have better information on your system about, buried depths, soil temperatures, those kinds of things will factor in. But the point is, hopefully you got a feel for the kinds of parameters involved and an idea of how to run some relatively simple calculations to give you some insight. I know that's a ton of material and lots of equations in a very, very short time. Why don't we stop there and maybe take a short break? And 10 minutes? People are on schedule, so if you want me to keep going, I'll keep going.
No, just take the rest.
Okay. You could take a rest too, yeah. So, I don't know. 1 o'clock, we start at 1? 10 minutes? 10 minutes? Okay. Okay.
So we'll take a 10-minute break. Just I wanted to inform that to become an American Waterworks India member, we are having, for government officials, we have a 1,000 rupee till 60 years of your retirement age, one-time fee only. And today, in all conferences, we give 20% discount, so at about 800 rupees, you can become a member of AWWA. And you will get all the benefits of AWWA as a member, even for all publications that you mentioned. You get access to all the publications of AWWA USA also. So it's something of great value, which is being offered. So if you're interested, at the registration desk outside our office.
Some of the stuff So let's talk about some techniques. I'm going to skip over some of the things I think we probably already talked about in context of some of those questions, or some of those calculations. So let's take a look at this. So there's some critical concepts, right? Obviously, keep water from freezing. The heat loss between the source and the discharge has got to be greater than, right? The heat loss between the heat heat loss between the water source and the discharge has got to be less than the heat available before state phase change occurs, right? That requires we manage heat loss, right, add insulation, or provide for heat addition. And first rule of the Arctic, right, if it's going to fail when it's cold. So you really need to consider backups and reliabilities for when things fail, and when they do freeze up, how are you going to thaw them? Okay? So there's a few options for managing water systems. Depth of bury, surface conditions, material selection, we've gone over that quite a bit. Insulation, I'll talk about that a little bit more. Some options for heat addition. Then I'll talk about some system configurations and system designs that we've used in really cold regions that have been effective. Okay. So depth of bury, right? That's the best way. If you can keep it below the frost line, that's the best way to prevent freezing. Right? All the way. If the ground temperature is above zero, you don't have a problem. And so it's a great thing to do if you can do it. Have specifications for your system that will specify that minimum depth of bury. It does tend, when they're deep in cold regions, tend to increase capital and maintenance costs because digging things up is expensive. That's an example of a steam set in Anchorage. There, our depth of bury is 10 feet. For us to dig up a pipe in the winter, we actually had to go thaw the soil. And so we put a boiler in a truck, and we had a number of steam sets that we would put into the ground and thaw the soil, and when it was thawed, then we would dig and repair the pipe. Right? So it does, if it's possible, this is the way to go. Here's a standard design detail from the Anchorage Water and Wastewater Utility talking about the depth of bury, 10 feet. Really works well. Our standard depth of bury in Bozeman, Montana was 6 feet. Where you can maintain that, that's great. Sometimes you can't. Sometimes you end up with those pipes in the frost zone or on the edges of the frost zone. If you know where those places are in your system, you can target your mitigation and management measures for that. You can also, have some impact on the surface conditions, right? Impacting that N ratio. This can be particularly helpful with service lines where you may be able to manage the surface structure to increase the overall thermal resistance of the soil column. Right? Best not to bury them under hard service lines under hard surfaces if you can help it. A snow cover can be a significant and keeping things from freezing up makes a big difference in the frost depth. Material selection, we've talked about that already, I think. The only difference that we've talked about the thermal properties of different pipe materials. That's not the only thing to consider. Obviously, the tensile strength and the physical strength of those materials is important, depending on where you're at, what kind of system you're in. There can be some pretty substantial forces exerted on pipes when you have a freezing front, pipe in the freezing front. So the other materials are, I think, become important. We've talked about this, I'm going to skip this. HDPE pipe is really, at least in Alaska, especially the Arctic Alaska, is the predominant material that's been used. It's got a very low flow resistance, it's very corrosion resistance. The nice thing about it in a true Arctic environment where it gets really cold is it can go through multiple freeze-thaw cycles. You can freeze it up and thaw it, you can freeze it up and thaw it. It can be thawed electrically, which is a significant advantage for metal pipes. It's got a temperature limit, somewhere around 60 degrees, depending upon the material, before it starts to form, it starts to melt, it starts to lose some of its structural integrity. It is got a high coefficient of thermal expansion, you take that into account. But the standard in most Arctic regions anymore is a 1 inch, 22 millimeter service line. Okay. I'll skip that. Just some pipe dimensions. So here's a pipe that's commonly used in the Arctic. I see some examples out here on the very similar pipe on the stands out here, but this is pre-insulated pipe. We call this Arctic pipe. And so that Arctic pipe is really a pipe material. It can be ductile, can be HDPE, surrounded by some high-density polyurethane foam, typically covered by a carcass or an outside pipe. So this is a pipe within a pipe, right? That can be an HDPE smooth pipe. I see some examples out here. In the Arctic, we'll frequently use aluminum corrugated metal pipe. And the reason we do that in the Arctic, I'll show you some pictures, is you run into these things a lot. And so this is it's tougher, right? In many cases, they're putting these pipes on the surface because burying them in permafrost, just not possible. But it's a really robust, very expensive, but robust pipe. Here's an example, right, of some installations. Right, there's a surface installation. These are all butt welded or thermally fused with couplings, and then some sort of foam spacer is either placed in the space between the outer jacket and then wrapped and sealed so that you have watertight and continuous outer covering. Make it all sorts of, it can be buried directly, it can be put on the surface. This is a very, very robust product that gets used extensively around the Arctic, and it may, there may be some opportunities here for you to use some of those things. It makes freeze-up issues significantly better. This will typically be, in an Arctic environment, anyway, 4 to 6 inches. You might get away with less than that. But you can run those insulation calculations and get a feel for how much insulation you would need for different kinds of certain situations. Insulation, we've talked about already in the context of piping insulation, but the other thing I'll mention here real quickly is that you can insulate the soil. And typically we'll use expanded polystyrene. I mean, there's all sorts of things that have been used for insulation. Sawdust, vermiculite, glass foam, right? All sorts of things. But polystyrene, extruded polystyrene sheets are very convenient to work with. They're relatively inexpensive. They have a great thermal conductivity. They're very good insulators. They're structurally stable and they're moisture resistant, which is kind of the most important thing about specifying an insulation material if you're in a water system. If we look back at our thermal conductivities, if it's wet, its thermal conductivity goes to heck, right? So if the insulation gets saturated, you no longer have insulation, you have water or ice surrounding your pipe, and that has a very high thermal conductivity. So making sure it's moisture resistant and structurally integral is important. This is something you can do to really reduce the frost depth, right? It's one of the most effective ways. You can buy these polystyrene rigid foam boards. You can cut them, right, easily in the field. They're relatively inexpensive. They're structurally stable. They're moisture resistant. Typically you want about 1 meter, 1.2 meters across the top of the pipe. They come in typically 40 or 50 millimeter thicknesses. A 150 millimeter thickness of polystyrene, expanded polystyrene, rigid polystyrene boards is equivalent to 1.2 feet of sand, right, or 1 meter of clay. So if your frost depth is 2 meters and you put in 50 meters of polystyrene above the pipe, you've reduced your frost depth right by half. And so this is really a great thing you can do. We talked about the pre-insulated pipe, right? Sometimes, if that's, too expensive or not in the cards, you can't do it. You can place that polystyrene board over the top of your pipe and really reduce the potential impact of frost. And if you want to get even more tricky, you can put a little tent over the top of that board. That becomes harder to backfill and compact. So this is more of a pain. Yeah.
The first time I think insulation is one of the most effective methods to reduce frost depth.
Yes.
So what would be the depth of insulations over the pipe?
So they typically come in 50 millimeter sheets. So typically we'll put one 50 millimeter sheet 1.2 meters, 1.2 meters wide, lay that foam board over the top of the pipe. That's the equivalent of adding another foot of soil material on top of it.
Can you put the pipe on ground after installation?
Can you put the pipe where?
Can we lay the pipe on ground after installation? Over ground. Above the ground.
Once the pipe is insulated,
yes.
Can we put the same pipe over the ground?
On top of the ground?
Instead of going below the ground?
Yeah, that's typically what we'll do with that pre-insulated pipe in the Arctic, is we'll put it on top of the ground. Right? In these cases, like this case here, burying this is not possible. It's a remote site, there's lots of permafrost, it's too expensive to dig and bury it, especially in permafrost, and so we'll put that material on top of the ground and run it that way. But as we did with those quick calculations, right, if you put an uninsulated pipe on the top of the ground and it gets cold, it's freezing. An insulated pipe like this has got a thermal resistance that is possible for it to work on top of the ground.
What are the materials that we normally use for the insulation?
Polyurethane. Yeah, yeah. This material is typically, this is typically a polyurethane. And these foam boards are typically rigid polystyrene, and they've got a spec here, right? There's an example of a rigid polystyrene board. Here's an example of here's a typical detail from Anchorage Water and Wastewater Utility. We're very concerned about hydrants in the utility, and so even though we have a depth of area, there's lots of stuff going on here, right? Lots of joints, lots of bends. A situation where you don't have much flow typically in those hydrants, and so in addition to a deep depth of bury, we'll specify 4 inches of rigid polystyrene insulation laid on top of that hydrant connection to try to mitigate the frost penetrating and causing problems. Relatively inexpensive way to deal with this.
Hydrants are exposed.
Yes, they are. Yeah. So we'll actually, there we would pump them down in the winters to get any residual water out of them. The whole crew would pump the hydrants down and put an antifreeze in there to keep it from freezing. All right, any other questions on insulation? Okay. Yes.
When you put the air release valve on this pipe,
yeah,
air release valve on this pipe, the valve portion will come above the top of the ground.
Yes.
And in contact with the weather, freezing temperature. So how do we solve this problem?
From an air release?
Air release valve, which are located on the pipeline, they normally come out of the ground level, above the level. And then it comes in contact with the freezing weather. How to insulate that?
So you can either put an insulated house over it, right, to protect it, or heat trace it. Yeah. Or put those air release valves in an insulated vault. Those kinds of things. But yeah, if you're exposed out in the atmosphere, you have a thermal conduit there. Okay. So let's talk a little bit about heat addition, heat exchangers, heat tapes, some thawing options. Right. So heat exchangers are pretty common. Lots of commercial off-the-shelf units are available. In many Alaska situations, where we might have a common facility for a pumping station that's got heating, or a wash facility that the community uses, that's being heated with something, right? And so if you got a boiler, right, gas or oil-fired boiler, and there's some waste heat that can be captured off of that and run through a heat exchanger, right, and utilized to put a little bit of heat back into the system. And some of these really small, convenient, off-the-shelf heat exchangers can give you a couple of extra degrees in your system it might be just enough. Especially in those central facilities, pump stations, well houses, those kinds of things where you might be able to rob a little bit of heat. You want double wall heat exchangers. Obviously, to prevent cross-contamination, there's always a risk. But you can do that in small scale, like I've shown here in a couple of these pictures. These are in wash houses or pump houses out in some rural Alaska villages. You can also do this in scale. So in Anchorage, we had a huge heat, we had a 60-inch main line coming into the community from a glacial-fed lake. And we had a big heat exchanger and an agreement with a local power company to take their waste heat and heat our water at scale. 20, 30, 40 million gallons a day. And we were able to add several degrees of heat to that water coming into town, and then be able to wheel that warm water in different places around town. And we knew, for example, that out in this area of town, the depth of bury was shallow and the soils were frost susceptible. And so in the winter, we would take that heated water and start to run it through this system to provide a few extra degrees to keep freezing from happening. And it can work. It's something to think about. More common in small systems is to use heat tracing, right? Whereas where you add heat along the length of the pipe, it's used primarily, right, to keep pipes from freezing, excuse me. You can use it secondarily to thaw a frozen system if you've got enough, enough energy that you can put into it. It does take a long time. You can use fluid-based, glycol-based systems or electric heat tape systems. Electric heat tape systems are probably more common. You have to evaluate that configuration. You can run some of those heat loss calculations that we did, right? We've went through a number of calculations where we estimated the heat loss per unit length of pipe. Okay, that's what you need to then put into your pipe through some sort of heat system. So we're running calculations in heat loss in watts per meter. You can go kind of match that up with heat tape specifications that are also specified in watts per meter. And there's some physical constraints and lengths and those kinds of things, but that's functionally how you would go about estimating how much you would need. Okay? So here's some examples of some liquid heat tracing systems. And so here's that Arctic pipe I mentioned before. And you can see there's glycol tubes inserted on either side of the pipe to do some thawing. Here's another configuration of that pre-insulated pipe with two glycol lines here and, right, a heat tape, all prefabricated into the Arctic pipe. This is one of those examples where it's out in the atmosphere, right? It's not buried. You're probably in a permafrost-rich, right, thaw unstable soil here. In the Arctic, right, when you have those thaw unstable soils, you really don't want to put a warm pipe into frozen ground, because once you melt the ground, the structural integrity of the ground goes to hell, right? It'll dissolve into a mud pit in many cases, and so it becomes a little bit different challenge than we've talked about here. So probably ethylene glycol, we can that every now and then. Somebody gets the wrong material and somebody gets pretty sick or dies. Make sure you use the right glycol if you're going to do that.
Will all the pipe materials take the vagaries of this glycol, or you need a specialized material for a plastic pipe?
Yeah, typically it's plastic pipe. I suppose you could use it in a metal pipe. I mean, you run glycol systems in metal pipes for heating, so. But in these situations, it's almost always a plastic polyethylene pipe to deal with the glycol, as well as the water. Yeah. And a different system for the glycol and water. So the heat tape systems, right? Self-regulated heat tapes are out there. Pretty common in cold regions. They typically consist of a configuration like this, a couple of wires, a coated copper braid, and a pretty, very tough kind of plastic jacket. And they come in typically 6 to 33 watt per meter systems are pretty common, right? They can be placed directly on the pipe. They're much more effective to place directly on the pipe and then insulated. They're easy to deal with in the field. You can cut them to length and make some terminations that are pretty easy to do in the field. They reduce their heat output as temperature rises, so they're self-regulating. You have to be a little bit careful about run lengths. They can't, there's several, a few hundred meters is kind of typical of as far as they can go, and then you have to add another power source. So there's some limitation there, but they're really, really effective for heat taping or tracing service lines, short runs of pipe, areas where you're prone to freezing. It is a very, very useful, really very useful tool in your toolbox for mitigating freezing impacts on cold climate utilities. If you do freeze, then you better have a backup system. It's much more difficult because we've got this thermal inertia, if you will, and when the pipeline is completely froze, you've got to add that latent heat of fusion back into the system before it starts to thaw, and so it can extend the time a lot. It does really help if you've advanced plan for access points and installation of thaw wires, those kinds of things, planning for the potential or the inevitability it'll freeze up and you can go in and fix it. One thing that we will use a lot, especially if you have small diameter metal service lines, is applied current systems. Basically hook up a welder to 2 points on the service line and thaw it with electric current. Now obviously you can't do that with HDPE pipe, right? It's not going to conduct electricity, but copper is a fabulous conductor of electricity. And so you can hook up a common welder to, inside of the house and, the curb stop, or if you thought ahead, maybe hook up, there's a thaw wire installed that you can hook your welder up to on the front and the back and thaw that service line. There's a whole bunch of ways and configurations that you can start to, get some heat into that system, apply the current until the water flows, and then keep it flowing. If you apply the current until the water flows and then you think, oh, I've got it done, right, and then turn the water flow off, it'll freeze up again. So once it's starting to flow, you want to maintain that flow until you're certain, right, you've got that line completely stopped. This is a pretty effective way. In the U.S., we've got a number of tradespeople that every year will market their services, and if your service line freezes up, they'll come out and hook a welder up and thaw your line. I've had them do it at my house, actually. Here's an example of another specification or drawing detail specification from Anchorage Water and Wastewater Utility. This is one where we have installed a thaw wire on a curb stop, and where it hooks, running all the way out to where it hooks to the main. So in this circumstance, this is an installation where we're concerned that we're in frost susceptible zones, and so planning ahead and putting this thaw wire on there makes it really easy to go out there and clamp onto it and apply a current and keep that service line thawed. Much harder if you haven't planned ahead, right? Much harder to dig that up and repair it. So obviously you probably don't want to do this everywhere, but in these places where through your analysis you kind of figured out frost depth and areas in your utility where you're prone to freezing, you can put some of these preemptive measures in place to make your job easier when it thaws out, or when it freezes out. There are some nifty, homemade systems out there. If you can't use electric current, certainly with HDPE and plastic pipes, you're kind of out of luck with electric current. So then you need to use some sort of hot water systems. They take forms of, various probes that you can insert into the line, pump hot water into it, and push it along and get that line to thaw. You can thaw at rates of several minutes a meter if you've got the right kind of system. Frequently, it can work very well unless you've got a lot of bends or kinks or valves and things in the lines that can impede the progress of that probe because you're inserting that probe into the end of the line. It does require an access point. Typically, you pull the meter off inside the house, right, and stick your hot water system, whether it's a commercial one or homemade, into the system and start the thaw. Let me talk a little bit about configuration and design, and I'm going to go in quick here so we have time for questions because I know a few people have got to leave. So some configurations and designs are worth thinking about. Main configurations and some service lines. So obviously, a lot of our systems are single pipe systems. When we have lack of flow, they're prone to freezing. Sometimes, right, you can stage the high density users at the far end of the system, so you're imparting a more constant demand on that system and get flow going through there. Obviously, this is something that requires a lot of advanced planning. It might not always be possible, but if you can't do that, then sometimes you might have to think about some sort of bleeder flow. In general, you want to avoid these long dead-end lines. Those are the ones that cause problems, both at a service line level and also at the water main level. Looped systems are better, right? Loop systems allow you to keep water flowing throughout that system. And so, right, fully or partially looped systems are really advantageous in cold systems. It's rare that you have a cold climate system, a really cold climate system that's not a loop system. Makes it so much easier to circulate flow, makes it easier to actually add heat back to that flow, right? And as long as you're maintaining that flow, you're significantly reducing the risk of freezing. We saw some of the calculations that showed even for insulated pipes that very small velocities can keep flow from freezing, but it doesn't take very long when you don't have flow, even in larger diameter pipes when it's really cold and you have cold temperatures, for those pipes to freeze. And so keeping that flow going is important. It does have operational costs, right? You're pumping water, or you're circulating, if you might be lucky enough to be able to do it by gravity, but typically you're pumping water and it increases those costs. The schematic, we've got this recirculating pump house where water's going in, it's going out. There's some loop links where you can wheel water around the system. That's what we would do at Anchorage. We have a winter operating scenario and a summer operating scenario. We'd actually change the flow direction in the system based on the time of year and the temperature outside, so that we can keep warmer water circulating in loops in the more frost-prone areas of town. And so kind of doing that kind of basic analysis on your system may give you some insights. If you've got dead-end lines that continually cause all sorts of freezing problems, is there a way that you can loop that system back and kind of get flow throughout to be maintained throughout the system? It can be a pretty cost-effective and long-term solution to dealing with cold temperatures. Here's an example of a circulating system that's pretty common in a lot of really Arctic communities. This is a loop system. The mains are looped, but the service lines are looped as well, and I'll talk about that here in just a little bit. This is not typical in most temperate climates, but in really cold temperatures, getting loop flow through the service lines is one really effective way to keep those service lines from freezing up. So I'll talk about the service lines here in a little bit, but here's the looped system, right? And so here we've got water supply coming into the system. We've got the circulation pump. Here's our heat exchanger, and water goes round and round and round, right? So there's flow in the system all of the time. Here's an example of a circulating service line system, right? We call this a slow main system because here's the service line. Oops, sorry. Here's the service line, and so I pull water right out of the main with the circulating pump and then push it back into the main. And so water is continuously flowing through that service line. Demand is then pulled off of the system by the house, that this is a way that you can impose a continuous flow on a service line using one of these fractional horsepower circulating pumps that you can buy off the shelf. And, they're Grundfos circulating pumps. They're pretty common plumbing apparatus, and they're quite reliable, and they're very low horsepower and very low draw. You can run them seasonally. You don't have to run them all the time. But encouraging that flow in that service loop is a great way if you're in really freeze-prone areas. And you don't have to have much circuit. It's called a slow main system because you're pulling water out of the main with a pump. So you don't have to have much flow through there. The other fascinating kind of system is used with this pit orifice system. So this is a unique, like Alaska original, right? One of the guys from the University of Alaska, Fairbanks, Amos Alter, designed this and patented this. But this is a pit orifice system, and the pit orifice sticks down as a copper pipe that's scooped out, sticks down in the flow, right? Pulls water out of one end, circulates it around, right, the service line, back into the other end with the pit orifice on the other side. So the differential head loss between these two is enough to create a circulating flow. This requires a relatively fast flow main velocity in the neighborhood of sewers, which should be 0.3 to 0.6 meters per second, so half a meter per second, whereas you may be much lower rates of the recirculating pump. But this is an elegant solution used in a lot of places in Alaska. Really, really very effective on helping mitigate one of the worst problems with cold temperature utilities, which is freezing of service lines. And so the installation is pretty straightforward. There's just another example of what it might look like in an Arctic guided installation. This is a little, I just got through this in interest. There is a company out there called the Clean Flow Products that make a little unit that will actually come with its own pump and its own little reservoir, and it will automatically circulate, right, water in your system. And so I'll leave that to you to look at. It's kind of slick. I've seen a few people use it. Not really common, but it's kind of an interesting idea. Same concept though, keeping the water line circulating. The other kind of nuance to some of these looped systems is preventing those service line freeze-ups are most of the primary, many times the primary problem. And so one way to do that is to place the mains close to the house. And so in some Arctic communities, this is relatively easy to do. It may not be in your community. It would be very, very hard to do this in a place like Anchorage or a major city. But for some small communities, it might work, right? Where you're running the main very, very close to the house. And you have a very, very short service line, which then reduces dramatically the risk of it freezing. So, there's an example of a system like that in the Arctic, where those lines are very, very close to the house, and you can have very short service line entrances. Right? Instead of several meters, it may just be a short riser, those kinds of things. They can reduce the amount of service line wreck. It's another thing to think about. Also works in those systems. Couple other things. Customer education is a big part of this. I noticed Neil sent me some videos of some things that you've all done, and boy, they looked great to me. But getting the word out about these processes, most homeowners kind of clueless, at least in the United States, they're kind of clueless about their house, right? They really don't know where this stuff comes from, and so a little bit of customer education helps a lot. If you get really cold temperatures and we're worried about it, we can give advices on cracking your lines, really even things that, like opening cabinets, can help a lot to keep service lines from freezing. Lots of times service lines and interior plumbing will freeze if it's close to the exterior wall or it's on the exterior wall. you can keep that plumbing material into interior walls, it reduces that risk a lot. But helping, helping customers understand the issue and what they can do to help mitigate it can be very helpful. This turns out to be often a really great tip that most people don't know about. Open the cabinets, get some airflow underneath the sinks where we can be prone to freezing. So let me kind of conclude here a bit. I've got a few slides on some of the things we talked about yesterday that I'll go through if we want. But here's kind of my checklist, if you will, for managing water systems in cold regions. And so I think the first thing, right, is to understand your climate. And more than just kind of a intuitive feel for your climate, but review your climate, which you all have, but review your historical temperature data, right? Start to calculate these freezing indexes, start to track that freezing index annually. And that's going to let you estimate with a reasonable degree of accuracy, not perfect, but to give a pretty good feel for what the frost depths are throughout your system. And you can then start to kind of identify where in your system you might be prone to freezing, right? Having pipes buried in the frost zone. The second is to really understand your soil conditions. What kind of materials do you have? What's their moisture content on average? Make some estimates of the thermal conductivity, the cold climate utilities manual, and the graphs that I put in the slide presentation can get you pretty close. And then that will help you kind of determine whether or not you can specify what the depth of bury will be, and it also helps you kind of know where your system is prone to freeze up. Then I would suggest developing some specifications to mitigate freezing, right? Specifying these minimum depths of bury. That may be different in different parts of your system depending on what you learn about your climate and the soils. You can put into place some installation standards and requirements, right? Where do you call out rigid foam insulation? Where do you specify that service lines and main lines have to be pre-insulated? Get those materials and specifications in place so that when a project comes, you're ready to deal with that. Right? Look at your pipe locations and configurations. Try to identify these dead ends, which are really the problems. And with the calculations we did, those no-flow conditions are the ones that are really problematic. So avoid those dead ends. Maybe you can encourage some loops into the system. Get some loops, put some loops in to circulate water. And then finally, develop some response plans for freeze-ups. You can make some estimates of how long freeze-ups are going to take with some of the calculations we've done. And so you know if you've got a situation where you've got temperatures and a winter where it's particularly difficult, you kind of know how long things are going to take, and you know if you get a cold snap, what kinds of safety factors and times until freeze-up you're dealing with. If it's a few hours, okay, you might have a problem. If it's a few days, you might be okay. You can kind of know what those flow velocities are going to be required in the system to prevent freezing, either on a service line or a main line level. So you can make some decisions about how to implement those flow strategies. You can develop some strategies for encouraging flow, like bleeding systems, right? Putting bleed points in. If you can do that safely and effectively, or putting loops into the system, and then develop some plans for adding heat. If you've got areas that are prone to heat, to freezing, you may decide that, some heat trace systems or some heat exchangers put in preemptively give you the tools to help mitigate that risk. It's one of these things where if you have even a relatively decent sized system, doing this everywhere gets pretty expensive. You're probably not going to go heat trace your whole system, but you can, I think, with a little bit of effort, a few calculations, and a little bit of kind of engineering judgment, kind of come up with places in your system where some of these mitigation measures make sense. You can put them in place ahead of time. And then when it comes time, right, we've got a cold snap and no snow, and you're worried about freezing, you can plug in heat tapes, you can turn on recirculating pumps, you can advise customers how to bleed, you can put in bleeding systems, those kinds of things. Right? And then you've got your backup plans for thawing frozen pipes, welders, electrical, hot water systems, sometimes steam can also work. You've got to be careful. And then prepare these public outreaches and messages to help your customer understand what the threats are and what the risks are and what they can do to help you. So, let me stop there and see if there are any questions. That's my initial presentation was kind of focused, put it together kind of focused on the whole pipe freezing part, based on some questions yesterday. I had a few slides last night about impacts on water treatment and some of the other things. But let me stop there and see if there are any questions on pipe freezing, some of the calculations we've done, some of the mitigation measures. Yeah. Any questions? Yes. I have a question.
Hello. I want to make a anti-freeze scheme in some of my areas where I come from. The source is a spring source. The location where I had to give the supply is about 10 kilometers downhills. So in winters, I experience freezing of that spring source. That is one point. And the alignment from where the main line will go through is total rocky, hard rock. So this is another second problem. And it goes through undulated valleys, so I cannot avoid siphoning systems. And the source is again an avalanche prone source, so there is no other option with me. And lastly, I have to construct a water treatment plant just nearby the vicinity of the habitation. So this much now these three problems are with me. So would you tell me the solutions one by one?
Well, that's probably not, but yeah, so in your spring source, is it, can you modify the spring source so that you can get, you're taking it right from the surface? You've got a well point, you've got an infiltration gallery that...
It's a kind of a surface, I had to catch surface water from that point.
Yeah, so one thing that we have used, on some of those kinds of systems is to create some sort of infiltration gallery. So I think I've got a slide here actually. Yeah, so there's an example. So there's an example of an infiltration gallery where you can do something as simple as putting in a perforated corrugated metal pipe, right, sunk down at the source so that you're not having to pull right at the surface that's prone to avalanche. That, this gives you a little bit of opportunity to maybe put some insulation and those kinds of things to keep the system from freezing. I'm assuming the spring doesn't freeze up solid, or it does. If the surface freezes solid, it likely doesn't freeze under the surface. And so creating some sort of infiltration gallery, even if it's something simple, can give you a better, more reliable supply. That's what we have done in Bozeman. We have a spring source where we have buried basically collector pipes underneath the surface to collect that water and then transmit it into the system. As far as the piping line from the spring, to your water treatment plant or to the community, this is one of those problems where it's really easy to say just bury it deep enough unless you're in rock right? Or something that's really expensive. And so it may be just uneconomical to bury that line below the frost line. And so then you're looking at, I think, some of these pre-insulated pipes that you can lay on the ground, or you can lay very close to the ground, that have a lot of mechanical integrity, and they're well insulated and perhaps heat traced, so that you can, deal with that shallow depth of bury. Because it doesn't sound like you're going to be able to bury it deep enough to make it, below the frost line.
How about the fittings part being taken care of? Like there would be regulations, lot of fittings also.
If the pressure line, you're okay, right?
For example, the gravity, because it will come from definitely what it says, oxythermal kind of environment. You will have to put up the fittings to be traditional or not traditional.
And most of
that part will be taken care of.
Yeah, most of the Arctic pipe, the HDP pipe's got a number of different fittings for, to deal with all sorts of configurations. As long as you're, if you're using HDP pipe and you're welding those sections together, either butt welding or with thermal couples, you're insulating that joint and covering that joint, and you've got mechanical integrity and pressure integrity on that, on the length of that pipe. If you don't,
that would be the weakest part.
well, I think HDP guys will tell you, and I have no reason to doubt them, right? That once you weld it, it's as strong as the virgin material. Yeah, that's been my experience. This stuff's covered now.
So could you say something about the water treatment plant?
Yeah. So what kind of treatment plant are you putting in? I can talk a little bit about the impacts of temperature on water treatment.
I want to know that what type of precautions should I take while constructing the treatment plant against this heavy freeze?
Yeah. So let me talk about that here. I think it's a good lead into this. So yesterday, a topic came up about the impacts of temperature on water treatment. And I didn't really had planned to address this much, but I added some slides last night to try to kind of talk about some of the major issues. So, right, the biggest issue with temperature on water treatment is the fact that it changes the viscosity of water. And it can change the viscosity of water a lot, right? So the absolute viscosity of water at 5 degrees Celsius is about 1.5 times what the absolute viscosity of water at 20 degrees Celsius is. And so all of the viscosity related processes are going to be impacted, right? That's typically the physical separation, the physical processes, sedimentation, mixing, pumping, head loss, those kinds of things. So nothing really changes, right, as far as the process calculations and design, other than everything is bigger and slower because the viscosity is higher. And so things like settling velocities are reduced because the settling, the sedimentation bases are calculated using, designed using, in theory, Stokes' law, how that particle settles through a water column is significantly impacted by viscosity. And so you're going to have slower, right, smaller overflow rates, larger clarifiers, larger sedimentation basins for the same amount of removal at 5 degrees relative to 20 degrees. Mixing requirements, velocity gradients are going to be impacted by velocity. Head loss and filters is going to be impacted by viscosity. Backwash velocities are actually reduced with increasing velocity. The water is thicker, if you will, it's more viscous, it's easier to fluidize the bed. But the velocity gradient G increases with temperature. And so at low temperatures, what you actually get is it's easier to expand the bed, but it's harder to get the bed to scour. And so you end up having additional mixing times, longer backwash times to get the same amount.
What are the methods to be adopted for the water treatment? What are the methods? What are the units?
All, I mean, what?
Process units.
Process.
All kinds. Yeah, I mean, there's no no real difference in the unit processes for cold water versus warm water. It's just the size of the process. Conventional filtration, fine. Coagulation, sedimentation, flocculation, filtration, great. Direct filtration, great. You just need to account for the viscosity changes and multiply, basically upsize all the unit processes to deal with cold temperatures. So, for example, in a lot of cold temperature, waters that have cold temperatures, tube and plate settlers, right, for clarifier units are very popular because you get lots of surface area in a small footprint, right? So you can have lower overflow rates, get better removal, those kind of things. Membranes, same thing. You can use membranes in warm water and cold water. The flux is dramatically reduced with cold temperatures, and so you have to bake that into your unit process sizing. You're just running everything at a lower flux rate. You're running things at a lower flow rate relative to more temperate climates. But there's no inherent, these unit processes won't work, right? Viscosity changes the physical, the temperature changes the viscosity, which impacts the physical separation parameters. Temperature also affects the reaction rates. So this is an example of a graph that's comparing alum and ferric chloride at 1 degree Celsius at 20 degrees Celsius. Basically shows you that at cold temperatures you have smaller flock size, right? So that reaction of those particles colliding and joining together is slower and less efficient, if you will, at low temperatures, and so you tend to have smaller flocks that form. If you look at the associated graph here on effects of temperature on coagulation, you also tend to have the same coagulant. Much higher doses required at lower temperatures relative to 20 degrees Celsius, but again, because the chemical reaction processes are slower. And so, one of the things that we see a lot in colder climates and waters that have cold temperatures is the use of partially hydrolyzed polyaluminum chlorides and those kinds of coagulants, because they tend to react faster. And that faster reaction is better in cold temperatures. It makes it better suited for cold temperatures. We'll also frequently use some sort of coagulant aid because you tend to have small flock particles, and the coagulant aid will either help them form larger flocks or help them filter better. And so there's a little bit of magic there in picking a coagulants, but lots of experience in the Arctic on relatively cold temperatures, right? Using partially hydrolyzed polyaluminum chloride polymers and flock sizes, and there's a number of vendors out there that will sell you that stuff. The other big thing that will impact the temperature impacts is disinfection. I think that was brought up yesterday. So this is an example of the CT values from the surface water treatment, the US EPA surface water treatment rule. This is the standard that we have to meet in the US for disinfection. It is a combination of disinfection concentration and contact time. And so we look at it in different logs, 1 log, 2 log, 3 logs, 99, 90, 99, 99% removal. What I want to do is point out down here, right, that for a 90% removal of Giardia, we look at Giardia, we look at viruses, to determine what's the contact, the CT time, or dose and contact time required. And so if you go down here and look at 90% removal at 20 degrees Celsius, right, versus 1 degree Celsius, your CT time is 4 times more to get a 90% removal of Giardia at 1 degree than 5 degrees.
Hey, Craig.
Yep.
Can you address the question of what measures we take for the water treatment plant from freezing?
Yeah. So, typically they're indoors. I don't know of a cold climate. Yeah, most of them are indoors, right? There are just too many processes that are much of that plant be outside. And so most all of the treatment plants that I know of that are effective long-term are indoors. So they're housed indoors, put in a building. There are a few, unique kind of things that you have to do in really cold climates for building, right? Construction, but it's not that different from anything else. But putting them inside, and I think what that does then is prevents all those unit processes from freezing. It does place a premium on very efficient unit processes, ones that have a small footprint. So you can reduce the size of your building. So you reduce the heating cost, reduce the capital cost, reduce the ventilating cost. We don't underestimate the fact that you've got to exchange cold air in that building, so that can increase the heating cost. But most water systems are, most water systems are inside. Most wastewater systems, at least part of that, are outside. Right? For example, in Anchorage, our main wastewater plant, 60 million gallon a day primary treatment plant, all of the clarifiers are outside. We would get down to 20, 30, 40 below. We rarely had a problem with icing. Right? If it was transient. Largely because wastewater is generally warmer and stays warmer because you got a significant amount of biological activity. So you can get away with it, if you will, outside. Plus, it's much harder to put a wastewater treatment plant inside. You have all sorts of issues with environments and odors, et cetera, et cetera. And so, the wastewater treatment processes are all going to be affected by temperature the same way water treatment processes are. Viscosity is going to be different, higher or low. The viscosity is going to be higher. Those physical removal processes are going to have to be adjusted. The chemical and biological process rates are going to be reduced because of temperature. But in general, right, wastewaters are warmer. I've seen them in some of the systems I worked at less than 3 degrees Celsius, but typically they're higher. And so you can deal with a lot of that without having to put it inside. On the water side, I think it's much harder.
What is the sir, my question is from slide. My question is that
Yes. Yeah.
We are using here is metallic pipe. So we are using any heat exchanger. It means we are increasing the temperature of this metallic pipe so that the water does not freeze.
Okay.
No, I am asking you.
Oh, can you? You could. Yeah, typically, those infiltration galleries you bury below the frost line.
So, what's the infiltration gallery? We collect the water and we, through gravity of pumping, we can shift it. We can move it to treatment plant.
Right.
Through main pipe. So, second question is that we put probes and hot water. We use a hot water. We use probe and put hot water into the system and into the pipe level. Main pipe level, so to increase the temperature of the water.
You can use a heat exchanger, right? Or you can look at some of these. You have to figure out if you need to do heat exchanger. Can you insulate the pipe sufficiently to keep it from freezing?
Avoid freezing, but we can use heat exchanger and or we can put a pump hot water into the system.
You can. That's hot water into the system is typically a thawing process. So that's what you do after it's frozen. So that's not something that you typically do kind of as a course of regular operation. You would put some sort of heat exchanger in to add heat to the water coming out of the infiltration gallery wall point. Right? You're increasing increasing the temperature as that water is going down your pipeline to town. Does that make sense?
Proposed a winter water supply scheme, and we have proposed 220 household connection. We have to feed water to 220 households in that town.
Okay.
So we have proposed a heat trace cable along with that service connection.
Yep.
So we have, the power will be supplied from the electric connection of the owner.
Yep.
But what will happen? We have not proposed any another alternate power source. But if the city goes out of power for 3 days, as it is a case in those climatic conditions, then what would you suggest us to do?
So
what power source should we connect to? Alternate power source.
Yeah. So I guess a couple things, right? So you've got, make sure I understand the situation. You've got a community where you've got 220 users, and every user is going to have a heat tape, right, wrapped around their service line, and they're going to be responsible for plugging it into their house to keep that service line freezing. And so if the power goes out, what happens? Right? So you can do some of those freeze-up calculations to figure out how long it's gone. So if the power goes out for 3 days, right, and you can run those freeze-up calculations based on your configuration to figure out will those service lines freeze in 3 days or not. If they will, then you think about insulation and heat tape, right? Specify the service lines so they're insulated enough that you can withstand a 3-day power outage. Use that freeze-up time to kind of back calculate, if you will, how much insulation what our factory will be on that service line, even if we're freezing up in 3 days. And so you don't really have many options, right? If you lose power, you don't have heat tape, and it's probably unrealistic to have each individual homeowner have a backup generator, etc. If the whole town goes out, the whole town's out. So you would want to plan for, if you can, kind of a worst case scenario, what kind of insulation and system do I need to specifications do I need in place to kind of minimize the risk that in a 3-day power outage I won't have freeze-ups. Yeah. Or maybe the other option is then, the third option is, well, or you just come up with a situation where you're going to run the risk of a 3-day power outage and let it freeze, but then you've got a system in place to go back through and claw all of those frozen service lines.
2-3 MLD scheme, which you, with your experience you can share the construction cost as well as the operational cost. What is the approximate idea?
For a treatment plant?
No, for a complete water supply system, maybe like 10 kilometers.
Oh my goodness.
Any fair idea with this aluminum or some other?
So I will give you some rough numbers, right? You might see in Bozeman, right? We're probably running just for the pipe, right? Not the pipe backfill, pipe installation, not the road over the top of it, everything. Maybe $1 or $2 a foot. In the Arctic, so what's that? Now I got to convert to meters. $3 a meter, $3 to $6 a meter. In the Arctic, it might be 10 times that. In Anchorage, we were running $10 a foot. So what's that? $30 a meter. Depth of bury, right? 8-10 feet. In Anchorage. In the Arctic, some of those small villages that I have talked about, it could easily be $100 a foot. I mean, that's a really rough number, but I guess, you know, the further north you go and the colder it gets, the more expensive it gets. Yeah. Good question.
economics will be different because how you get the material and input cost.
A lot of that, those Arctic materials are being barged out there, right? So the transportation costs are huge. The construction season is 8 weeks. There's all sorts of factors that go into.
And roughly operational cost for any one.
Yeah.
Operational cost.
Yeah.
Any idea about the operational cost?
Yeah, so I think the biggest change in operational costs, you got obviously your labor with your operators. It's a little bit more labor intensive, but the biggest cost is the pumping and heating cost, right? And so you can kind of do a rough calculation where, you know, you can run some of those basic calculations and come up with an estimate of how many watts you're going to need to add, and then, you know, what's your power cost. That's the additional power cost associated with that.
Yeah, and they recover the whole cost from the users.
That's what I want to know. That's what I want to know. There's no question that they're more expensive systems to operate because you're keeping things moving and you're keeping things heated, and that's just energy, energy, energy.
So I think we are running a bit late. So if you have any questions, after lunch we can take some few questions. After lunch we have one presentation from Mr. Shirish Kavile. It's more on the package water treatment plant, prefabricated. So that may be of some interest to people who are having questions on water treatment. We also give the opportunity to our sponsors to make a few presentations. I think I will try to run the video, it's a 2 to 3 minute video. So before we break for lunch, and then we'll take up the presentations of the.
So making a presentation? Yeah. Now or after?
After lunch. Shop manufactured prefabricated package water.
Of water supply, irrigation and water waste project. Welcome to Unipro Technical Infrastructure Private Limited, where innovation meets excellence. As one of the premier construction companies, we specialize in the construction of water supply, irrigation and water waste projects. Unipro Techno has earned a reputation for excellence and innovation in the construction industry. At Unipro Techno, our commitment to quality and passion for construction have been the driving forces behind our success. With a rich legacy and vision for the future, we stand tall as leader in the infrastructure industry. Unipro Techno Infrastructure was established in 2006 with its starting operations in Himachal Pradesh and thereafter. The company has expanded its operations to states including Uttarakhand, Rajasthan, Jharkhand, Uttar Pradesh, Madhya Pradesh and Manipur. Presently, the company boasts a formidable team of approximately 800 plus engineers and staff members, ensuring the continued success and growth of Unipro Techno Infrastructure Private Limited. With the visionary leadership and over 25 years of invaluable experience of promoter directions Anil Kumar Vashisht, Rakesh Gupta and Anil Madan, a civil engineer, Unipro Techno Infrastructure thrives and spearheads the company's endeavors in finance, design, execution and marketing across various projects. Together, they form the backbone of Unipro Techno Infrastructure, guiding its path to success. The entry of next generation Ankush Vashisht, Siddharth Madan, MBA ISB and Sarita Gupta, an architect, are also forwarding the legacy of hard work and dedication. Handles the construction endeavors of Unipro Techno Infrastructure. Some of our benchmark projects are Lift Water Supply Scheme of Mawa and Bamsan in District Hamirpur, Himachal Pradesh. Hamirpur Down, various schemes, Tehsil Hera, Kundia, Jaisinghpur and Palampur. Multi-village rural water supply scheme Mukhed, District Chhindwara, MP. Water supply scheme to Mandi Town from Ohal River in Mandi. Rural water supply scheme Dhonitalaya, Jharkhand. Barwar Group of Villages Water Supply Scheme, District Jhansi, Uttar Pradesh. Multi-village rural water supply scheme in Dharampur block of Mandi, Himachal Pradesh. Akri, Banjula Pumping Water Supply Scheme, Dev Prayag, Uttarakhand. Urban Water Supply Scheme of Neemka Thana, Jaipur. Apart from these projects, we have successfully executed the following snowbound area project. Lift Water Supply Scheme, Sant Nala for rural Shimla, Chaba, 10 MLD. Lift Water Supply Scheme in a record time of less than 6 months in Tehsil Suni, District Shimla for Shimla Urban. Saloni Water Supply Scheme for drought affected area in District Chamba. Water Supply Scheme to various villages in the Sori District, Solan, Himachal Pradesh. Urban and Rural Water Supply Scheme, Dalhousie, Himachal Pradesh. Khajia Lift Water Supply Scheme to all drought affected areas in District Chamba. Water Supply Schemes in Siraz Block, Tunag, District Mandi, Himachal Pradesh. Lift Water Supply Scheme, Saror and Tattapani area in Tehsil Karsok, District Mandi, Himachal Pradesh. DPO Rural Water Supply Scheme and District Mandi and Kullu. Chhota Group of Villages Pumping Water Supply Scheme, Rudraprayag, Uttarakhand. What sets us apart is our commitment to tackling challenges head-on. Our portfolio proudly showcases the successful completion of projects in the challenging snowbound areas of Himachal Pradesh, where executing construction work is exceptionally demanding. In these extreme conditions, Unipro Techno has not only demonstrated technical prowess, but also displayed resilience and adaptability. Now the company has expanded its business to agro and scientific storage of food grains by constructing steel silos for Food Corporation of India, a Government of India undertaking. The company has constructed the steel silo of 50,000 empty capacity at Rohtak, Haryana for storing wheat grains for FCI Government of India undertaking. Unipro Techno Infrastructure Private Limited has witnessed remarkable growth over the years. The turnover of UTIPL in the financial year 2010-11 stood at 12.29 crores. In the current financial year, it is likely to surge impressively to approximately 700 crores, reflecting the company's sustained commitment to excellence and success in the construction industry. Our mission is to become a spearheading force in infrastructure development, contribute to the development of society, work as per the highest work ethics, adopt the latest and most eco-friendly technologies, think globally and act locally.
इस कैमरा में देखिए प्लीज क्या गोलियां खाता रहता है क्या कर गए अंदर हाँ
Thank you. Thank you.
Trying to receive the raw water and dampen the entry turbulence.
At the outlet side of the receiving chamber, there is a mixing or measuring weir or a notch. It is a calibrated scale to measure the flow. The coagulants are added on the downstream side of the weir or a notch over the free fall. There is a free fall about 0.4 to 5 meter on the downstream side of the notch, and it acts as a static mixer or a rapid mixer. This is the coagulation phase. The coagulation water then is passed on to the flocculation tank, where it is slowly agitated with a rotating paddle agitator to achieve multiple recontacts. The settleable floc then is passed through the tube settling tank. These tube settlers are with hopper bottoms. The flocculated water enters into the tube settling tank above the hopper, rises in the upward direction. The solid liquid separation takes place. The clarified water is collected by the collection troughs, and the sludge which is separated in the tubes goes down to the hoppers and is taken out from the system periodically. Final polishing of the residual turbidity is done by rapids and gravity filters or by dual media filters. These filters do not employ mechanical rate controller, but rather they have been designed with the hydraulic control system. The filters are backwashed with the pumps, dedicated pumps, or from the elevated service reservoir. Normally the community's supply reservoir is located near the plant, and one can also take a tapping from the elevated service reservoir to backwash the filter beds. For the small capacity plants up to 3 MLD, normally the air blowers are not provided, only the high rate backwash provision is met. And finally, the disinfection of the water is done by bleaching powder, that is calcium or sodium hypochlorite. This ground level. The water falls from the outlet V-notch weir into the mixing channel where the coagulants are added, and V-notch acts as a dual purpose weir. It also measures the flow, incoming flow, and acts as a static mixer. From here the coagulated water goes to the flocculation tank. This is a paddle flocculator, vertical shaft with a drive mounted on the walkway level with a small HP motor. After the flocculation, the water enters into the tube setting tank through this perforated pipe and rises in the upward direction. This is the tube bank through which the solid liquid separation takes place. The water goes to the top, is collected by the collection troughs. Sludge settles down to the hoppers and it is removed periodically. Clarified water then is passed on to the rapid sand or dual media filter. These are manifold and lateral type underdrain systems are there for this. Now normally 600 to 500 mm of gravel, supporting gravel media is provided. If it is a sand filter, then 600 mm of sand. If it is a dual media, 300 mm sand and 400 mm of anthracite coal. The water passes through the filter and then it is taken over to the pure water sump. Over the pure water sump, a room is constructed, which is a multi-purpose room, which is a control room cum pump house, and the top slab of the pump house is used as a dosing platform for coagulation tanks. This is the actual picture of a 1.5 MLD plant in Ahmednagar region of Maharashtra. This is the receiving chamber where raw water is admitted, flow over the V-notch. Then it goes into the mechanical flocculation tank. Then from the bottom it passes through the tube settling tank. You can see the difference in the turbidity of flocculated water and the clarified water over here. The clarified water is collected in the collection trough, 2 number of collection trough, and through this pipe then is passed on over to the gravity filters. From the gravity filters it goes to this multi-purpose control room, and the roof slab of the control room or dosing tanks are located over here. The drainage from the hoppers of the tube settler and the wastewater from the filter backwash is then collected into the channel and is disposed of to the nearest natural drain. This is another picture of a 0.5 MLD plant on the left hand side and 0.8 MLD plant on the right hand side. You can see the water treatment plant over here. This is a control room, multi-purpose control room, and behind it is the elevated service reservoir of the community. Now in this case, for backwash of the filter, the tapping is taken from the elevated service reservoir. Similarly, you can see a 0.8 MLD capacity plant in the Latur region of Maharashtra. This is a picture on the left hand, a picture of 2 MLD plant at Hatta, Nanded region. The maximum plant which we manufacture is having capacity of 3 MLD. Because after 3 MLD, you have to repeat the plant units in parallel, and then you lose your cost advantage. The plants could be, as you can see in the left hand picture, this plant is located high up in the hill over here. So these are easily transportable plants. Now this is the interesting thing. We have received an inquiry from Kelong in Himachal Pradesh. Incidentally, WS2 EPL's package treatment plants are approved by Government of Himachal Pradesh. So on the left hand side you can see a plan of a 1 MLD plant. These are the process units over here, and this is the pure water sump and a laboratory. Because of the climatic conditions at Kelong, where it is freezing, it freezes always, it snows there. The entire plant is enclosed in a RCC building. The size of the RCC building is about 15 meters by 10 meters. And you can see the cross section on the right hand side. On the left hand side is the water treatment plant, on the right hand side is a sump and a laboratory. And above that, with the 45-degree slope roof is provided to get protection from the snow. Now this entire civil structure will be insulated from the inside with a suitable material, and the room, the entire building will be heated so that it becomes an antifreeze room. This is the another view of the cross section of the plant, which will look like. Now these plants are manufactured at Nasik facility of WS2PL, and the dimensions are made in such a way that they become easily truckable. On the left hand side you can see the entire plant of 1 MLD being transported on a low bed trailer to the site. The erection and commissioning at the site is very easy. It is a simple plug and play system. The contractor has to prepare the civil foundation and the small multi-purpose room over here, and the entire plant can be erected within the duration of 7 days. And if your raw water available and pure water machinery is ready, then the scheme can be commissioned in 10 to 15 days. 0.5 MLD plants require about area of 10 meter by 10 meter, and 3 MLD plants require area of about 30 meter by 15 meter. These shop fabricated or ready to erect plants is an attractive option for speedy execution of water supply schemes. Standardized modular systems, these are standardized modular systems, hence quick transportation and delivery at site. All unit processes are as per CPHA manual, revision March 2024. These plants are small and simple, robust and portable. The container of tank material is 6 mm thick mild steel. These plants are fabricated in 6 mm thick mild steel plates. They require minimum space. And from inside they are coated with 6 mm thick FRP lining to prevent the corrosion of the steel. This state-of-the-art technology is available in the WSP plant at Nasik. Since these plants are shop manufactured, the quality is assured. They are cost effective and sustainable. And quality of the treated water is as per CPHO manual or IS norms. Maximum turbidity, these plants can handle raw water turbidity is around 100 to 300 NTU. And the treated water turbidity from the filter you get is about 0.5 to 1 NTU. Little about the company WS2EPL was established in the year 2016 with one small unit of 20,000 square feet in Nasik at a place called Sinnar. And another, today they have 4 manufacturing units covering area of 70,000 square feet at Nasik and one manufacturing unit at Butibori at Nagpur. The modern manufacturing unit at Sinnar can produce about 15 to 20 plants per month. This is one of the critical part of the prefabricated plant. That is the internal lining of the entire plant with 5 mm thick fiber reinforced plastic. This ensures the age of the plant is 25 years. All the internal components of the plant, from agitator, dosing tanks up to 210 systems, are manufactured in-house. Metropolitan Region Water Authority, National Drinking Water Mission, Rural Water Supply Mission, etc. etc. The product is now approved by Water Supply Department, Government of Himachal Pradesh for application in Himachal Pradesh. Yeah, so that's all what I wanted to tell you. I would like to thank AWWAIndia for giving us the opportunity to make this presentation. Any questions?
Do your company manufacture insulating material or the insulating part?
No, sir, no. We are only manufacture water treatment plants. Normally that part is taken care of by the civil contractor.
You are suggesting only RCC building.
Yeah.
Can we construct that CGI sheet shed?
Yes, definitely there are various options, no issue. What is the cost effective and most robust option that we'll go for? In fact, someone suggested that roofing could be done in the other material.
You will only provide us this WTP.
Yeah, WTP.
But the other building structure that
The principal contractor will supply that.
So what about the O&M?
O&M for commissioning, the company's team will come there and they will give the training to the contractor.
Commissioning, how long you will give us the services of maintenance?
From time to time, whenever it is required by the contractor. Whatever is O&M period is there, up to that we will give the support.
You will train other people also?
Yes, contractors people.
Is there any AMC after that or?
Pardon?
Any AMC after that or period is over?
I didn't get you.
AMC, annual maintenance contract.
AMC. No, normally we do not take those. O&M you said, O&M contracts.
So AMC, periodic visits for maintenance.
No, not that. Frankly, it is not required. There is only one rotating part in the entire plant, which is a flocculator. Otherwise, there is no maintenance required for the plant. Once the operator has been taught the relationship between the coagulant dose and the turbidity, and when he grasps those aspects, then our work is mostly done.
Sir, it is feasible in minus temperature also. I don't think so. क्योंकि आपका 6 mm
No, we are constructing an anti-freeze rooms in RCC to cover the entire plant. The plant will be located inside the building with a sloping roof. As far as the process is concerned, we have tried the process, this process in Gangtok, where the temperature of the water in the winter goes down to as far as 5 degrees centigrade. And in plains, normally we have temperatures of around 15 to 25 degrees centigrade for water.
You manufacture only up to 3 mld, sir?
Yeah.
Not more than.
No, after that it loses its cost effectiveness because you have to construct the trains in parallel. And now above 3 mld capacity, normally the RCC work is preferred by the government organizations. This is basically suitable for the rural, remote, small capacity plant where RCC or masonry construction is virtually impossible.
There at Kelong we need to provide compressed hot air at the inlet to raise the temperature of the water so that the processes can take place.
No, it will not be required, sir. 5 degrees.
I don't think that it will work at that low temperature.
Because as far as our
the temperature will be below 5 degrees centigrade.
Normally 5 degrees centigrade is the minimum temperature.
What would be the cost of 3 mld, sir?
Cost of 3 mld
below 5 degrees centigrade.
In Maharashtra, it is about 81 lakh rupees.
81 lakh rupees.
In Maharashtra.
Including the multi-purpose room with some kind of pump house.
DSR जो है महाराष्ट्र का SSR उसमें 81 लाख रुपए।
Normally in Maharashtra now they have started constructing solar panels by the side of this treatment plant so that the energy cost gets recovered. They supply electricity to the electricity board. In almost all the tender that is now mandatory. And second thing is that in Maharashtra they have made overtime compulsory for 5 years for all sorts of rescues.
What is the cost of your plant per MLD?
Per MLD? For 1 MLD, Maharashtra SSR DSR rates are about 55 lakhs. 55 lakhs.
55 lakhs.
Yeah, 1 MLD. Including all the civil works.
So it will take only the transportation cost up to the Kelong?
Including transportation cost. In Maharashtra.
Including transportation cost. You would charge extra for transportation up to Kelong?
Yeah, definitely. Either it could be taken, transportation cost would be taken care by the contractor or by the manufacturer, depending on their convenience.
How much do you think that what would be the cost of transportation?
Probably
What would be the cost of transportation?
about 3 to 4 lakhs from Maharashtra to site at Kelong. Because I believe that entire plant will come up to Shimla on a 40-feet trailer, and from Shimla onwards it will be transported on 20-foot trailers.
It should go to the Shimla, it should come to the Anandpur.
Whatever the place is, yeah. And the plant will be fabricated in such a way that it has the dimensions of a standard container. That is 8 feet in width and 20 feet in length and 10 feet in height.
Does it need any corrosive paintings frequently?
Yeah, we provide a 5 mm thick FRP lining from inside for the entire plant.
But that is an insulation, huh? That's not a part.
No, that is not. That is a corrosion.
It is epoxy basically.
Epoxy.
It's epoxy with fiber.
So if there are no more questions, then I will thank you all for the patient hearing. Thank you so much.
Thank you very much to AWWA for giving the opportunity to showcase our product and services. So before we start our presentation, I'd just like to introduce my team here. Basically, our presence is here in Himachal Pradesh. He is Mr. Hitendra Chande. He looked after the projects here based in Himachal Pradesh. We have our design engineer and project manager, Mr. Prasad Durge. He looked after all the India projects. Then we have our director, Mr. Sanjay Bhandari. And we have Mr. Vipin Sharma, but unfortunately he is not here today. His brother passed away yesterday, Mr. Bipin Sharma. So, aunt is a So we, Jain Irrigation, we are the manufacturer of HDP pipes, plus we are the service provider. So in this presentation, in this gathering, we would like to showcase you our experiences in terms of the services, and also we want to showcase you the best piping product. Because many of the cases, what we have seen, that tender is good, everything is good, only because of the bad piping material, the project fails. So here we just want to take you through the projects which we have completed. We have completed 24/7 water supply, we have completed desalination plant projects, we have given the pipelines to the sub-zero temperatures. So here in this video we can see this is the large diameter pipe, 1.6 meter diameter pipe. Typically these pipes are used for the seawater desalination plants. So where we take the water from the sea 24/7. So there these large diameter pipes are installed below the sea, and sometimes these pipelines are gravity pipelines, sometimes these are pumping pipelines. So these are few another videos for our large diameter pipes. We will come to our main product, like anti-freezing product. So before that, I just want to take you through the large diameter pipes and fittings. So we can see this is 2 meter diameter pipeline. So we have supplied 6 kilometer pipeline for the thermal power plant in Tuticorin, Tamil Nadu. And then this is 1.6 meter diameter pipeline. Then this is 2 meter diameter pipeline in Dwarka. So basically we supplied for the caustic soda manufacturing plant. So these are the few projects wherein these large diameter pipes are used and installed below the sea. We have some projects wherein these large diameter pipes are used for the canal replacement. So instead of open canals, above ground canals, we have converted everything into underground gravity network of HDP pipes. So in Punjab, we have completed one of the project, Kandi Canal. So there 14 kilometer stretch we have converted into underground network of HDP piping system. So in this case, typically no need to go for the compensation to the farmers, no need to buy the lands, and typically farmers are very happy because their land is not divided into two parts. So nowadays these large diameter pipes are used for the gravity as well as canal replacement, pumping applications, seawater, power plants, all these applications. And these are the photographs or videos taken during the installation. Otherwise, these pipes will be installed down below the seabed, and typically the depth of this water, seawater is around 10 meter and trench is around 14 meters. So around 25 meter drop is there in the sea. So absolutely there is no issue with the load coming on the pipe and all. So because these are the strong pipelines and the flexible pipelines. So our founder chairman, we all are working on the fundamental. He has given us, leave this world better than you found it. So we all follow this mantra. So before we start the presentation, I just want to pass you through the presentation for our company. So our head office is based in Jalgaon, Maharashtra, and we are around 10,000 people in company. Our annual turnover is 8,000 crore turnover. So this is our piping division, is one of the division. We have micro irrigation division, we have food division, energy division. Now we have recently started the hydrogen division also. So hydrogen to electricity. So that is also our energy division. So our annual turnover is 8,000 crore. So it is $1 billion company. So our plant across India and the dealer network. These are the snapshot for our factories in India. Then this is outside India, our plants and depots, dealers. So these are the few photographs for our factories outside India. We have 17 manufacturing plants outside India. So these are the brands by which we sell our products. So typically for the piping side, we have these brand logos. Then we have also the Palm Fresh brand. Typically we sell the Mango Purity Coca-Cola, Nestle. So that is our food division. So our founder chairman, he got the Padma Shri award. Then we have tie-up with US for the agriculture research. President Obama during his visit, he visited us. So we have new variety for the rice which can be grown on the drip irrigation. So this way we have the products which can help the farmers to enhance their capabilities. So HDP pipes, basically these pipes can be used for gravity applications, pumping applications, This can be used below ground or above ground. So absolutely there is no constraint by which we can say that these pipes cannot use in this area or that application. So now to the topic, these are our product. We have sample outside the seminar hall. This can be used for the sub-zero freezing temperature. So we have a puff insulation outside the HDPE pipe. The outside it is the jacket. It is just protective layer to the inside puff insulation. So we have this, at present we have the product up to 315 millimeter diameter pipe with insulation. Otherwise we have products up to 2.5 meter diameter, but we have not developed those because there is no application for that, for the such large diameter. But we have starting from 20 millimeter to 315 millimeter. So this is how these pipes are joined together. Using the bud fusion also and using electrofusion also. These are the typically two types of joints used for the drinking water scheme or 24/7 water supply systems. So in this case, there is a bud fusion joint. We joined using the welding machine only. So using the hydraulic press machine. So it is not a manual joint. It is a bud fusion joint. And then over this part, we will put the puff insulation at the side. In next slide, I will show you how to put the insulation. And this is the joint for the electrofusion. So this is how we encase the in-between part. So we have these saddles. So typically we just cover the saddle at the side and then we insert the foam into this saddle. So this will encase completely at the side. So this is like at the side we are doing the insulation and there is a spray available for the puff insulation. So with this we can get the complete continuity for the HDPE pipe with the insulation. And the wall thickness of the insulation typically depends on the temperature of the surrounding. It is a design parameter. Dr. Gray has explained in a nice way. So we have all the range available for the insulation thickness. Like as I said, starting from 20 millimeter to 315 millimeter, we have the main pipe, which is like the carrying pipe, which is carrying the water. And then these are the conductor or the outside jacket pipe. Then now we will see how the quality of the HDPE pipes matters here. Typically what happens in many projects, or this is our experience, because we are the manufacturer as well as service provider. So we have completed 11 projects of 24/7 water supply across India. And so we have experience of services also. There we are providing services, operation maintenance of 10 years also. So we have both the experiences of the manufacturing of the waste product and providing the services also during the operation and maintenance. And what is our experience? I just want to take you through that. So as a service provider or as a contractor, basically our profit is through the operation maintenance cost. So because of using the best piping material, absolutely there is very least maintenance cost which is coming to us. And that is our clear profit during the operation and maintenance. If we use best piping product, which is the heart of the piping system, then absolutely there is no maintenance during the maintenance time. Only the maintenance is required at few places like valves, maybe some pumping system. Absolutely, otherwise whole network is intact. Absolutely no maintenance is required if the joints are leak proof. And because of that, in some projects we have seen that the leakages earlier it were 40% NRW, now it is 9%. And then in those projects, like this is the Harihar project I am talking about. It is in Karnataka, North Karnataka. It is like a very small township, 30,000 house service connection. But the NRW is up to 9% now, and it is only at the WTP level because there is no backwash arrangement. So in polyethylene we have 3 grades, but typically in market people call HDP. But all the 3 densities are available in the market: low density, medium density, high density. So in this there are 3 grades: E100, 80, and 63. This 100, 80, and 63 this stands for the bar strength of the material. So definitely this is the best material because the strength of the material it is P100. Like in concrete we have 53 grade material, 43 grade cement. So like that we have 100 grade material. So typically we always suggest P100 material for the HDPE piping system. But for some applications like sewerage applications where typically the gravity pipe is going deeper down, there the moment of inertia of the wall thickness matters. So there we recommend P80 material. Otherwise, we always recommend P100 material. The important parameter in HDPE pipe is the life is 100 years, and the life of the HDPE pipe is assured up to 50 years by the standard itself. So this is the minimum required strength. Like in concrete, we have compressive strength, M15, M20, M40. In steel also we test the steel, torch steel, and we check the tensile strength of the steel. Like that in plastic, because this is a flexible material, this is a plastic material. So we are not worried, or the standard is not worried about the strength of the material as of today. So we are checking the strength of the material at the end of 50 years. So this is the flexibility, or this is the design parameter, it is covered in the HDP pipe, that the life of the HDP pipe is very much assured at the design stage itself. So this is the minimum required strength, and these are the values given in the standards like IS standard or ISO standard. So these are different international as well as Indian standard by which we manufacture these 2.5 meter diameter pipes. So starting from 20 millimeter to 2.5 meter. So the process extrusion, we put the raw material, these are the granulars, and we create the pipe. So these granulars or the raw material, it is available in different colors. So as per the design or as per the consultant's recommendation or as per the ISO standard, we use the raw material. Like in few cases, we use blue color pipe. Like I am working in Pune water supply project 24/7. There the blue HDP pipe is used for the drinking water pipelines. Otherwise, black color is recommended. So either of two, or these other pipes are also available. Like for the fiber optics cable for the Reliance Jio network, we have given this duct and they have installed across India. So we got the work order from the Reliance Jio for the complete India, 800 crore order we got it, and we have supplied this HDP ducts for the installation of the cables, fiber optics cable. So this is our manufacturing plant spread over 300-acre area in Jalgaon, Maharashtra. So we can see this is the largest plant in Asia Pacific. This is spread over 6.5-acre area. There is single roof on the one plant, and these are the silos, or we can say we store the raw material in the silos. So one silo is carrying 300 ton of raw material. So like that, we have 30 silos in this campus. So one silos, the size is around 6 meters is the diameter and 50 meters is the height. So this is the capacity we have in terms of manufacturing these HDP pipes and fitting. So one bag is around 40 feet trailer, and we put the raw material, we put the granules in the tank by vacuum. So pneumatically it is added to the silos. So there is no bag of 50 kg we are tearing and putting it. So no human adulteration is done with the raw material. So this is the quality we have in terms of manufacturing the HDP pipe. So the raw material comes to the hopper, and this is the process called as extrusion process. There is a heater which heat the raw material at 220 degrees Celsius, and then it passes through the die. So die means there is a cavity. So through cavity the pipe is formed. Then the very first point there is a vacuum chamber, and then the pipe is manufactured like this. So this is around 70 to 80 meter long length where we manufacture the HDP pipe. And this is the inside view for the HDP pipe. So we have parallel extrusion lines up to the 2.5 meter diameter. So now we can see this is the pipe coming at the end of the 70 meter path. And why this long path is required? Because we are heating the raw material at 220 degrees Celsius, whereas we need the pipe at ambient temperature. So that is why this long path is required, where we put the water, chilled water on the pipeline, like 14 degree water. So because of that, the diameter, ovality and the wall thickness, it is maintained as per the standard, because this is a flexible material. So life of the HDP pipe, it is 100 years. This is not the manufacturer is claiming, but internationally it is available in the codal provisions. So this is the DIN standard, European standard 8074. It is clearly mentioned that life of HDP pipe it is 100 years plus, at least 100 years. And it is a food grade material, because whatever milk bag we have, 1 liter, 2 liter milk bag, it is also polyethylene. It is HDP material. It is basically a human grade material. We can drink the water through these pipes. Then this is the certificate we got from Austria-based consultancy firm. So there is a ISO, in ISO, there is a test mentioned, and if we conduct that test, there is an extrapolation done, and we get the result that life of the HDP pipe, chain HDP pipe, it is at least 100 years. So this is as per the standard. Then Plastic Pipe Institute, Greg already referred. So this is one of the prestigious organization in the world, US. So they have also mentioned life of the HDP pipe is 100 years plus. Basically, it is an inert material starting from 1 pH to 14 pH, acid to alkali to base, nothing reacts to this material. Even the toilet cleaner, that acid comes into the same bag, HDP bag. So it can contain the acid, it can contain the milk, even the small baby milk bottle, it is also of HDP. So it is a food grade material with a longer life because of its inertness. So we have all certifications, like we have WRS certifications, then we have WRC NSF certification, we have INSTA certification. So these are the certifications required in India also, as well as outside India. Like this is for the Nordic region. Just an example, because we have selling these pipes from long back, but these large diameter pipes we have supplied in 2008. That time even there was no IS standard. IS standard just came in 2022, but we have supplied as per the ISO standard. Because these are the international standards accepted by all the desalination plant, power plants, because there is a huge investment in desalination plant. More than 6,000 crore is the investment for the desalination, more than that in the power plant. So typically industry is not going to wait till there is an industry standard. We have supplied, and all the even Indian standard as well as the ISO standard, it is the same, because it is the latest material available. So there is absolutely no change in the Indian standard. So these are few certifications for the France, like European countries. So for all our piping products, we have the certifications. Now the best point is for the HDP is like this is the state of the art manufacturing. Why it is the state of the art? Because the quality is assured at the 3 levels. Absolutely, this is the only piping material. It is not like Chinese manufacturing, but for the product, for the HDP, because the levels, quality levels are at the raw material also. There are national as well as international standard available. So we can check the quality of the raw material, the finished product, and the installation and testing also. So all the 3 levels we can check the quality of the HDP pipe. This is absolutely nowhere available in the conventional piping material. You go for any material, whether it is a steel, it is a concrete. Absolutely, there is no standard for the raw material which can be used for the pipes. So pipes are available up to 2.5 meter diameter, pressure up to 25 internal bar, internal pressure 25 kg bar. So pipes are available in coil form also for small diameter. Yellow color means these pipes are used for the gas supply. This is not for the water supply, but material is the same, HDP. Only the color coding is for the identification. Now this is the code 2022. Pipes are available up to 2.5 meter diameter. Typical joints for the HDP pipes: butt fusion, electrofusion, and a flange joint, mechanical joint. So we have fittings both in fabricated. These are manufactured out of the pipes, and these are the molded components, molded fittings up to 2.5 meter. So these are a few snapshots for the molded as well as the fabricated fitting. So this is the 2 meter diameter stub end. Then this is single mold T. Then these are the puddle flanges, manholes, desilting chamber. Typically in canal water or any water which is coming from the stream, from the dam. So there is a silt and clay. So how to stop the silt and clay from the piping network? So these are the chambers installed in between. So we can trap the silt and clay down below. We can pump it here, or we can have the manual entry from the top. So these are the diffusers. So whatever reject water is coming from the power plant, from the desalination plant, or any municipal corporation, so they can disperse this using these diffusers. So there is a one-way wall, tight flex wall attached at the end. Then these are all the HDP fittings we have. This is the intake arrangement strainer. So we can have the butt fusion joint, and we can collect the water from the water source. So this is just for example. We can have in any shape, like up to 2.5 meter diameter, we can get these strainers. So these are the fluffilators. Then this is a floating submersible pump. Pipes are available up to 2.5 meter diameter. We have the sample outside this conference hall. We take this sample for the exhibition purpose. See the manufacturing plant, the height of the person. This is how we supply the pipe to the site, to one pipe in one trailer. Small diameter pipes are available in coil form. This is our experience for the 24/7 water supply system. So typically not in the sub-zero temperatures, but this is during the normal context. So this is the network. Typically we are providing HDP. So everything is polyethylene. So because of that, leakages are up to 9%. So these are few projects we have completed. Already operation maintenance also completed. 11 projects in India. These are ongoing projects in India. 8 projects. I am working on Pune Municipal Corporation project. So there we are using everything is HDP in that project. So these are all pipes and fitting we are using for the water supply network. These are the meters we are using in Pune, and the beauty of this meter is this meter has the battery life of 12 years. So every 30 seconds there is a one pulse which is reaching to the corporation, and the reading we can see online on the mobile. So this is the first project, utility project in India. Even not the energy, not the electricity, not the gas, nowhere this such type of meters are installed. This is the only project implemented by Pune Municipal Corporation, and we are working. These meters we have purchased from Germany, Xylem. This is the Census brand company. Meters, and in this we are getting the signal by two methods. One is fixed area network, second is walkway or drive-by. So this project is under implementation, and here we have 10 years of operation maintenance also. So whenever we go, we undertake the project. It is not only we supply the products, provide the services, but we actually take the operation maintenance part also, so that the smooth transition will be there and there will be success in the project. So these are all quality certifications we have. Now we will see how the HDP pipe is joined together, because many projects where we are not supplying the pipes, but typically some local pipe manufacturers are supplying, and we have observed that the leakages are only found at the joints. So typically could be two reasons. One is the material is bad, second is the services are bad. So now we will see how the butt fusion joints are done properly. So we can see there is no second material at the joint. It is just parent material we are heating and jointing it together. So this is the jointing machine. This machine needs the electricity supplied by DC set, diesel generator set. These are the two pipes. Either these pipes can be 6 meter, 12 meter, or maybe the coil form. So first phase is aligning the two pipes. So this is the hydraulically operated jointing machine. Then second phase, once both the pipes are aligned together, then we put the trimmer in between. So this is the trimmer, same as the wooden trimmer. It has both the sides, there are blades. So this is the circular trimmer, it rotates and then it cleans both the sides of the pipe. Because maybe at the side there are some particles attached to the thickness, wall thickness of the pipe. So this trimmer will make sure that the matting surface is perfectly vertical. So now the pipe will be pressed against the heater, and then the trimmer rotates, the trimmer rotates. So there is a motor on the top. See, now the motor is absolutely pressed against the pipe and the extra part is removed. Then we remove the trimmer and we put the heater in between. So again the heater temperature is 220 degrees Celsius. So same temperature we are maintaining which was maintained during the manufacturing of the pipe. We heat both the sides of the pipe. Typically this heater is coated with Teflon, so the pipe will not attach to the heater. Now the welder will remove the heater and he will just press it together, and there will be hydraulic pressure on both the pipes. So there will be molecular fusion joint, and there is no second material at the joint. There is no rubbering, there is no solvent cement, there is no adhesive added at the joint part. So the joint is done. So this is a perfectly molecular joint, and we can see the wall thickness at the joint, it is around double. So because of that, we always say that joint is stronger than the pipe. We can remove the extra part if it is like there are applications where solids are passing, then we can remove up to 80 millimeter diameter. So this is how the pipes are after jointing. So there is a chart available for jointing also. This is also this is also skill process. So we have to follow the chart. As per the chart, we have to join the pipe. So it is heated. Both the sides are heated up to 220 degrees Celsius. Many sites we have seen that people are buying the pipes not from the wood manufacturer. The pipes are having the bad raw material or recycled material. So typically the 220 degrees Celsius the pipe is heating before that. So maybe 150 degrees it starts melting and the joint is not a proper joint. So we have seen the leakages only at the joints. So these are the pipelines ready at the site. I have warning, so I'll just take 2 minutes, madam.
It's okay.
Yeah, so we have automatic machines also where everything is mounted on the machine. So everything is controlled by the remote control. So this is the electrofusion joint. There is a coupler available. There is a barcode available, and the joint will be done. So now this is our project in Leh Ladakh. The HDP pipes are supplied for the ice stupa. So typically whenever there is a minus 40 degree, minus 45 degrees Celsius in the atmosphere, the water is sprinkled in the air and there is a formation of ice stupa. So we can see these stupas are maintained for the next season for 6 months. So the water is conducted or conveyed through the HDP pipes, underground network of. So this is how these pipes are supplied in coil form and installed in the trenches. And this basically this area is called desert area, everyone knows. So during the winter summer season, this water can be used for irrigation or maybe for the drinking water. So slowly there is a greenery developed. So height up to 55 feet. This technology is by Dr. Solan. So we are the technology partner. We work on the piping side with him. So these are the HDP pipes. Then we have the sprinkler irrigation systems. So these are the long boom sprinklers by which we sprinkle the water. Because basic aim is to have larger mass for the conical shape. So in the night time, whenever there is a freezing temperature of minus 45, the water is sprinkled from the outside also. So these are the ice stupas. Center pipe is PVC pipe. This is how the irrigation is done. Downside, gravity, or it can be used for the drinking water. See the height of the people, height of the stupa. There is a road, there is a stupa. We have completed few projects like Kelong. There was temperature of minus 5. So these are the HDP pipes we have installed there. So we have just now Dr. Craig he has referred some river water infiltration. So we have completed few projects. I will just go through. These are the large diameter pipes and these are used for the river water infiltration galleries. So this is how there is a river and these are all perforated pipes in the river during the summer time. And we put the gravel on this or locally available sand. And only the filter water will pass into the HDP pipes. So these are the 15 millimeter diameter perforations all along the circumference to these HDP pipes like this. So there will be completely gravel cap of 6 meters. So we have supplied some other projects. These are the pipes with coupler. I waited now, so I will just take 2 minutes. So these are the pipes, HDP pipes. We have also supplied with perfusion jointing. So we can see these are all river water infiltration galleries. Pipes are jointed using the perfusion. Then these are also used for the Suzuki car company in Rohtak. So there we have supplied slotted pipes for removing the water. So thank you very much. If you have questions, I am here. So let the other presentation continue. Thank you very much.
The insulation is factory treated. Only at the joint we put the insulation at the joint part.
No, insulated, you're talking about insulated pipe now. Is there a separate insulation code for the pipe, HDP pipe? No.
Same HDP pipe which we are using for the 4984 drinking water. Only the insulation thickness is calculated as
I request you to please take this offline so that we can have the last few.
So I'm Sandeep Singh Suri, presenting RG Industries.
तीसरा जो नीरू के मैप में हमारे पास है, नीरू का मैप जो है इंडिया में देशों का लाइफ ऑफ इंडिया 45 तो गवर्नमेंट इंडिया उन्होंने वो दिखाया है 100 बोला ना इसमें वो फॉरेन के दिखा रहे हैं जो गवर्नमेंट ऑफ इंडिया का है नीरू मैंगो वो 1 यूज करता है।
I'm Sandeep Singh Suri, representing RG Industries here. We are basically into the business of casting. We are A-class foundries. And in terms of metal castings, we are dealing with ductile iron, cast iron and cast steel castings. Sorry, I guess there is some problem with it. So our capacity is about to 2,000 tons per month, and then annual turnover of about 250 crores last year. So our main, we are doing 3 types of castings right now. Green sand for smaller castings, no bake. I'm just running through the slides quickly because I guess you've got less time. So no bake and sodium silicate. And this is the last foam casting that I'll be just briefing in the last slide. This is our new unit coming up in Lalaru. So we have got all the in-house facilities, right from casting to EPDM, fitting, coating, everything. This is all in-house. So these are the processes, manufacturing processes, which include metal, right from pattern making to finishing, core preparation, everything. So this is just a glimpse of, this is melting section. And this is our machine shop having HMCs, BMCs, turning machines. Everything is done in-house. So we have got the testing facilities, this spectrometer and all the analyzers. We have got this CMM. So this is a coordinate measuring machine. So any component from 1 meter, 2 meter by 1 meter. So we put over here, we get the exact dimensions. In terms of, we can just run it into the CNC and CMC also, the same, we can duplicate anything from it. So the EPDM, we just manufacture it in-house. And now everything, right from your spindles, chuck nuts, everything is in-house. So this is our epoxy coating plant. So we have got 3 verticals in terms of manufacturing. We are into water, automobile and railway. So here we will not touch these 2. We are just gonna just touch the water one. So in case of water, we are into manufacturing of sluice walls, non-return walls, butterfly walls, dual blade check walls, then ductile iron fittings, dismantling joints. So we do it GI, CI and casting. So all types of walls we make. So these are the walls that we make. We have got the in-house life cycle testing facility. So this facility enables us to test a randomly picked wall for 10,000 cycles. So it takes 4 to 7 days to test it, and we give the warranty of 5 years on our valves and fittings. So this is for the low temperature. As we are working with the people in Ladakh, Mr. Iftikhar is over here. We have been working with them from last 4 or 5 years, and we have got our valves installed over there. So there we use G40 valves for up to minus 40 degrees Celsius. It has got an elongation of 15 degrees, 15%. So apart from this, basically we don't use G50 over there also. So, and if the temperature is on lesser than -5, we have used this A148 grade valves over there in Ladakh. So the main purpose over here is that this is a lost foam casting, which we are just right now in the process, and maybe in the next seminar we are just gonna show you our products of lost foam also. So lost foam casting is basically a high precision casting with a very low carbon footprints. So emission is very low. Carbon emission in normal casting is 200 ppm, but in lost foam casting it's 72 ppm. So we can generate quick these castings, and our technology is from Kurtz, Germany. So the material for lost foam casting is EPS, EPP and stemma. So EPS and EPP, stemma is for very high precise surface finish, and for normal surface finish we use EPP, and then for a typical, for example in case of walls we use EPS. So this is a sort of thing that we make an identical pattern, we make an identical item. For example, I have to make a sluice wall, so I cast a wall with an EPS. So this is an EPS casting. So we, in case of the conventional molding, what we used to do is that we used to put a pattern, then there was a drag box, drop box, we used to put a split pattern, split box. So everything is now very much easy right now in this. We make an identical mold of item. For example, this is a engine part. So we make an identical mold of it and put it into box. I will show it. These are these machines. These are the molding machines. So for example, this is a part. This is an engine block. So in case of conventional casting, we will not able to make the engine block. So there what we do, we cast these separately. We make the mold, for example, this 1, 2, 3, 4, 5 parts, we mold it separately and we glue it. and make a full part. And when we make a full part, this is a gluing machine, this is a basically molding machine in which these parts are made. This is EPS. And now, this is a flask. What we do is we put this part, we put a sand over here and place this whole part over here in this flask. And after the sand filling a bit of compaction is done, then a metal, here basically it's not shown over here, basically it's a vacuum over here. We attach a vacuum parts over here, and when the metal is poured over here, this one get burned, this whole EPS, and the metal takes place of this EPS. And this whole, that whatever is residual of it, it's just sucked through this flask by a vacuum. So nothing in terms of carbon footprint just remains over here, and we get a full casting over here. This is, for example, this is a pump. So we make a pump out of EPS, and this is a wall, so we make an identical wall out of EPS, and this is the final product. So this is a motor casing. This is into two, we have glued it, and this is the final product. So the main part over here is EPS. Now the main part is EPS and EPP valve insulation. As we are making valves using this lost foam method, so we have got the mold, so in which we make this. So what we do is that there are two things, EPS and EPP. EPS has got a good thermal resistive value. So it's a good insulator. EPP, on the other hand, it's just 5 to 10% less. It has got less properties. So what we are doing right now is we are working on the combination of both of EPS and EPP. So this is what we are doing right now. For example, in the cold regions, what's happened is when we provide a EPS, so that is a bit fragile over here. We have to put some aluminium foil on top of it. Now what we are doing is we are making an EPS. Internal will be the EPS, and on top of that, this will be the EPP coating, this one. So every wall that we produce, for example, this is a wall that we produce, we have got that will be a perfect fit for this. So what we will do, we will reverse this mold. This is the internal, for example, this is the wall I am producing, I have got the mold of this wall. Now what I will do is reverse this mold and make the insulation of this. So this will be an insulation cell exactly fitting, will be the exact as per the wall. So this is an example of small walls. We will be making it for big walls up to 250 mm, 200 mm. So right now this is a full EPS. This is EPP. This is a hard sort of a, we have seen it in cars, cushions, so we use EPP over there. So right now we will be combining both of these. So the inner lining over here, this will be EPS, and the outer lining will be EPP. So this will be very much safe in colder regions. For example, this here. Sir, this is EPS. This is polystyrene. This is, see, this is expanded polystyrene. So what basically EPP is, these are the small polystyrene, it has got pentane in it. What we do is that, it has the value of 18 grams per liter. So from 18 grams we can expand it to 1 liter. So this is the expander, this is the expander. So what is basically the chemistry behind it is, when we use 18 grams and we expand it, we can expand it to 1 liter. So there is a pentane in it. When we put it into a steam, the pentane bursts and its size increases. So this is the theory behind EPS and EPP. But this is EPS. You may have seen it in packaging. And this is EPP. This is EPS and this is EPP. Now the EPS one is a bit rigid and we can directly put it into ground and anything. But EPS, it's not that, it's a bit fragile. But taking in view the quantities of EPS in terms of insulation, so we are combining both of them. So there is a German machine. What that does is, it basically takes out the mold from this EPS and then it does a coating of 2 mm, 3 mm of EPP on it. So this machine is right now in Kurds. We are importing it in next 2 months. So it will be there in India. So this is what we are planning for the cold regions. So walls of any diameter that will be supplied by us, that will be, we will just provide a shell, temperature, this anti-freeze shell on top of it with a press fit fitting. So this is a technology, these are not done in India till now.
R&D is under progress.
Yeah, it's R&D has been done, machines are under process, so they will be imported in the month of May. So we have already done R&D and we have checked the samples in Germany.
These technologies in any IS code?
No, not in any IS code till now. So this will be providing a full antifreeze. Basically what happens that right now in cold region there are thermal jackets, so we provide, but they are not that effective. But this one it is very much press fit and it is exactly as per the size of the wall. Yeah, it will be handy because we have got the inner mold of the wall, so that we will be using for producing it output. So internal dimensions will remain exactly the same. So we are doing this 2-in-1 process. So this is it, sir. Next time maybe I will be able to I will be present with this product also. Thank you all. Thank you all for giving me the opportunity. Thanks a lot.
Sir, namaskar. Sir, namaskar.
Thank you, sponsors. I just take this opportunity to just thank all the sponsors once more. I'll request one representative from each sponsor to come on stage once. We just have a token from our side. Unipro Techno, please. Anyone from Unipro? From RG and from great solutions, innovative solutions. I hope a lot of many others also take inspiration and develop more products for unique solutions for different difficult problems. Hemant sir, I just invite Hemant sir for the closing ceremony.
I think this brings an end to our seminar and workshop. I hope everybody had a very valuable insight that you took from the workshop and the deliberations that we had. I believe there were certain questions which remained unanswered, and we'll try to see what we can come around on that. Also, the advisor had told that there are certain things which are not covered in the manual. As a result, it becomes quite in a gray area in terms of the guidelines to approve any DPR or guidelines for the department to follow for the upcoming projects. I think this workshop was one of the main reasons to look at these gray areas which are not covered in the manual or are not deliberated a lot. And I am glad that you people could come out and spend 2 days. No, this election is coming on the any week this, and also March ending is there. So, but I am thankful for the state of Himachal Pradesh, Leh, and the other sponsors and the other consultants out from Maharashtra who have come down and spent their valuable time for 2 days over here. Special thanks to Craig. I know Nilash could not deliberate much today because of his bad health, and we'll try to cover up in a webinar that we're planning another about 5 to 6 months with more focused on the concerns that we had in terms of source, storages, distribution, etc. And we'll try and do some issues related to not cold but also hilly states, or the elevations and the pressure issues that are faced for maintaining a 24/7 water supply. I had requested during the lunch break that the participants could draw out and send out their concerns which needs to be raised at national level or even at the ministry level, and from AWWAIndia we would be pleased to forward them and try to deliberate and come out with something which would yield some results for future projects. With that, I would bring a close to this seminar and workshop. Thank you.